Hello, Ajay. Hello.
Good morning, sir. Sir, actually, I am in the Marie Curie Hall, and students are coming and sitting here. We are yes, sir. That I am doing, sir.
Edu-
Hello. Okay.
Good morning to everybody present in this webinar. We are going to start a program. Uh, I would like to invite our student, Miss S. Kritika, to give the welcome address. Okay, thank you, Ritika. Now, I'm going to ask Mr. S. Maheshwaran, our BSc second year chemistry student, to kindly introduce the speakers for today. Please, Mr. Maheshwaran.
Hi, Muhammad. There is no voice.
Hello. Not audible. Hello. Not audible here.
Sir, we are sorry, sir. We are just rectifying the problem.
Excuse me, the previous what Kritika said also is not audible at all.
Yes.
Okay, sorry, sir. Now is it rectified, sir? Now audio is coming.
He also qualified National Eligible Test NET in 2011. He also graduated Aptitude Test in Engineering Gate, India. Sir has published more than 10 research articles in various reputed national and international journals.
Hello. Still not audible. Please make further announcement. Please.
Chennai.
Yeah.
He completed his PhD in IIT Guwahati, Assam, India in 2009. He completed his postdoctoral fellowship at Institute of Molecular Science, Nagasaki, Japan in 2011. He also completed postdoctoral research fellow at Hebrew University of Jerusalem, Israel in 2014. He acted as experimental research officer at Nanoscale Physics Research Laboratory, University of Birmingham, United Kingdom in 2015. He also awarded Young Scientist Research in India. He also awarded postdoctoral research at the NPRL, University of Birmingham, United Kingdom. Next, our another honorable speaker, Dr. S. Ganesh Raj, Department of Chemistry, National College, Autonomous, Tiruchirappalli, Tamil Nadu. He completed his PhD in Pondicherry University in 2014. He also completed postdoctoral research fellowship in Chinese Academy of Science, Dalian, China in 2018. He awarded assistant researcher in Talented Young Scientist Program by China Science and Technology Exchange Center in the year 2018. Thank you.
Okay, thank you, Maheshwaran. Now we are going to ask our esteemed guest, Dr. S. Chandrasekhar, to kindly start his webinar. Dr. S. Chandrasekhar.
Yeah, very good morning.
Good morning, sir.
So first of all, I would like to thank our chairman and principal for giving the good opportunity for the presenting here. Like I will thank for the Comedy department for giving the good opportunity for me and students also for the CSR awareness. And I will thank for other faculty members and other students. So I'll start my presentation.
Sir, 1 minute. Some technical problem is there, sir.
Yeah,
Can you just wait for 5 minutes, sir?
Yeah, sure.
Thank you, sir. Thank you. Good morning, sir. Sorry, sir, for the delay, sir. The technical problem has been resolved, sir. You can start, sir, your presentation.
Can I start?
Yes, sir. Thank you.
So, good morning to everyone. So today we're going to discuss further tips and tricks in the CSIR-NET chemical science examination. So today my talk was arranged in the following manner. So first I'm going to introduction part. I'll discuss about what's the CSIR, why you want to clear for the CSIR-NET exam or JRF exam. So what's the useful for the NET and JRF exam? Then after clear for the NET exam or CSIR like JRF exam, how to enter for the IITs and IIScs or NITs. And followed by I discuss for the naming reaction and rearrangement and some reagent followed by conclusion. So first I'm going to discuss further what's the MSc. After completing MSc, you have only two options. One is you have with the MSc we can go for the job. Then you want to go for the higher studies. If you want to for the higher studies, there will be more than 10 options will be there. If you have directly you want to go for the PhD, you want to clear for the GATE and TIFR and CSIR exams. It is depends on the institutions. If you want to enter for the directly integrated PhD, you want to clear for the IIT JAM exam or GATE exams. So, if you clear for the JRF or NET exams, you can enter for the in IITs. In India, we have IITs, 23 IITs. Once clear for the JRF exam, you can enter for the PhD course. So if you want to go for the teaching with the NET exam, like up to 2080s, NET exam is eligible. After like last year, they made us a compulsory for the PhD compulsory. So you want to for the compulsory for the assistant professor. So you can clear for the CSIR JRF exam and go for the very good institution for the doing the PhD under state university or IITs, ISR, so many institutions available. So other institutions I shown for the like top institution in the India, IIC Bangalore, like we have like ISR 7 institutions and IIIT 26 institutions and the NIT is 31 and the Central University 54 in India and other state universities. So if you want to enter for the IIT, IIC, ISR and IIT and NITs, if you need for the compulsory for the GATE exam or CSIR JRF exam. So if you want to only clear for the NET exam, you are eligible for the assistant professor. They're going to extend for the PhD. That is like next year, it's not not eligible for the NET exam. So other institutions means CSIR of the one institution, particularly chemistry purpose, they like only for the SICRI in Karaikudi, like dedicated only chemistry and CLI Chennai and IIC like IICT and IIP Dehradun also they're doing for the only for the chemistry. So in like Tamil Nadu, they have only for the two CSIR institutions, one is Karaikudi, one is Chennai. Like another particularly for the NCL Pune, this was only used for the organic chemistry. They're doing for the very organic chemistry research in the NCL Pune. So next I'm going to for CSIR-NET chemistry exam pattern. The CSIR exam chemistry pattern like almost 200 marks. This is basically part 1, part 2 and part 3. The part 1 is like 20 question paper will be there. Out of 20, you can answer for the 15 question paper. If answering more than 15 question, they will only consider for the 15 questions. So if the 15 questions, each 2 marks, they will give for the 30 marks. There will be negative mark for the 0.5 mark. Each question, they have negative mark 0.5. In part B, there will be 40 questions. You can answer for the only 25 questions. And the part C also, 16 question paper, there will be, you can answer for the only 20 questions. So basically, if you take the like part A, 20 means there will be general knowledge will be there, remaining chemistry will be there. In part B, 40 marks, whatever 40 questions, they divide for the organic, inorganic, and physical. They take the 75 marks, in organic 25 marks, inorganic 25 marks, and the physical 25 marks will be there. When go for the part C, like 95 marks, there will be 30, 35, 40 will be there. Like almost 33, 34 will be there. So Next, I'll discuss for the GATE exam patterns. The GATE exam pattern, general aptitude is 10 questions will be there. So each first questions, 5 questions for each 1 mark. Next 5 questions, each 2 marks. Next subject questions, we have the 50 questions. First 20 questions, each 1 mark. Next 30 questions for the 2 marks. So here also there will be negative mark. If you take for the 1 mark questions, 1/3 negative mark will be there, and 2 marks, 2/3 negative mark will be there. So you go for the subject wise, there will be 1 mark 1/3 and 2 marks is 2/3. So I'm comparing further like how they asking a GATE exam like subject wise, like subject means topic wise I'm discussing. Like example in 2020 I'm discussing. In quantum chemistry, they asking for the 3 questions. There will be 1 2 mark, 1 mark. There will be 2 mark, 3 mark difference will be there, but compulsory they asking for the 3 marks, 3 questions. And the same like group 3 also they asking one questions. And physical maximum physically asking physical chemistry they will ask for the thermodynamics is maximum questions of 4 marks. In the chemical kinetics 5 marks, first 5 questions. And the electrochemistry 2 questions. And the solid state 2 questions. And the spectroscopy they are asking for the 2 much questions like 8 questions. And the coordination 2 questions. Organometallics 4 questions. So in organometallic also they are asking 4 questions. And come to the organic part. In organic part, stereochemistry, they are asking for the 3 questions. Stereochemistry with aromaticity. And reactive mechanism, sometimes they will ask, maximum the word ask reaction mechanism. They ask for the reagent and a name reaction based reagent. So next I move for the chemistry. First I go discuss for the Baeyer-Williger oxidations. So the Baeyer-Williger oxidations useful for the oxidation of the ketone to ester. So when used for the NCPB, TFPBA, and hydrogen peroxide and PF3. So it is for the reagent. So it is very useful for the cyclic ketone to the lactones. Hello. Hi, are you audible? So, when used for the metacorbenzoic acid, it is popular reagent, the more versatile reagent for the Baeyer-Williger oxidations. So, when go for the peroxyacetic acid, it is called PPA, and per trichloroacetic acid, TFPPA. We can use for the hydrogen peroxide and PF3. So we can use for other reagent also. Normally in Baeyer-Williger oxidation, they will take the substrate of ketone. They will give different oxidation, means different reagent. You should know which reagent is suitable for the Baeyer-Williger oxidations. So I give the maximum reagent for these slides. Maximum will be for the MCPBA. So when used for the ketone or aldehyde, we cannot do the ester. So given the possible mechanism, the metacorbenzoic acid first will attack with the carbon. This oxygen will take place, this hydrogen will come corresponding to the intermediate. The intermediate will come corresponding to the enol formation, will get migrations. This migration based on the electron density. If you have like phenyl and like this R is phenyl, R dash is toluene, the toluene will be more migrative, migration is more because electron density. So we'll get corresponding the ester, we'll get the corresponding the acid. This acid coming from the metacorbenzoic acid. Sometimes in the reactions, they will take the deuterated oxygen, like take the oxygen 18, they will keep the reactions. In the exams and all, they will ask for the only based on the deuterations or like a oxygen 18s or like a bromine, like they will have the isotopes only. They won't ask the directly questions. So you can think which oxygen involving for the migrations exactly. When take for the metacorbenzoic acid, the pink color where is involving for the migrations. Okay, that is very important. Sometimes they will give for the electron density migrations. Sometimes they will give for the electron less density migrations. So it is generally this Baeyer-Williger oxidations, second order kinetics. It is basically rate determined by the like a mode of like addition of like a peroxide and like eliminations. So the electron withdrawing groups like I groups, the peroxides like when you have like a metacorbenzoic acid with more substitutions like chloro, like nitro, the reaction is very fast. Sometimes they will compare the which reagent will give the more fast reactions. Example, metacorbenzoic acid, metal nitro, like that will give so many reagent. You want find out the which reagent will give the more fast reactions. That time you can consider only for the electron withdrawing groups. So I told already, if you have this ketone with a different group, that will be unsymmetrical. That will be depends on the migratory aptitude. This is very reactions. So given for the sum of the migratory groups, first is hydrogen. Then one is like a tertiary alkyl and a cyclohexyl and a secondary alkyl and a benzyl and a array and a primary carbocations and a alkyl and a methyls. So this reaction is a concerted process. This example, you take with a ketone with some chiral moieties, chiral with substitutions. So example is shown for here. You take for the 3-methyl pentane 2-none in the presence of metaborbenzoic acid. There is nothing happening, not disturbing the chiral centers. We get corresponding the ester compound. So when you take the chiral compound, it is not disturbing. So in exam, they will ask. In example, they will use the same reactions. They will ask different product. Example, they will put the 2s or 3s like this. They change the stereochemistry. There will be nothing to change the stereochemistry. They will give the same intensive configurations. So I given for the example for the various oxidations. First, I given for the cyclohexanone in the presence of metaborbenzoic acid in the DCM solvent. We will get the corresponding lactams. So when used for the 5-number ring, we use for the sodium carbonate, the hydrogen peroxide, and the stick unnitrate. We'll get a corresponding the lactams. When you use the presence of lithium aluminum hydride, we'll get corresponding the diols. So like when you read for the based on the CSIR-NET or CSIR-NET exam, when you take the one of the molecules, example you take for the cyclohexanone, you want read properly like cyclohexanone, cyclopentanone, butanone, which one is giving the more fast for the lactams, which one is like which we compare for the like IR values, we can read for the NMR values. Okay, that is very useful. When take the like example, when you can hear me, my voice?
Yes, sir, we can hear you, sir.
Yeah, thank you. So we can use for the multi-purpose. You can think the multi-purpose. Okay. So next I taken with the cyclohexane ketone. In the case, you can see the migration. In the migration case, in the presence of metaborbenzoic acid, sodium carbonate.
நான் வந்து kinetic model, anaerobic digestion.
DCM.
Can
you mute? Too much noise coming.
Sit in education தான் இனிமேல் தான் ரெஜிஸ்டர் பண்ணிருக்கணும் அப்ளை பண்ணிருக்கேன்
எங்க பண்ணிருக்கீங்க
பாரத யூனிவர்சிட்டில
Okay. Next example, I taken with like some bicyclic compound. The bicyclic compound, you can see like when you take the organic chemistry, it like you can read per here IUPAC name also. Example, IUPAC name, you can see this bridge carbon, that is called the bridge carbon. You can see this 1 and 2. This is like right side is 1 and 2, left hand side is 1 and 2, and the bridge carbon is 1. So name called as here bicyclo 2,2 and 1. Like it corresponding the compound name. So always bicyclic compound, you can write right side, left side, then bridge compound. So basically, higher number compound we can put it there first. So the compound is taken in the presence of metaborbenzoic acid. In this same case, we getting corresponding the ester. See here, ester is in this ester. Like bicycle is not migrating, only migrating for the acyl groups. Okay. In the like again, this next step is in the presence of lithium hydroxide. Will get corresponding the alcohol. It is like ester hydrolysis reactions. So next reaction I taken for the norborins. The norborins there will be two product like possible. One is exo, one is endo. in presence of metacarbobenzoic acid in the sodium bicarbonate in the DCM solvent. So here possible like metacarbobenzoic acid, oxygen will attack as a top position and a down position also. See, in the case there will be exo case is more favored because double bond formation will be there. Will get corresponding the lactam formation. In the presence of KOH, will get the corresponding hydrolysis. Will get corresponding the acid compound. So, in possibly in the exam, they will ask like this kind of questions. The incorrect statement of regarding the bare village oxidation. This is like the given first CSIR-NET practice test 2019. So they asking ketone or convert to the ester. The configuration of the microtree group is retained. It is involved the concentrated rearrangement group attached to the carbonyl into the electron-rich oxygen. There is oxidative cleavage for the cis-1 formation. So in the case, you should understand everything. The ketone was converted to the ester. It is correct statement. Next, before I go, the configuration of the migration is almost retention. It is retention. So this statement is also correct. You can see the third statement. Involve the concentrated rearrangement group attached to the carbonyl and the electron-rich oxygen. Not like this. It is third option is incorrect. So the incorrect statement is C option. So we'll take for the example 2. I taken 2 years, 3 years, 2,3 dimethyl cyclohexanone treat with for the MCBA, like in the DCM solvent. You can see here, like one side is substitution, other side is there is no substitutions. So always the migration will take place at the more substitution sites, electron rich side. So in the case, you can see the first example. The first example is the substitution in the like lactone formation in the less substitute site. So this is product is not possible. Okay. So you can see for the B example. There is no stereochemistry is not changing. Both stereochemistry are same, and the lactone formation is more substitution site. Take the example C. There will be lactone formation same, like a more substitution site. The stereochemistry was changing. You can see the D option also. The stereochemistry was changed in the fourth questions. So you can see the options B is correct because like substitution, like just here lactone formation at the more more substitute site, and so there is no stereochemistry change. So I will take for the next example. In the presence of other oxidant, we can get the example same. Like you can same apply for the same kind of conditions, like same concept. We can get the answer here. So we can see here the first one A is like substitute side. You can see the B is same, like more inter side. The stereochemistry is not changing. Okay. So next example I will discuss for the bare relaxations. I taken like a bicyclic compound in the presence of MCBA. Here also is 2 possible. So in the case in the MCBA, we'll get corresponding that like first will the yes, electron formation at the near to for the bridge positions. Like this is a very CH2. This is a like quaternary carbon. We'll take the insertion this carbon positions. We'll get corresponding there. Like the answer is D because we'll take this lactone. We'll go for the further hydrolysis in the presence of sodium bicarbonate. We can correspond the D compound. So next, most important for the very important region, Bombard-Stevens reactions. So here, in exam, they will give directly sometime aldehyde or ketone. They will react with the phenyl hydrogen in the presence of base. We get corresponding the alkene compound. This is basically alkene, like ketone to alkene. When you took the like, when take for the like ketone to alkene, we have so many methods. Like I discussed for the Stevens reactions. Example, ketone to alkene, there will be one more reactions. Peterson Olipinski reaction will be there. They are also using for the triple phosphate. Okay, in the case, we take an ketone, we use for the phenyl hydrogen in the presence of base, we getting for the like alkene. So one more difference will be there. When Stevens reaction and Saffir reactions, there will be 2 differences. So when used for the Stevens reaction in this like sodium methoxide, we'll get for the cis and trans alkenes. When used for the Shafir reaction, we can get for only exclusively trans product. Okay. So in exam, here also they will start with the ketone or tosyl hydrazone. So depends on, you can understand what's like if you use for the ketone and hydrazine, what's the coming intermediate. Then in the presence of base, what will happen? Or directly they're giving for the tosyl hydrazone in the presence of base, what is happening? Which base present? Example, sodium methoxide or lithium nitrate or lithium, like sodium nitrate or lithium nitrate or sodamide. Like you can check base, depends on base. If you're giving for the sodium methoxide, lithium nitrate, and sodium nitrate, that's going for the Stevens reactions. If you're giving for the Grignard reactions or lithium, like a lithium based reagent, they're going for the Stevens like Shafir reactions. Okay, so next I discuss further some examples. It is basically when used for the depends on the solvent. When used for the protic solvent, example take for the water, methanol, and ethanol and acetic acid. So example for C. First I will discuss here. In the presence of base, the first proton will take for this carbon nitrogen that will go for the like migrations. The double bond will migrate here. This SO2 and a toluene ring will replace. Then we get corresponding double bond. Again, this nitrogen load proton will go here, will form corresponding the nitrogen triple bond. So that's taken for that nitrogen triple bond. We get corresponding the disonium ions. The disonium ions is not stable. Okay, it's like a art itself we can decompose. We'll get corresponding the like carbonium ions. The carbonium ions will take for the migrations. We'll get corresponding the EZ and like EZ mixture compounds. Okay. When take for the like aprotic solvent, in the case like a Stevens reaction also depends on solvent. You take for the aprotic solvent like a chloroform and a THF and a DCM. In the case, we're getting for the exactly Z alkenes. So we want to know what's a protic solvent, what's aprotic solvent, what's the difference between the protic and aprotic solvent. You can read that based on the solvent properties. So next I shown for the examples for like Stevens reactions. They directly given for the tosyl hydrogen compound, which is cyclone, in the presence of sodium methoxide in a glycol solvent in the 180 degree. They're getting for the corresponding the EZ product. Okay. Another reaction they're taken for the cyclopropane attached with the ketone, they're directly given for the tosyl hydrogen in the presence of base. They're getting for the 3-member cyclic rings. Okay, cyclopropane rings. So other example I discussed for the Shafir reactions. So same example you can use for the sodium methoxide, we can get for Stevens reactions. When used for the 2 equivalent of butyl lithium, you can get for the Shafir reactions. Okay, so you can see this 2 equivalent. The 2 equivalent first 1 equivalent will go for the less sintered side. Example, this is a methyl substitute side. It is like CH2 side. 1 equivalent of butyl lithium will take the proton here, will form the carbonium. Will go attack here, like we go migrations. The double bond, like carbon nitrogen double bond, will move here. The tosyl will replace. Then there will be nitrogen double bond with that. Again, this one more butyl lithium will take the proton from the nitrogen. Will form the N minus. The N minus will come again. Will form the N triple bond. There will be form the carbons. Okay, carbon will form. So the carbon or like carbonium will like carbonium will attack the aldehyde. Will get corresponding the alcohol product. I shown the like option is 2 will form the corresponding the alcohol. So in the alcohol, so when used for the like you want to make the for the more leaving group. Alcohol is not that much leaving group. So you want to make the productions. They used for this ester group. So they made us alcohol productions. In the presence of acid will get corresponding the alkene and followed by substitutions. So next I am discussing for the Shafir reactions. So in the case, see this very interesting reaction. All the examples, maximum GATE or CSIR-NET exam, even Tamil Nadu TRB exam also, this questions maximum will be there. Okay, I'll discuss for the substrates. Like they given for the directly ketone, like tosyl hydrazine in the acetic acid condition in the base. The presence of acid in the tosyl hydrazine will become corresponding to tosyl hydrazone. So in the presence of base, the example 2 equivalent. The 2 equivalent will take the base, first will take the less sintered side. Okay, less sintered side will go for like same what before I discussed, will go for the migration, will form first will replace for the tosyl hydrazone. Then we form the nitrogen double bond. Then we go for the nitrogen hydrogen. We come for micro means stability. We form the nitrogen triple bond. Nitrogen triple bond. That will be like nitrogen triple bond is like diso is not stable. Then we'll form corresponding that carbon. The carbon will form move to here. Then oxygen will, like epoxide will cleavage. The epoxide minus will be there. The minus epoxide again will form the ketone formations. That time the bond will cleavage. We can correspond in the third options. So you can think about like you given the same options. See, this A options like 1 and 3. They given the same options. You can see that like on the options B, what is happening in the presence of like palladium and calcium carbide. It is a linear catalyst. So when used for the lithium aluminum hydride in the presence of triple bond, example, and first and third options, that will be triple bond will be there. When used for the linear catalyst, we can get for the corresponding cis like Z alkene. When used for the lithium aluminum hydride, we can get for the corresponding trans alkene. So you can think lithium aluminate always give the trans alkene, linear catalyst always give for the cis alkene. So next example I'm discussing for this one. So same things you can apply for here. When given the directly ketones will form the corresponding tosyl hydrogen. So tosyl hydrogen, the given tosyl hydrogen. So they given the sodium borocyanide. So what's the role of sodium cyanide borohydrate? So sodium borocyanide is used for the reduction of imines. Okay. After reduction of imines, we'll go for the 2+2 circular additions will come corresponding to the compound. So next example, the given for the bicyclic compound of the tosyl hydrogen in the presence of 2 equivalent butyl lithium in the DMF solvent. So in the presence of like 2 equivalent, we'll take this one of the one first butyl lithium will take one proton from the CH2. We get corresponding the like carbon. Then carbon like react with formaldehyde, it could corresponding the like formaldehyde, like vinyl carbaldehyde. That is the first options. Next, I'm going to discuss for the conditional reactions. So this conditional reactions, like we have seen that before aldehydes, ketones, this conditional reactions, particularly non-ionizable aldehydes. What's mean the non-ionizable aldehydes? It is there is no alpha hydrogens. Example, benzaldehyde, formaldehyde. There is no near to carbon like CH2 carbon is not there. Only attached to like carbon attached to the hydrogen. There is no carbon then hydrogen. Okay, there is like not like there is no alpha hydrogens. So it is basically disproportional reaction. Why it is calling as a disproportional reactions? There is like one of the aldehydes going for the oxidations, one of the aldehydes going for the reductions. Example, we taken by the 2 kind of aldehydes. We taken by the 2 kind of aldehyde in the presence of base. We getting by the 1 kind of alcohol, 1 kind of corresponding to acids. So we taken for the formaldehyde in the presence of sodium hydroxide. So first base will attack. Example, I'm taking for this example, this benzaldehyde. In the presence of potassium hydroxide, first OH will attack here this benzaldehyde carbon, will form the O minus. So here O minus will be there, here OH will be there, one more hydrogen will be there. So the OH is there is no like that is not stable. Will come for again like ketone formation. The ketone formation, the hydrate will replace, will attack for the other aldehyde. We get corresponding the one of the like alcohol, one is corresponding the acids. So example for next like I discussed for the furfural aldehyde like ketone converted for the furfural acid and alcohols. So next example I discussed for the with after like alpha keto. Example is taken this compound in the presence of alkylic compound. The same like compound they have ketone and formaldehyde. One of the ketone compounds going for the like reduction, one is going for the oxidations. So one more example, this like benzene ring attached to benzaldehyde, like aldehyde in presence of base, converting the one of the molecule, like one of the aldehyde is like acid, one of the aldehyde is alcohol. So basically in exam, they will ask like which among the following undergo the conditional reactions. So before I told there is no condition, is only one condition, there is no alpha hydrogens. Example, you take the acetaldehyde, there will be alpha hydrogens. You take the phenyl acetaldehyde, there also there will be the alpha hydrogens. You compare the acetone, there also alpha hydrogen will be there, two alpha hydrogen will be there. The formality will be there is no alpha hydrogen, that will go for the and like it will undergo for the Cannizzaro reactions. So next question, the Cannizzaro reaction is given for this. Like Cannizzaro reaction is the example of, like they will ask condensation, nucleophilic additions, or alcoholic additions, disproportional reactions like this. So you can remember that always Cannizzaro reactions will go for the disproportional reaction. One is oxidation, one is reductions. So next example I'm going to discuss for the Michael additions. So generally this Michael additions is basic, very basic for the all the reactions. So based on the Michael addition, I'm going to discuss for the Robinson annihilation reactions and Stark element reactions. What's the Michael addition? First of all, the Michael addition is conjugate to the 1,4 additions. Example, first I take the parties like Michael donor. I mentioned it's a Michael donor. Example, all like nucleophile as a acting as a Michael donor. If you have the 1,4 additions, like you can consider as a oxygen is 1 and a carbon position 2 and third and 4. That is called the 1,4 additions. Consider as oxygen 1 and a carbon is 4. Why are you considering as a 1,4 additions? The compared to the like resonance at a more electrophilic nature of the carbon, that's going for the 1,4 addition in the presence of base. That is called as the Michael acceptors. The Michael addition, there will be Michael donor will be there, Michael acceptor will be there in the presence of base, will get corresponding the 1,4 addition of adduct will get. Okay. So after addition of Michael addition in the presence of protic solvent will get corresponding the enol formation. The enol form will get corresponding the ketone, will get corresponding the 3,4 addition of product. What's the 3,4 addition of product? Example, attacking the fourth position is going for the enol formations. So enol formation, after enol formation, when coming for the enol to ketone, that time the double bond will shift to the third position to getting the like hydrogen. So basically attack on the fourth position and getting the third position. So third and fourth position is changing. Basically, like addition is take place. So number of hydrogen or some other group is addition take place. So Michael donor always the CH2 carbon acting as a Michael donors because more active methylene group in the acidic nature. Okay. So example I given for the keto like diketo. Example, this is electron, given the generally electron hexane group, there will be electron hexane group, cyano will be there, nitro will be there, like acid will be there. Okay. Example, like acetoacetic acid, like acetoacetic ester, it's acting as a very good Michael donor. So Michael acceptor. So not only alpha beta anchovy ketone is acting as a Michael acceptor, also ester, nitrile, sulfone, like other compound also will act for the Michael acceptor. So I shown for the sum of the Michael donor, I shown for the esters and like here like ether ketones and the cyano groups. I shown for the Michael acceptor, the double bond and like attached with the ketone or ester or aldehyde or cyanide, like diesters also will act as a Michael acceptors. So in the strong base, like when used for the LDA and sodium hydroxide in the calcium hydroxide, in the presence of protic solvent, that will take the protons. Example used for LDA will take for this more active CH2 position, will take the proton. This acting as a nucleophile. Okay. So it is basically we can go for the two product formation. One is thermogenically controlled 1,4 conjugate addition. It's 1,2 addition. Basically, there will be chances 1,2 addition, 1,4 additions. So when we'll take for the 1,4 additions, when we'll go for the 1,2 additions. So example, take for this 1,4 additions. You take for the more active methylene group, go for the 1,4 additions, we get the corresponding 1,4 additions. In the presence of protic solvent, we get corresponding ketone. Example. So you conjugate like a example used for the 1,2 additions in the lower temperatures. Example used for the protic solvent in the lower temperature that will go for the 1,2 additions. We get corresponding the alcohol. That is for the kinetically controlled 1-2 additions. And shown for the some of the other example for this reaction, like Michael additions. First Michael additions, we get corresponding compound. We get like for the enol we get corresponding ketone compound. So another example taken by ethyl acetoacetate, the like we get go for the like 1,4 additions. We get corresponding enol formations. We get corresponding the ketone compounds. So based on this Michael addition, I'll move on for the Robinson annulations. What's the Robinson annulations? Robinson annulations, they call it as a Michael addition followed by the aldol condensations. What's the Michael addition? Before we discussed, the octamethyl group will attack at the 1/4 positions. We get corresponding the ketone position. That is called the Michael additions. So this Robinson annulation, first we'll take for the Michael additions. Example taken for the diketone. The diketone presence of base will go for the Michael additions. Will get corresponding the ketones, like ketones. The diketones in the presence of excess base. Again, the base will take the proton here. Will pass the carbon ion. Will attack this ketone. Will form the like double bond. Like first will form the alcohol, followed by the water elimination. Will get corresponding the alkyl product. That is called the intramolecular aldol condensations. So next example given for this one, methyl ketone and ketone. The presence of base will get corresponding for the Robinson annulation. Robinson is in the example they will ask Robinson annulation. They will give for the 4 options: Michael addition followed by some other options. They will give example Michael additions they will give followed by other reactions. Michael addition followed by the Rapamensky. Some other like some Glycine reactions, Ekman reactions. They will give the so many options they will give. But you can remember that Michael addition followed by the aldol reaction is the Robinson annulation. You can refer further like so many times asked for the Robinson annulations. Like the name wise they will ask, others they will do the structures, reactions. So I showed for the possible mechanism. The presence of base will take for the active methylene proton, will form the corresponding the carbene, will attack for the 1/4 positions. The enol formation will get like enol formation in the presence of water, will form the vinyl alcohol. The alcohols will get the corresponding the ketone. The ketone presence of like a deprotonation will attack for the aldol reaction, will get corresponding the alcohol. The presence of base will get corresponding the Robinson annulation product. So basically, you can think this one. What's the like Robinson annulation? It's basically alpha beta bond formation, alpha beta bond formation. You see it. Example: this take this carbon. This is key, depends on this blue. Like I mentioned, the blue. It depends on the base this carbon. This is alpha positions. So it is based on this carbon, this is beta positions. So always this alpha positions will attack the beta positions. So one of the reactions, method is over. Next reaction, compared to the next molecule, next carbon position, it is the alpha position. Attack to the this like blue I mentioned for the ketone, attack for the this carbon, like this ketone, there is a beta carbon. So always Robinson annulation will take for the alpha beta and alpha beta reactions. So next before I discuss for the based on the Michael addition, discuss for the Robinson annulation. Next I discuss for the Stark-Enamine reactions. So Stark-Enamine reaction is good for the Michael donor. So in the Stark-Enamine reaction, you can consider the ketone and the secondary amine. When we make for the imine, we use for the Michael acceptor, we can correspond to the Michael addition reactions. Okay. So in the case, like why are given for the here Stark-Enamine reaction, because of the I want focus for the Stark-Enamine reaction, particularly for the Michael additions. So in the case, the Michael addition, they will give for the so many, like before I shown that they will give for the ketone or ester, cyanide in the presence of Stark-Enamine reactions. So that time you want to realize that in the ketone, in the presence of cyanide amine, in the presence of like a Michael acceptor, will go for the Stark-Enamine reactions. Simply they will ask, they will give the ketone one, they will give ketone, second amine. Third one is Michael acceptor. Like this reaction will undergo like a Michael addition, Stark-Enamine reaction, Robinson annulation like that. Then you can understand that in the presence of secondary amine, we'll go for the Stark-Enamine reaction. Okay. So in the Stark-Enamine reaction, when used for the secondary amine, we'll take the Stark-Enamine reactions. When used for the primary amine, what will happen? So when used for the primary amine, in the case of secondary amine, the primary amine case, if the primary amine in the presence of secondary amine, the primary amines itself they will take for the Michael additions. They won't go for the carbon-carbon formation. They will take for the like a nitrogen and a carbon formation will take. That is why the star chemical reaction always will take for the secondary amine. In the exam, they will ask suitable base for the star chemical reaction. They will give for secondary amine, tertiary amine, the primary amine. The most suitable for the secondary amines. So I given for the like other examples like secondary amine, I given for the ketone in the presence of mild acid. So what's the mild acid? So you can use for like mild acid means you can like they will give an example PCl3, POCl3, so sulfuric acid and HCl. The mention they will give different acids and different like base also will give suitable acid for the star chemical reaction like they will ask. So basically you can go with the star chemical reaction, Michelson, Robinson evaluation. You go with Jerry books. So Jerry books, all the examples they covered in the Jerry books for the star chemical reactions, Robinson evaluations, particularly in these reactions. So I taken for different Michael acceptors. So this is a Michael donor. I given for the like acid chloride. I give like we can for the corresponding the CC bond formations. I take here like acid chloride, different acid chloride. Okay, if taken, we can corresponding the 1, 2, like 1, 3 ketones, 1, 2, 3 ketones. So it is also for star chemical reactions. It's very useful for the synthesis of the 1, 3 diketones. Okay, so in the case, see here we can synthesis for the 1, 4 like 1, 2, 3, 4 ketones we can do for the synthesis for the examples. So in the case, I mentioned for some of the examples. So directly the given for the star chemical derivatives in the presence of the given for the Michael acceptor. First we'll go for the Michael acceptor, followed by the like hydrolysis. In the presence of base, we'll go for hydrolysis. We'll get corresponding the ring annulations. So next they ask you for the like Michael, like which is like they given some molecules. Before that they'll give for some molecules. They correspond to the Michael acceptor, Michael donor, like that will ask in the old CSIR exam as GATE exams. Or here also they asking for the retrosynthesis. Example, they will give a molecule. So suitable reagent for this molecule, like that will ask. Then you can fix Michael acceptor, where is Michael acceptor, where is a Michael donor. You can do the retro analysis. You can find a suitable reagent. Okay. So next I will move on for the Rapper-Minsky reactions. So before I discuss for all the reactions based on the ketone with use for the amine and like a Michael donors or tosylitozones like this. So in the case, I use for the alpha esters. So it is also like Grignard reactions or Gilman reactions. Why are you calling us the like Grignard reactions? It is also bromine react with zinc. There will be Grignard reactions, bromine react with magnesium, right? So in that case, in the Rapper-Minsky reactions, compulsory Grignard reactions or Rapper-Minsky reactions you need for the inert conditions. Okay, so the first the zinc react with bromine will form the like alpha zinc bromo like zinc complex. The zinc complex will attack for the ketone will form corresponding the alcohol. So this alcohol plus the acid will go like this alcohol. We'll get like when before the like addition, we'll get the O minus the presence of acid will get corresponding to alcohol. So the Rapper-Minsky reaction will give the corresponding the beta hydroxy ester. So Rapper-Minsky is for the synthesis of the beta hydroxy ester. So in the exam, the CSIR exam or TRB exam, they will ask Rapper-Minsky reaction will give for the 1,4 ketone or alpha hydroxy ester or alpha hydroxy ketone like that they will ask. You should remember the alpha hydroxy ester for the giving the Rapper-Minsky reactions. They will be giving for the, some other reagents also will give, like zinc will give, nickel will give. You can find out which is metal will give for the Rapper-Minsky reactions. Okay, so usually we can use for the almost the Grignard and the Rapper-Minsky reaction THF solvent only. So I'm shown for the mechanism here. First is react with zinc, we have the corresponding zinc bromine like argon zinc reagent. The argon reagent will attack for the ketone, we form the corresponding zinc coordination with oxygen, we form corresponding the presence of acid from the corresponding alcohol. So next next examples I showed with like a same moiety. alpha bromo ester, the presence of zinc and toluene, we get corresponding the hydroxy, the presence of acid, we get corresponding the compound. Other examples I showed, like you can do it for the workup in the home. Like after my presentation, send you the like I share the PPT. You can do the like all the questions I taken from the CSIR, GATE, and others like Pondicherry entrance exam or IAC entrance exam. Like all the entrance exam I taken for the this like discussing for the this CSR presentations. So all the questions so very important for this. Like you can work up, like you do it for the you take like you can do for the workup like you solve all the questions in the your home. So next reaction I'm going to discuss for the Siemens-Smith reactions. So what's the use of the Siemens-Smith reactions? It is basically cyclopropanation of the double bond. You can take for the any double bond, you can use for the cyclopropanations. Why you take for the cyclopropanation with only for the like electron withdrawing group? Okay, so in the Siemens-Smith reactions only work for the electron withdrawing groups. So I have taken for the like here ester, the presence of zinc and copper will get corresponding the cyclopropanation rings. So in the first example, in the presence of like alkene and like in the zinc and copper, what is a suitable reagent? So example C here. So first options there will be cyclopropanations. Second also see. Second options there will be alkene formation. Third option there will be epoxide formations. Fourth options there will be double bond formations. So in the case there will be answer is first. Always Siemens-Smith reactions will be for the like cyclopropanation rings. So here also shown some of the cyclopropanation for example. So first is will form the cyclopropanation. We form the corresponding the presence of acid will go for the like cleavage. We form the diol and diol presence of diol. The sodium per iodide will give the diols will correspond the aldehyde compounds. So here also double bond will be there, will correspond to the cyclopropanation. The cyclopropanation, the presence of ruthenium trichloride and sodium iodide will get corresponding the acid compound. So next reaction I'm going to discuss for the Periyar reactions. So the Periyar reactions very important reaction for the CSIR and the GATE exam and the NET exam and TRB exams. So the Periyar reactions. So what's the Periyar reactions? The Periyar reactions compulsory need for the alpha allo compounds. What's the like alpha allo compound means? It's alpha allo compounds. Okay, it's alpha dash, it's alpha. So alpha ionizable ketones. So it is a compulsory like the Periyar reaction condition like that they will ask, like they will alpha carbon, beta carbon, gamma carbon like that they will ask. So the Periyar reaction compulsory need for the alpha allo ketones. Okay, so you will take for the alpha allo ketones, the presence of acid will get corresponding the acids. So the Periyar reaction we get the corresponding acid or ester we can get it. The presence of depends on the substitutions. We can get for the lactam also. So first we'll take like example shown for this example. The presence of base will take the like alpha proton. We'll take for the like enol formation. We'll come back again. We'll attack for the allo compound. This allo compound will form the corresponding cyclopropanone. The cyclopropanone again will undergo for the presence of base. Will go for the like acid. This acid presence of acid will get corresponding the acid or ester compound. So example take this compound presence of sodium methoxide. Like we'll take the first proton here, we'll attack this, we'll go for ionization, or we'll attack this here, we'll go chlorine replacement, we'll get corresponding there. So like 5 number cyclopropan, like propanone. Again, one more methox will attack this carbon, we'll get corresponding the 5 number ester compound, dibromo compounds. Example, before I discuss for the only a single allo bromo compounds, now we're going to discuss for the double allo compounds. Example, first allo compounds, it will take place for the near to this like this carbon. Because this carbon is almost like too much entered. So this carbon first will take, will go like enol formation, then followed by bromine elimination. Okay, bromine elimination, we get corresponding this intermediate. One more methoxide will go for attack for the ketone, will get for the enol formation. That time we'll replace the bromine, will get corresponding the unsaturated ester, will get it. Okay, so in the case we can get for the corresponding the ketone. First we'll go for the like same things will go for the brominations. we'll get for the corresponding acid. In the presence of acid, there is a no stable, we'll get corresponding the because of why not stable means when you have the alcohol and the acid, we go for the enol formation, like ketone formations, you get corresponding the ketone. So I was like discussing further, say like quick Weber's reactions. What's quick Weber's reactions? It's like all exam they will ask for this example directly. This example is taken from the Jerry March. So in the presence of like base, I first attack this like a ketone. The ketone will go for the like O minus. They'll come back for the ketone. You know, like ketone terrorism. When come back, the phenyl ring will come and attack the chlorine replace. The chlorine replace. Okay, we'll get the substance of the ipso questions. The presence of acid, the presence of acid and the ethanol will get corresponding the ether compound. They will ask in the exam, demineral synthesis from the like that. They will ask. There will be so many options. You can see it is like this phenyl is migrating. Okay, all the case before we discuss only for the, we'll go for the like addition will replace the bromine. In the case migration shift will be. So if you remember some of the example, you can go and work it in your home. If you have any doubt, you can call me anytime. So next time we will discuss for the Beckmann reagent. So one of the very important reactions. So in Beckmann reagent, you want to understand. So the ketone they will do for the amine hydroxide like ammonium hydroxide and some other hydroxide. So different acids, sulfuric acid, HCl, PCl5, PCl3, thionyl chloride, zinc oxide, silica oxide. So when example they're giving aldehyde and amine oxide, they're giving zinc oxide means you want to realize, oh, this is a zinc oxide, it is for the Beckmann reaction. Don't think, oh, zinc oxide is given, it is acid or not, base or not. Don't think like that. Before the going exam, you want to like think which base giving for the Beckmann reactions, which ketone giving, and which acids. Very, very important for the Beckmann reactions, it's acid only. Because they will give a different acid, you won't realize it's going for the Beckmann reaction, some other reagent. So you can go for the Jerry March, given for the very details in the Beckmann reagent, all the acids, you can write it for the, you can like you can see which acids given for the Beckmann reagent. Okay. So mostly they will give for the directly ketone. When amine like ammonium hydroxide will form the like ketoxanes or like ketoxane aldoxanes. Like this in the case, the octane is like very less leaving groups. That is why they taken for the acyl chloride, the protected acyl like acyl chloride. In the presence of like very easily we can migrate, we can leave for the this like nitrobenzyl group. We can correct for the like a migration. We'll take the migration. We'll get corresponding the product. So basically, what we get the like in the Beckmann reactions. So the oxide to the N-substitute amide group. In the example, they will ask what is the use of the Beckmann reactions. Oxide to the amide or ketone ester. They will ask. So you can should remember that oxide to the N-substitute amides. Okay. One more thing here. When you take this stereochemistry also won't change. Always they will ask the stereochemistry. In Beckmann reaction also they will ask stereochemistry based questions. If you have stereochemistry, the migration also there will be like anti-classical migration additional take place. Example, in the case migration won't take this place. The whatever given methyl like a Weaver positions won't take this position. Always anti to the nitrogen. Anti-position to the nitrogen like this like nitrogen and oxygen. So anti-position to the this carbon. So this position will take the migration, will leave the corresponding the acyl absolute nitro or substitute nitrochlorines. Okay, very, very important for the migrations. There will some in the example they will ask the anti-migrations or this kind of migrations. Will give the different product. You can check the always anti-migrations. I given for the some of the examples. You can see here like the given for ketone and like the ammonium hydroxide, the presence of thionyl chloride will get corresponding in the amide chloride. This is also cycloamides. Okay, this is given directly for the oxides. When there is a presence of trivinyl phosphine, the like acetonitril, the water case will get corresponding the amide product. Here also the given the ketones we can use for the ammonium hydroxide. the given different pass like your pass like try 5, you can realize you can answer it. So here the given like ammonium hydroxide, in the case the sulfuric acid, you can see this like which carbon will take for the migrations. In the case like this RT question to this phenyl ring, this phenyl ring will go for the substitutions, will OH will replace, will get corresponding the cyclo closed like this certain will get the followed by the presence of ketone will get corresponding that it is like titanium tetrachloride and zinc will get corresponding that double bond. So it is basically McMurray coupling. Okay, this McMurray coupling also they will ask all the exams. What's a McMurray coupling? So McMurray coupling reagent like this. Okay, McMurray coupling always useful for the ketone to the alkene formations. It's one of the ketone to the alkene formation applications. So down I given for the one more examples. So you can go and work it out. So next I'm going to discuss for the phenol and phenol reagent. It is very useful for the like making ketones like phenolphthaleins. Example, I taken for the diols in diols and glycols. The presence of partial conditions will get corresponding the one of the ketones. Okay, so how it's like how is forming, like how is what is removing, how it is carbocation is forming. It is basically depends on how the carbocation is stabilized the carbon. Example, it is like all the substitutions given for the same substitution methyl. There is no problem. We can get anywhere for the carbocation will methyl shift will get corresponding the phenol reactions. If substitution is different, example, the substitution is like one is methyl, like example 2 methyl 2 phenyl means which is like migratory activities more. Okay, I given here example when form here. See like when form the like if forming the carbocation here is a very less carbohydrate stability. When form the methyl position, there will be more stability. So here will form the more stable carbocation. Then phenyl will shift, will get corresponding the phenol corresponding the product. Okay. So in the case there will be both ring. So in the case will form the corresponding the both the ring are same. So we get a corresponding the carbocation. In the case the ring will CC bond will cleavage will take the corresponding the ring opening and will the form corresponding the from the 5 number rings. In the case the same things will form the corresponding the here carbocations, the double bond like a cyclopentanone, cyclohexanone will ring open, will get the corresponding the cyclohexanone ring, will get the corresponding cyclohexanone rings. So next I'm going to discuss for the benzyl acid rearrangement. So the benzyl acid rearrangement will take for the benzyl, the presence of base will get for the corresponding the benzyl acids. Okay. So first we have the 2 ketones. So we attack the one of the ketones will form the corresponding the O minus. The O minus will come for the again ketone formation. One of the ring will migrate, will attack to the another like alpha portion to the ketone will get corresponding the alpha hydroxy ketones. Like alpha hydroxy acid ketones. This is called a benzylic acid rearrangement. So next, like I discussed before for the like some of the name reaction, some of the rearrangement. So why what I'm discussing for the like Grignard reactions or Gilman reagents, some other reagents. So all the exams, the lithium based or Grignard based or Gilman based, one of the question will be there. So in the Grignard reagent, so how your representing means RMGX. So R will be alkyl, aryl or something, then MgE and halides. Okay. So X is chloro, bromo, iodo will be there. So the Grignard reactions used for the nucleophile. Okay, this acting as a nucleophile. So in the case, in the exam, they will ask Grignard reactions involve the magnesium 0 to 1, 0 to 2, 0 to 3, like they will ask. You can remember that like magnesium is 0 to 2 only take it is like oxidation taking place. Okay. So one more thing, sometimes they will ask like how to wash the magnesium. Like because the magnesium always will oxidize, will get the magnesium oxide. Sometimes you want washed with like HCl, you want to use for the pure magnesium. In sometimes they will give the example, Grignard reaction also magnesium barred by HCl. So we realize that why they given magnesium then followed by HCl. So that what you think that magnesium is not for the pure, you want use for the acid condition, you can get it for the like good magnesium, we can go for the Grignard reactions. Okay. So I'm going for directly like in the reaction also Grignard reactions very important for the solvent also. They will ask for the Grignard reaction suitable solvent part. They will give for the like ether, like a toluene, dioxin. Like this means you can like always ether solvent is suitable for the Grignard reactions because that Grignard reactions more suitable for the ether solvent means the Grignard reagents will stabilize for the ether solvents. Other solvent won't stabilize. The toluene also like penicillin toluene also stability giving, but compared to the ether, the giving for the very less. Okay. So it's shown the like how is stabilizing for the take place. Sometimes they will ask in the like how is stabilizing the monomer, like a Grignard reaction stabilized by monomer, a dimer, like this. Okay, this is a dimer. Like the last 4 number, last 6 number, like cyclization, like the last. You can check the, you can write it and answer it. Or it's forming 6 number or 4 number cyclization, like this. Okay. So I'll move on for some other directly reactions. So we can make for the vinyl magnesium bromide very directly. The phenyl also we can make for the directly the vinyl magnesium bromide. In the case of like alkyne, we cannot make directly for the Grignard reactions. We want to use for the like ethyl magnesium bromide as a Grignard reactions. Sometimes they will they will ask for the like suitable reagent for the vinyl, like a vinyl Grignard reactions. They will do directly MgBr, like magnesium followed by the bromine and ethyl magnesium bromide, like that will ask. So because more arsenic won't form for the Grignard reactions. When we want to create the like a alkyne, we want to use for the ethyl magnesium bromide. So in the case, when used for the generally Grignard reaction with like functional group, like aldehyde is more reactive compared to the ketone than ester than amides. So given for the some of the reactive order. So in the exams, I will have the Grignard reactions reactive order, like they will ask orders aldehyde, ketone, ester, amide, like that. First always more reactive for the aldehyde because less intrinsic. Okay. So I given for some of the Grignard reaction with some functional groups. Example: the Grignard reaction will react with the aldehyde, will get correspond to primary alcohol. When used for the ketone, will get correspond in the tertiary alcohol. In the example, they will ask for the Grignard reaction with the formaldehyde, primary alcohol, secondary alcohol, tertiary alcohol, like that. They will ask always formaldehyde, like aldehyde, will correspond to the primary alcohols. So given for the some of the epoxide and the carbon dioxide. When used for the carbon dioxide, we get the corresponding the acid. When used for the like nitrile, we get corresponding the ketones, and the ester also giving the alcohols because they'll go for the 3 times additions. Okay. So I taken for some of the GATE and CSIR exams. So basically, they taken for they given for directly Grignard reactions. They given for the Michael given the Michael additions. Okay, one of the Michael addition, one of the aldehyde will be there. So you can think about. There will be aldehyde given. If you example like given for the ester, there will be chance will be the 1,4 additions. If you given for the like aldehyde, there will be 1,2 additions. So there will be first is 1,2 addition. The magnesium, like this carbon will attack for the aldehyde, will get for the corresponding the alcohol. Okay, the alcohol. Further, the alcohol will go for the corresponding the oxidations. Like why is oxidation means? Yes, see this one more thing. So given for the allylic alcohol. Normally, Grignard reactions will go for the aldehyde directly. The given for the allylic alcohol will go for the like inside the inside my like resonance will go for the this position 1, 2, 3rd position will go for the aldehyde attack will get corresponding the compound. So I given for one more example. So given for some of the Grignard reactions like acid, ketone, like this, you can work out this one. So generally given for this is also one more examples. So next one I given for the directly Gilman reagent. In example, they will give for the you find out the Gilman reagent. They will give for the Grignard reactions, Gilman reagents. So what's the Gilman reagent? Gilman reagent should be Me2 and copper lithium reagent. Okay. So they will ask Gilman reagent how to prepare the suitable solvent, like that will ask. You can remember what's the Gilman reagent, what's the suitable solvent, like that you can remember. Okay. So Michael, whatever the like Gilman reagents very favorable for the Michael additions. Always Michael additions are for the Gilman reagents. Okay. So in the case, so given the epoxide, the given for the Gilman reagents will attack for the one core question. The epoxide will ring opening, will get corresponding there. One fourth question alcohol. In the presence of zinc and a couple of before discussed for the Siemens reactions, they will go for the cyclopropyl reactions. Okay, I given for another example also. So next I will discuss for bridge reactions. Like I discuss for one of the reagent and one of the I'll discuss for the two reduction reactions. The bridge reactions will take for the benzene, because of lithium, ammonium liquid or like ether solvent, will get for the corresponding the add 1,4 dienons. Okay. So how you are finding for the 1,4 dienons? Why taking for the 1,4 dienons? Why not 3 and why not the 1,4 thing? Okay, this based on the stability. Okay. So in the bridge reactions, they will ask suitable reagent for the bridge reactions. You want to remember that always lithium, ammonium, and ethanol case. You take the sodium, no problem, and ammonia and ethanol. So they will give some of the other conditions also. Okay. So I'll go for directly discuss for the mechanism. The presence of lithium and ammonium case will form the electrons. The electrons, the presence of ring will form the first is single electrons. The solvated electron, the single electron will in the presence of benzene will get the corresponding carbanium. The carbanium will take the proton from the ethanol. Will get the corresponding that 1,4 we'll get the 1,4 diene. The presence of other lithium and ammonium will correspond in the one more single electrons that will take again will convert to the carbanium. Will take for the one more ethanol will get correspond the 1,4 dienes. So here the dienes the registrative will be there. This depends on the electron donating group and electron withdrawing groups. Okay. So you given the sum of the electron withdrawing group and electron donating groups. So what will happen when you have the donating groups, when you have the electron withdrawing groups? When you have the electron withdrawing groups, there will be stabilizing the ipso positions. What's the ipso positions? Ipso positions, there will be substitution on the carbon position. It's called the ipso positions. When you take the exact bridge reactions, other conditions, whatever electrons will attack the fourth positions will stabilize at the ipso positions. Okay. So I given for the here sodium and methanol. The presence of donating groups that will attack will stabilize for the not all ipso positions, other positions, alpha positions. So in the case, examples of our case, we will give sodium and ammonia and ethanol. The presence of HCl will get past this product. The presence of HCl, the vinyl ether will cleavage will form the corresponding the alcohol will get corresponding the ketone compound. So in the presence of acid will get corresponding the ipso positions, stabilizing positions. We get the corresponding the 1,4 dienons. Example, if you have the donating and the withdrawing groups, so more dominating is the electron withdrawing groups. We will get corresponding the ipso position of the acids. So before we discuss now, so if you have the vinyl ethers, example, it's a vinyl ether plus the mild acid, we will get corresponding the ketones. So this ketone is not stable. We will get corresponding the alpha beta and ketones. So I given for some of the bridge reduction examples here. So I taken for some of the other examples. If you have the ethanol and the phenol, so in the case, because in the presence of base condition, phenol will form the corresponding the phenol tiones, so won't involve for the bridge reductions. So you will think that always presence of bridge reduction, phenol in the presence of ester group, withdrawing and donating group will be there. That time will go for the electron withdrawing group, because the phenol always for the ions, the won't undergo for the bridge reductions. So we'll go for the ester, we'll go for the 1,4 cyclones. Given for the toluene acid also, same case. And taken for the pyridine, the case also going for the, it is acting as a electron withdrawing groups, it is giving, and in the presence of acid condition, we go for the hydrolysis, will get corresponding the compounds. So I'm going to conclude by my presentation for the CSIR-NET exams. So I'll prepare the two books for you. One is for the Glyden Warner for this organic chemistry. You can read this organic chemistry book. We can keep like within first attempt, and you go through for the Cox and Norman for the organize this book. Particularly for the Norman, the Norman Cox and books, oxidation reduction, very useful for the all this Cox and Norman. They given for all the examples, particularly oxygen reductions. You can go through these books. The Gladen books you can go through for the selective, hemoselective, regioselectives, and stereochemistry also. They given for that very nicely with good examples. One more thing I will prepare for the Jerry March for the rearrangement. You can go through for all the rearrangement with the Jerry March books. So finally, thank you for all the thank you for all the participant and giving for the I'll thank for the HOD and the other principals also. Thank you very much all.
Thank you very much, sir.
So if you have any questions, can you ask? Otherwise, can we ask personal also? No problem. Anybody have any questions? So I taken basically for the CSIR based important rearrangement and reagent. Okay. Somebody asking some questions? Yeah. Anybody have any questions? Hello.
Yes, sir. We are asking.
I'm not audible. Hello.
Sir, 1 minute, sir. Yes, sir.
Yeah.
Sir, I'm asking students to ask some questions, sir.
Yeah.
You just wait for 5 minutes.
Most welcome. So I'm not audible. Whatever question
There is one question. The student is coming, sir. 1 minute. Can I ask him something?
Good morning, sir.
Yeah, good morning. Very good morning. Yeah, go ahead.
Sir, there are many. So there are many naming reactions there.
Yeah.
Some easiest trick to understand the various naming reaction.
See, when I am doing the CSR preparation, so I will take for the all the name reactions. I will write on papers. I will write on board. So which is starting material, which is giving the product, which condition necessary, what's the stereochemistry. Okay, you can go through for daily. Example, it start only for the rearrangement or reactions. You can go through daily once. Don't need first day very tough to understand. You can go through at least 10 days. You can remember all the reagents, all the starting materials, all the stereochemistry. You can remember all the things. You can make it list also, list. What's the starting material, which part is giving, which is suitable reagent,
Okay.
what's the stereochemistry. What's the rate of the reactions? Sometimes you'll ask the first order, second order like this. Okay.
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 Thank you, sir.
Thank you, ma'am.
Thank you, sir. Thank you very
Hello,
much
sir.
for your
Yeah, one more thing. I'm telling to student.
informative speech, sir. Yes, sir.
Yeah. Yeah. Hello.
Hello, sir.
You can speak,
Yeah.
sir.
Yeah.
Hello.
So one more thing. They when focus
Hello.
for the CS. Hello.
Hello.
So they going to prepare for the CSIR-NET or CSIR exam. They focus for only two subjects. If they want to do PhD in organic, they focus for inorganic and organic. They easily they clear for the CSIR exam. They reading for the all the means inorganic, physical, organic, somewhat tough will be there. They focus for the only two chapters, only organic or inorganic. We can clear for the easily organic chemistry. Means easily can clear for the NET or CSIR exams. So my advice is you can go through for any two topics, organic or inorganic, or inorganic or physical chemistry. Okay. Thank you all.
Thank you very much, sir.
Sir,
Any
excuse me,
other
sir.
question? Yes, sir. Please.
Sir, can we have the PPT for reference, sir?
Sure. I'll give to the college. You can get it from college.
Okay, we can get it in mail, sir, because
Yeah,
I'm from out.
sure.
Okay, sir. Okay. Thank you.
I think the college send you, I think corresponding person will send you this PPT.
We will send it, sir. We will send it.
Yeah, okay, fine.
Okay. Thank you very much, sir.
Yeah,
Thank you for your informative presentation and information towards CSIR, sir.
So the
It
given
is our
for a very
pleasure
short
to,
time.
sir. If
So
you need,
now-
we can arrange one more webinar like this, sir, in near future, sir.
Okay, sir. Okay. Most welcome, sir. Thank you very much.
Thank you very much, sir, for your informative presentation, sir.
Thank you, sir.
Okay, now we will ask for okay, we are moving forward towards our session 2, which is inorganic chemistry, and we will be discussing on coordination chemistry. To discuss this topic, we have our esteemed guest, Dr. A.S. Ganesh Raja, sir. So I would like to ask Dr. Ganesh Raja, sir.
Yeah, I am here. Yeah, I am
Yes,
here.
sir. Good morning, sir. Welcome
Yeah,
to
good
our
morning.
webinar, sir.
Thank you.
Sorry,
morning.
sir. There are some glitches in this webinar, sir. Actually,
No problem.
For that we are very sorry.
No problem. No. That is
So,
not
sir, you
Sure.
can start your presentation, sir.
Yeah. Thank you.
Thank you, sir. Thank you.
So, good morning to everyone. I am very happy to deliver this lecture in national level webinar on tips and tricks in CSIR-NET chemical science examination organized by Department of Chemistry, Periyar Maniammai Institute of Technology. This is one of the very important webinar in this period, because this webinar is very useful for master degree students to achieve JRF-NET and GATE examination awards. So I really thanks to organizer to organize this webinar, particularly Dr. S. Komadi, to give this opportunity to me. Okay. First, our first speaker, Dr. Chandrasekhar, gave clear cut identifications of how to prepare CSIR examination and question paper analysis and top CSIR institute in India. So directly I move to my topic in coordination chemistry. In coordination chemistry, in CSIR examination, yearly 7 to 12 marks comes from coordination chemistry, and 8 to 16 marks comes in gate questions. So today I am only going to focus on coordination chemistry. If I get in future opportunity, I can discuss overall inorganic chemistry topics. So today I am only focusing on coordination chemistry. So I'm going to present my PPT. Can you see my slides?
Sir, it is visible, sir.
Okay, thanks. So in this case, we are going to discuss in competitive exam manner. So I don't like to discuss fundamentals of coordination chemistry, like what is coordination chemistry, what is ligand, what is coordination number, what is oxidation state, counter ion, everything. So if you go to prepare this coordination chemistry topics, you must know all basics of coordination chemistry. So directly I move some important topics in coordination chemistry. Why I choose these are the important topics? Because most of the questions, CSR and GATE questions come from these topics in coordination chemistry. First one, isomerism in coordination compounds, then effective atomic number and spin only magnetic moments, theory of coordination chemistry, particularly valence bond theory, crystal field theory, ligand field theory, and crystal field stabilization energy, John Teller distortion, and last two sections, two topics is stability of complex formation constant and reaction mechanism of coordination complexes. So first of all, we should know coordination compounds is only formed for these transition elements and inner transition elements. For CSR preparation, you should know all transition elements, electronic configurations and oxidation, more stable oxidation states of transition elements, as well as in inner transition elements. These are the electronic configurations of first row transition elements, particularly scandium to zinc. So here scandium to zinc, this unpaired of electrons is present in the 3D orbitals, like one unpaired of electron, two unpaired of electron, and so on. Here zinc is no unpaired of electron. This no unpaired of electron is shows different characteristics of color and magnetic properties. So first topics, isomerism and coordination chemistry. In isomerism, different types of isomerism is present in coordination compounds. One is structural isomerism, another one is stereoisomerism. This structural isomerism is divided into two types. One is coordination isomerism, another one is linkage isomerism. Coordination isomerism means is to exchange ligand on the counter ion in the coordination compound. In linkage isomerism, different donor atoms. You suppose if one ligand having two donor atoms, one donor atom coordinated with one compound, another donor atom coordinated with another compound. So different types of. So first isomerism is molecular same molecular formula but different structural formula, that is isomerism. So here in stereo isomerism, different stereo isomerism also is divided into two types. One is geometric isomerism, another one is optical isomerism. In geometrical isomerism, different arrangement around metal ions. In optical isomerism, it's having a mirror image or not. So first one is this is structural isomerism. Here we have to source to linkage isomerism. This linkage isomerism, this is a nitro isomer compound. This is nitrido isomer compound. In nitro isomer compound, in this ligand having two donor atoms. One is oxygen, another one is nitrogen. If nitrogen is coordinated with the central metal atom, otherwise oxygen can coordinate with the central metal atom. This is this type of isomerism is called linkage isomerism. So in coordination sphere, in coordination sphere isomerism, if this is one compound, chromium complexes, here we have to get different types of coordination isomerism. Here you see this is this coordination sphere, this is counter ion. This counter ion can move to this coordination sphere, this coordinated ligand can move to this counter. This type of isomerism are called coordination sphere isomerism. So in geometrical isomerism, in geometrical we already know about the cis compound and the trans compound. In cis isomers have like groups on the same side. In this case, in this chlorine is having a same side, and ammonia also is having a same side. This is a cis compound. In trans compound, in opposite side, in like groups on opposite sides. So cis and trans isomerism is present in the square planar complex as well as octahedral complexes. This is the optical isomerism. In optical isomerism, these compounds having a mirror image, those compounds is having a optical isomers. This is one compound is shows with in front of mirror to produce another type of another structures of compound. So we have to compare these two compounds with different structural formulas. Therefore, we called this is the optical isomers. In this optical isomers, this is a cis isomers in the octahedral complex. In cis isomers is this is a trans isomer. This is a trans isomers in the octahedral compounds. In trans structures, you don't have optical active compounds. This is a cis compound. These cis compounds having an optical active in the octahedral structure. In octahedral structure, in the further two types of isomers are there. One is facial isomers, another one is meltial isomers. In facial isomers, this is a three identical ligands. The three identical ligands means this donor atom. This is one donor atom. This is one donor atom. This is one donor atom. Same donor atoms. The same donor atoms at present the corners of trigonal face of octahedron. This is the corner of the trigonal space of octahedron. So this type of isomers are called facial isomers. In meritonial isomers, you don't have any trigonal face. The three identical ligands at corners of trigonal meridian inside octahedron. This is called meritonial isomers. So I can move to simple examples of oxidation, how to calculate oxidation states of coordination complex, because oxidation state is very important to identify compounds and the EAN rule. It can applicable to many systems. Therefore, we must to know how to calculate oxidation state of coordination complex. This is the oxidation state of central metal ion. If you don't know oxidation state of central metal ion, we must know about charge of these ligands. This is a neutral ligand, this is anionic ligand. So this chlorine having -1 charge. So 2 chlorine is there. Here water is don't have any charges, that is neutral ligand. So we don't know oxidation state of X, that is central metal atom. So X plus 4 into 0 plus 2 into minus 1 is equal to this outer sphere having a plus 1 charge. So we can calculate yeah, X. The X means oxidation state of central metal ion. So here I am showing some different types of ligands. These are the neutral ligands. This is monodentate ligand. This monodentate ligand means it's donate only one pair of electrons. Therefore, we called this is monodentate ligands. These are all monodentate ligands. This is the polydentate ligands. In polydentate ligands, having tridentate, these compounds having a three donor atoms. Therefore, we call this is tridentate. This is tetradentate, bidentate, so and so on. So this is the anionic ligands. These anionic ligands having a negative charge fluoro, chloro, bromo, iodo, carbonato, cyano, hydrido. Because why I am showing these ligands, you should know charge of the ligands. That is very important to calculate many. We can use these charges in many calculations. Therefore, we should know oxidations, these charges of ligands. This is also anionic ligands. So next I move to effective atomic number. This effective atomic number are octet rule. This effective atomic number is based on the stability of the complexes. Effective atomic number, how to calculate this effective atomic number is equal to Z minus X plus Y. Z means atomic number of metal. X is the number of electron lost during the formation of metal ion from its atom, and Y number of electrons donated by the ligands. How many number of electrons donated by the ligands? For example, this is the hexacyano. This is hexacyano ion 2 plus ions. Here, ion oxidation state is plus 2. Z, Z means atomic number. Atomic number is 26. So we can calculate EAN. So EAN 26 minus 2 means this is the oxidation state. So 26 minus 2 plus 6. So 26 minus 2, 24 plus 6 into 2, 12. So this is 24 plus 12 equal to 36. This 36 is electronic configuration for next nearest inert gas configuration. Therefore, this compounds is more stable, and then this is the this complex is obey EAN rule. So here I am showing some complexes obeying EAN rule. You should remember these complexes because sometimes they give statement for EAN rule. So you should know these compounds obey the EAN rule, and the other compounds is not obeying EAN rule. These are the other compounds is not obeying EAN rule. So this is the one CSIR question related to EAN rule. They gave one general formula of these complexes, and they asked to identify this compound. What is this? What is this right compound? So they gave three complexes here. So we need to identify which one is right one. Here they gave assuming this complex obey EAN rule. They told this compound is obeying EAN rule. What is the formula for a carbonyl complex of manganese? They gave general formula where there is a single covalent bond between the two manganese atoms. That means this is the structure. So this is the covalent bond. Covalent bond means we already know about delta bond. Delta bond having a this one electron, this another electron. So sharing these two electrons. So for this case, it's this bond having one electron. This case, this bond have one electron. So totally, we can calculate for EAN rule. These other two compounds is not obeying EAN rule. This only first compound is obeying EAN rule. In the given compound, atomic number of manganese is 25 and COCO carbon monoxide is neutral. This is a neutral ligand. Carbonyl ligand is neutral ligand. So oxidation state of manganese is 0. In this case, no other ligand. So this is neutral ligand means this oxidation state only 0. So also the number of electrons donated by each ligand. So this each ligands donate 2 electrons. So hence the EAN is equal to electrons of metal plus electrons of donated by ligands plus 1. Why it is 1? Because in this case, this is a covalent character. This covalent bond is having a 1 electron. So we take this 1. So totally we can calculate EAN equal to 25 plus 1 plus 10 equal to 36. So this compound is obey EAN 2. Therefore, this is the answer for this question. So next I move to VPT theory, valence bond theory. This valence bond theory, this theory is only focused on the central metal atom electronic configurations in the outermost orbitals. So, we can take d orbital, s orbital, and p orbital, and then this also explain the hybridizations of these orbitals. This hybridization can give structural properties as well as magnetic properties of these coordination complexes. So in hybridization, we already know about in organic chemistry. Also, we can studied about hybridizations of orbitals. So here, many hybridizations I am showing. This is sp hybridization. Is molecular geometry is linear. So sp2 hybridization trigonal planar, sp3 hybridization tetragonal, dsp2 square planar, and dsp3 trigonal bipyramidal. So many. So in this octahedral structure, D2sp3 or sp3d2 hybridization, that is inner orbital configurations or outer orbital configurations. So these are the examples of these hybridized compounds. So in this case, we can explain inner d orbital, that is inner orbital complex, and outer orbital complex. Inner orbital complex means these electrons from ligands is present in the 3D cell. 3D cell, those compounds we are called inner orbital complex. If electrons electrons from ligand present in the 4D cell, we called outer orbital complex. So whenever it's come inner orbital complex, those complexes having low spin or spin paired complex. This is low spin complex and spin paired complex. Low spin means number of unpaired of electron is lesser than that of high spin complexes. These are the high spin complexes. High spin complexes almost outer orbital complexes and spin free complexes. So in this case, when strong field ligands, we already know about the spectrochemical series. I also in later slides I will show spectrochemical series, importance of spectrochemical series. In this slide, when strong field ligands like ammonia, cyano is very strong field ligand. Yeah, involved in the formation of complexes. They causes pairing electrons. Pairing electron means that the unpaired electrons can get paired. Present in the metal ion. This process is called as spin pairing. So, for example, we take tetrachloronickel 2 plus complex. This is the we should know about the electronic configuration of nickel and the electronic configuration of nickel 2 plus. This is the electronic configuration. This is the D8 system. Because D8 system means in 3D cells having 8 electrons and 4s2. So when it's get oxidized to nickel 2 plus 3d8 and 4s0. So we take here 3d8 and 4s0. In 3d8, in this electrons can filled to obey the Kunz rule. So first off pair and full pair. This is the 3D and 4s0 because nickel 2 plus and 4p. 4p also is the empty orbitals. Suppose these two s orbital and p orbitals to get hybridized to form sp3 hybridization. This sp3 hybridization, this sp3 hybridized orbitals having a vacant orbital. So this vacant orbital can fill these ligands, 4 ligands. This is 1, 1, 1, 1. So 4 ligands from 4 ligands here, chlorine as a ligand. So this complex sp3 hybridizations means it shows tetrahedral structure. So these compounds shows a tetrahedral structure and having a 2 unpaired electrons. So paramagnetic as well as tetrahedral structure. So here we can compare strong field ligand and weak field ligand. This is weak field ligand. This is strong field ligand. We already know about strong field ligand can get pad the electrons, spin pad the electrons. So this is a cyanoligand. This cyanoligand, this electron can pair to this cell. So this electron is moved to this cell to get paired. So this cell it's showing some vacant orbitals. So nickel 2 plus state, this is vacant orbital. So these are the 3 orbitals are there. So in this case, it makes a dsp2 hybridization. So dsp2 hybridization is shows square planar complex. So if chlorine is present in the compound, it's shows a tetrahedral structure with paramagnetic property. Suppose the cyano group present in this complex, this is a square planar complex with a diamagnetic property. This is explained by valence bond theory. So this is one example for how to calculate the valence bond theory and questions from valence bond theory. This is one complex. This is octahedral complex, hexaquo iron 2 plus. They are asking this is outer orbital complex or inner orbital complex. This is diamagnetic property or paramagnetic property. So we can calculate, first we can identify what is the oxidation state of iron central metal atom. Here iron is 2 plus oxidation state because here H2O is neutral ligand, therefore iron is a 2 plus oxidation state. 2 plus oxidation state means D6 system. So D6 system, this is this is the electronic configurations, outermost electronic configurations of this Fe2 plus and the DC system. So here this is the weak field ligand. Therefore, it's not getting any pattern spin pairing. Therefore, it's only shows the sp3d2 hybridization. sp3d2 because the 4d electron. Therefore, this is the outer orbital complex. Suppose this ligand is present in these 2 cells, it may be a inner orbital complex. So this is the outer orbital complex sp3d2 hybridization. Suppose d2 sp3 hybridization means inner orbital complex. This is for this answer for this question, outer orbital complexes and paramagnetic properties. Why paramagnetic properties? Is having a 4 unpaired electrons. So these 4 unpaired electrons may make magnetic properties. Therefore, this is paramagnetic and outer orbital complex. This is the answer for this question. So suppose this is a weak field ligand. Aqua is a weak field ligand. Suppose it's having a strong field ligand. Strong field ligand means cyano. Cyano is one of the strong field ligand. So if you get a strong field ligand, this 2 electron is get paired. It goes to this cell and this electron is goes to this cell. So these 2 cells are having a empty orbital. So we can get D2 sp3 hybridization. So in this case, D2 sp3 hybridization, that is inner orbital complexes with diamagnetic property. So this is another typical examples for 5D system. This is 5D. In this case, nickel, palladium, and platinum. Nickel is 3D, palladium is 4D and platinum is a 5D orbital. So this is 5D8 configuration. In this case, whatever present in this ligand, it may be a strong field or it may be a weak field. We should consider this is all ligands having a strong field. Therefore, in this spectrochemical series, only applicable for 3D series. So, spectrochemical series, that is strong field or weak field, it's only applicable for 3D cells. It's not applicable for 4D and 5D series. So, in this case, this is a 5D series. All the ligands acting as strong field. So, in this case, all ligands having a strong field. Therefore, we only get hybridization D2sp3 hybridization. That is, spin pairing should appear in this complex. So, D2sp3 hybridization. So, D2sp3 hybridization means low spin complex and inner orbital complexes. So, this is magnetic moment is equal to 0. That means diamagnetic property and the inner orbital complex. Even this is a weak field ligand. So next question, this is the geometries of this same like question. So this is the nickel compound. This is platinum compound. So platinum is 5D series. This is 3D series. So this 3D series is to only produce the tetrahedral compound. This 5D series is make a square planar complex. Therefore, this answer is A. This is a tetrahedral structure. This compound having a square planar structure. These all questions from CSIR question paper. So next topic is spin only magnetic moments. So how to calculate spin only magnetic moment? Mu s equal to root of n into n plus 2 Bohr magneto. Mu s is spin only magnetic moment. N is the number of unpaired electrons. So magnetic property is only depends upon the unpaired electron present in the coordination complex. So this is the formula. You should remember this formula. Mu s equal to root of n into n plus 2. So we can calculate different systems. This is the spin only magnetic moments of metal complexes. Here number of unpaired of electrons. Suppose if we have one unpaired of electrons, spin only magnetic moments is 1.73. Two unpaired of electron 2.83. Three unpaired of electron 3.87. So we can calculate from mu s equal to root of n into n plus 2. Here you can see this is suppose they gave only spin magnetic moment value. For example, spin magnetic moment value is equal to 1.73 and 2.83 means you can see 1, 2, 3, 4, 5. Just this is simple tricks. 1, 2, 3, 4, 5, 6. If your value having a 1, this is the number of unpaired of electron is 1. Is 2 and number of unpaired of electron is 2. 3 is number of unpaired of electron 3. 4 number of unpaired and so on. So you should remember these values. This is the questions related with the magnetic spin only magnetic field. So here they asked this is what is the structure and magnetic property. So in this case, this is also D8 system, 3D, 4S and 4P. This is a weak field ligand. So this is weak field ligand, it's make only sp3 hybridization. So sp3 hybridization means this is tetrahedral structure and it's having a 2 unpaired electrons. So 2 unpaired electron means it shows paramagnetic nature. Therefore, this is the answer, tetrahedral and paramagnetic property. So here I am showing different complexes in the tetrahedral structure. This is carbonyl and chloride. So just you should remember those complexes to easy to answer these related questions. This is diamagnetic and paramagnetic. This is diamagnetic. It's mostly zinc complexes are diamagnetic because we already know about zinc complexes. D10 system. D10 system you should don't have any unpaired of electron. Therefore, this zinc complex is mostly is a diamagnetic system. So this is another question. Here they gave magnetic moment of two magnetic moment. One is an octahedral complex of metal ion has a magnetic moment of 5.92 Bohr magneto, and another octahedral complex of the same. This is not sum. This is same metal ion in the same oxidation state has a magnetic moment of 1.75 pm. So this oxidation state is same, but it may be a different nature of ligands. One is strong field ligand, another one is weak field ligand. If strong field ligand is present, it may be a 5. Its mu s value 5.92. Weak field consistent series forms a tetrahedral complex which has a magnetic moment. They gave magnetic moment and structure also, which is diamagnetic. The metal they asked to identify what is the metal ion. So they gave structure, that is square planar structure, and they gave magnetic property and the magnetic moments. So same like questions. So answer is B, the nickel 2 plus complex. So next topic is crystal field theory. This is a very important topic in coordination chemistry. What is the crystal field theory? It's approaching both central metal atom as well as silicons. For example, in valence bond theory, we only considered about hybridizations of s orbital, p orbital, and d orbital. Here we can consider electronic density, electronic loads of ligands as well as metal atoms. This is we already know about shapes of d orbitals. This is the dh square orbital. This is dx square minus y square orbital. Dx square minus y square means this orbital's shape is along the axis, along the x-axis and along the y-axis. This is orbital shape is along the z-axis. So this is dxy, yz and zx. This is in between the axis. This is y-axis and z-axis. So this loops is present in the in between the axis. So we already know about d orbitals having a 5 cells. These 5 cells having a different directional properties. So this is the directional properties. So suppose this ligand is approached along the axis or in between the axis. It depends upon the splitting patterns of these complexes. Here, repulsion between ligand lone pairs and the d orbitals on the metal results in the splitting of the energy of the d orbitals. D orbitals can get split. We already know about degenerate orbital. Degenerate orbital means same energy levels. When is approached ligand to central metal atoms, it may be split into different energy levels. One is lower energy level, another one is higher energy levels. So in different structural complex, it is having a different splitting patterns. This is how to split uh, the free electrons as well as the coordination complex. Suppose when it's having a free metal or free ligands is having a high energy levels. When it's attracted with the metal and ligands to take electrostatic attraction. This electrostatic attraction means one positive charge, one negative charge. So these both attract together to get neutralized. So these energy levels it get down. This is down. But in this case, metal having some ligands, d orbitals having some ligands. So those ligands can repel ligands present in electrons present in the ligand. So electron repulsion between the ligand as well as the metal to get splitting. So it's go to higher energy level. This higher energy levels also split into different energy level. It depends upon the ligands approaching in the directions. So here I am showing the octagonal splitting. In this octagonal splitting, this is the electronic load present in the octagonal complex. This electronic load we already know about. It can split T2G orbital and the EG orbital. This T2G orbital is having a three orbitals. These three orbitals in between the axis. Loops are present in between the axis. These two orbitals, the loops are present in the loops means that these electron clouds. This electron clouds is present in the along the axis. Along the axis means x-axis, y-axis, and the z-axis. So in octagonal structure, these ligands are approaching the along the axis. So along the axis means this is the along the axis. These are the ligands 1, 2, 3, 4, 5, 6 ligands. These 6 ligands are approaching along the axis. So this along the axis means this electron density as well as this electron density can repel to get higher energy level splitting. Therefore, these two orbitals goes higher energy level than that of T2G orbital, because this T2G orbital in octagonal structure having a in between the two ligands. Therefore, this is goes to lower level is compared to EG orbitals. This is the splitting in the octagonal complexes. So, in the octagonal complexes, here we can calculate the splitting energy. This is lowest splitting energy. This is highest. It means lower splitting energy means it's lost some electron, some energy levels. Higher splitting means it's gain some energy levels to get higher energy states. So this is the octagonal field. Octagonal field means T2G and EG. So this is the different structural components having a different splitting patterns. This is a octagonal splitting. This octagonal splitting having a T2G and EG level splitting. This is lower energy level and higher energy level. This is tetrahedral structure. In tetrahedral structure, ligands are present in the approaching in between the axis. So in between the axis means so in between the axis the orbitals are dxy. These three orbitals are present in between the axis. Therefore, these orbitals which goes to higher energy levels and EG orbitals is come to lower energy level. So, in this square planar complexes, this is dx square minus y square is goes very high energy level, because in square planar complexes coordination number is 4. These 4 ligands are approaching in the x-axis and y-axis direction. So x-axis, y-axis directions only is split higher energy level. Therefore, this dx square minus y square is goes to very high energy level, and dz square is come to lower energy levels. So you should know this splitting patterns for octagonal complex, tetrahedral complex, as well as square planar complex. So this is one questions from CFT. They ask the order of increasing energy of different d orbitals in a square planar geometry. This square planar geometry, which one is higher energy level? So which one is lower energy level? You can see this is square planar complex. This is higher energy level orbitals. This is lower energy level orbitals. So right answer is this one. So this is a higher energy orbitals. Next higher energy orbital dxy, and then these orbitals are lower energy orbitals. So another question: which of the following cation is colorless in aqueous solution? So crystal field theory can explain the color of the complexes. Color of the complexes means we already know about various transitions present in these compounds, like DD transition, charge transfer transition, metal to charge transfer, or ligand to charge transfer transition. Mostly coordination complexes having a DD transition. DD transition means electron can transfer lower energy d orbital to higher energy d orbitals. So they are asking which of the following cation is colorless in aqueous solution. Colorless means it's um, uh, so mostly we already know about electronic configurations of first row transition elements. So zinc is a full-filled d orbital, so D10 system. So D10 system is full-filled. So here we cannot get any DD transition. So if we get DD transition, those complexes having a colored. So in this case, A is the answer. So D10 system don't have any DD transition, therefore this compound is a colorless compound. So another same like questions, which of the following cation is colored in aqueous solution? In aqueous solution, this is copper plus, zinc 2 plus, and titanium 4 plus, and nickel 2 plus. In this case, these three orbitals are vacant orbital or full-filled orbitals. So these full-filled or vacant orbitals is don't get any DD transition, it only get this nickel 2 plus. Nickel 2 plus is a D8 system having a unpaired of electrons. So these unpaired of electrons can move lower energy levels to higher energy level. Therefore, these compounds having a DD transition. Therefore, this compound is having colored. So this is a D is a answer for this question. So another one is spectrochemical series. In this spectrochemical series, you should know what which ligands are weak field ligands, which ligands are strong field ligands. So you should remember this order. This is a weak field ligands. These are the strong field ligands. This cyano, whenever you see the cyano or carbonyl compounds, those compounds are very strong field ligand compounds. So when it's present in the weak field ligand, the smaller delta value, that is splitting energy is get smaller than that of strong field, and longer lambda value. Lambda value means wavelength of light. Wavelength of light absorbed in this compound. So we already know about energy is indirectly proportional to lambda. So when you get smaller delta value, so E value is smaller, therefore lambda value is higher. So you should know about smaller value having a longer lambda value. So same like strong field ligand. In this strong field ligand, these are the strong field ligand. So the splitting energy is get more. So larger delta value and shorter wavelength of light observed. So here in this section, we can calculate crystal field stabilization energy. This is very important in the CFT. Crystal field stabilization energy is equal to number of electron. How to calculate? Crystal field stabilization energy is equal to number of electrons present in the higher energy orbital. This is higher energy orbital. This is lower energy. This is the octahedral splitting T2G and EG. This is higher energy orbital. This is lower energy orbital. So number of electrons present in the higher energy orbital into 0.6 delta O. This is the energy level of the higher energy orbital. So 0.6 delta O minus number of electron present in the lower energy level orbital. This is lower energy orbital into 0.4 delta O. This minus sign is not is negligible in this formula. So you can take this is not minus, this is plus charge. So number of electron present in the higher energy orbital into 0.6 and minus number of electron present in the lower energy orbital into 0.4 delta O. So crystal field stabilization energy is equal to for different system. This is one system, this is one system, this is D1 system. So D1 system having the one electron present in the T2G orbital and no electron present in the EG orbital. So therefore we can calculate CFEC, the crystal field stabilization energy is equal to higher energy level, no orbital, about 0 into so 0 into 0.6 minus 1 electron present in the lower energy orbital. So 1 into 0.4 delta O. So this is 0. So minus 0.4 delta O for this system. And same like this system. This is D8 system. In D8 system, it's having a T2G orbital. This is T2G and EG. T2G orbital having a 6 electrons and EG orbital having a 2 electrons. Therefore, crystal field stabilization energy, we can calculate 2 into, this is 2 into 0.6 minus 6 into 0.4. So, we can calculate crystal field stabilization energy is equal to minus 1.2 delta O. So, we can calculate all system D1, D2 and so on, many system. In this case, you should remember for your CSIR examination, because D1, D2, D3, D8, D9 and D10 system, it's not affected strong field and weak field ligand. It's not affected nature of the ligand, because yes, strong field ligand and weak field ligand same electronic configuration. So crystal field stabilization energy is same for strong field ligand compound as well as weak field ligand compound. So it's no difference in the strong field as well as weak field ligand. So you should remember D1, D2, D3, D8, D9, D10, because D1 means this only one electron, D2 means 2 electron, it's only possible to fulfill this type, and D3 is only possible to this, and D8 also, D9 and D10. So this is not affected nature of silicons. But other types, these are the types. This is D4 system and D4 system high spin state and D4 system low spin state. When weak field ligand present in this compound, so this delta O value is lower than that of pairing energy, electron pairing energy. Therefore, this electron is present in the first half filled in the T2G and EG. So one electron, one electron, one electron. This fourth electron is close to EG level. This is the weak field ligand. But suppose it's take a strong field ligand, this is the energy level. Delta O value is higher than that of weak field ligand. Therefore, this electron is present. This electron is get spin pairing. So, first electron, second electron, third electron. This fourth electron is not goes to this level, it is goes to this level. So, crystal field stabilization energy we can calculate for a weak field ligand as well as strong field ligand. These two ligands are different in this system. So same like D5 system. D5 system having a weak field case and strong field case. In weak field case, that is high spin complex. This is high spin means D5 system. D5 system is having 1 half field, and then this is a strong field system. Strong field system. First electron, second electron, third electron. Fourth electron is goes to same orbital and the fifth electron is goes to this orbital. So this only fill T2G levels, is not filled in EG level. So this crystal field stabilization energy is different in strong field in D5 system and weak field in D5 system. So same like D6 system. D6 system also is same like different crystal field stabilization energy in weak field and strong field cases. This is a D7 system. D7 system also same like weak field is different and the strong field is a very different case. So from this CFT, it's having some model questions. So which of the following spectra used to calculate crystal field stabilization energy? So crystal field stabilization energy is only depends upon the energy levels of the orbitals. So energy level of the orbitals is only calculated from the UV visible spectra. It's not calculated from ESR and microwave and the NMR spectra. Therefore, this answer, this question D is the answer for this question. So another one is factors affecting the delta O value is very important for this competitive exam questions, because different factors affecting the delta O value. Delta value O means crystal field stabilization energy. For example, first one is increasing oxidation state of metal, also increasing delta O value. So oxidation state is increased, automatically delta O value is increased. For example, this is two set of complexes. This is cobalt 2 complex. This is cobalt 3 complex. This cobalt 2 complex delta O value is lower than that of cobalt 3 complex. Same like iron 2 complex and iron 3 complex. So when you see higher oxidation state, you can compare lower and higher oxidation state. Higher oxidation state having a higher delta O value than that of lower oxidation state. So you should remember that thing. So another one is row of the transition metal. So row of the transition metal means suppose your complex is having a 3D series or 4D series or 5D series. If d orbitals, size of the d orbital increases, and the delta O value also increases. So if you can compare 3D, 4D, and 5D orbitals. 5D orbital compound having a higher delta O value than that of 3D orbitals. This is the example of this compound. This is so which of the following would having smallest value of delta O, smallest value. So this is the one column of this compound, that is iron, ruthenium and osmium. So you can you see this is the same ligand and different same oxidation state, only different in this central metal atom. So they are asking wood having the smallest value of delta O. So smallest value is iron 3 plus state, because 3D, 4D, 5D, 5D having a higher delta O value. So 3D having a lower delta O value. So this is a right answer. Iron compound is a smallest delta O value. So this is another example for this delta O higher and lower. So next one is nature of the ligand. Delta O value is it depends upon the nature of the ligand. Nature of the ligand means high field ligand or low field, weak field ligand. So here the size of delta O depends on the ligand present according to the spectrochemical series, which is a list of ligands in order of decreasing crystal field strength. So crystal field strength goes decrease. So when having a weak field ligand, delta O value is smaller than that of strong field ligand. So if we get if it's present in the strong field ligand, delta O value also is very higher than that of weak field ligand. So next one is ligands influence the magnitude of delta O. So here Cl minus and the SCN minus. Cl is a weak field ligand, SCN minus is a strong field ligand, and Cyno also is a strong field ligand. So strong field ligand is having a the higher, larger delta O value than that of weak field ligand. Okay, this is another simple question from GATE question. This is magnitude of delta O value will depend upon which delta O value it depends upon the what. So first one, charge of the central metal atom, central metal ion. Yes, it's influence the charge of the central metal atom. Then second one, nature of silicon. Yes, its nature of ligand also affect the delta O value, strong field ligand and weak field ligand, and the principal quantum number of the d electron. Yes, it's also affected 3D series, 4D series, or 5D series. So all the above statements are it's related to the delta O value. This is fourth is the answer for this question. So this is another question. They gave hexacyanoferrous 2 plus ion. This is a diamagnetic complexes, and statements are, what are the statements are true or false. They are asking which statement is true and which statement is false for this complex. This complex, octahedral complex, So you should know structure of this complex and oxidation state of this complex and electronic configuration of this complex and the nature of this ligand. This is the nature of the ligand is strong field ligand, and this is oxidation state is iron 2 plus, and then we can calculate this is outer orbital complex or inner orbital complex like that. So they told it is an outer statement, it is an outer orbital complex. I think this is a strong field ligand. So strong field ligands is only producing inner orbital complex. So first statement is false. So second statement. Second statement, its hybridization is sp3d2 hybridization. So when it's get outer orbital complex, that times only we can get sp3d2 hybridization. So second, but our complex is a inner orbital complex d2 sp3 hybridization. So second statement also is false. So third one, it is a spin pad complex. Yes, it is a spin pad. Spin pad means all electrons get paired because this is strong field ligand. So this strong field ligand is it's get paired the electrons. This is D6 system. So D6 system get paired. It is high spin complex. Spin pad means it's not high spin. So it is a not high spin complex. This is a low spin complex. So fourth statement also false. It's obey Hund's rules. I think it's not obey Hund's rule. And its geometry is planar hexagonal. It's not planar hexagonal. This is the octahedral structure. So answer is only true statement is C. It is a spin pad complex. This is only right statement. These all statements are false in this complex. So another example. So octahedral field splitting energy delta O is always higher than tetrahedral field splitting. So when you get we can compare octahedral splitting energy and tetrahedral splitting energy. Tetrahedral splitting energy is always lower than that of octahedral splitting energy because in octahedral structure having a 6 electrons. So these 6 electrons is get more splitting than that of 4 electrons. So this is a statement. In octahedral complexes there are 6 ligands, whereas tetrahedral complexes there are only 4 ligands. Hence decrease in the number of ligands. So automatically decrease the crystal field splitting. So next important topic is John-Teller distortion. John-Teller distortion is very important in the gate questions. Here, in a non-linear, when it's get distortions in the octahedral structure, those compounds having a non-linear molecule, and if have a degenerate orbitals are asymmetrically occupied. Asymmetrically, symmetry we already know about what is means symmetry and what it means asymmetry. So those molecules having a asymmetric occupied. So yeah, distortion will occur to remove the degeneracy. So those type this degeneracy orbitals can split further split into different energy levels. So what is means John-Teller distortion in an electronically degenerate state. A non-linear molecule undergoes distortion to remove the degeneracy by lowering the symmetry, thus by lowering the energy. So lowering the symmetry and also is lowering the energy. This is the degenerate state. Degeneracy means these 3 electrons. This is D2G orbital. D2G orbital. These 3 orbitals are same energy level. Therefore, we are called this is a degeneracy state. So if D1 system, this D1 system having a only 1 electron, this 1 electron can go XY orbital or XZ orbital or YZ orbital. So different structure, this structure or this or this. Suppose this is a degeneracy, asymmetric degenerative state. Asymmetric means it's not same. Same electronic energy level. It's a different energy electronic energy level. orbitals. So this is a D3 system. In D3 system, yeah, each orbital having a one electron. This one electron, this one electron, this one electron. This is a symmetry occupied orbitals. So these symmetric occupied orbitals don't get any John-Teller distortion. So John-Teller distortion is only appeared in the asymmetric occupied d orbitals. So D1 system can get John-Teller distortion. This D3 system is not don't it's not get any John-Teller distortion. So here I am showing some configurations with the significant of distortion, John-Teller distortions. This is a D4 high spin state. This is D4 high spin state. Low spin state means it may be this electron is come down this electron, this state. So this is T2G and EG. This EG is having a asymmetric. This is symmetric occupied. This is asymmetric occupied. So this is asymmetric occupied orbital. So therefore, this system should have higher John-Teller distortion. So significant, very strong John-Teller distortion. As well as here D7 system, D7 low spin complex, low spin. So low spin means it may be weak field electron. It's present in the weak, low spin means it may be a strong field electron. So D7 low spin system. Here, this one electron, this is asymmetrically occupied d orbitals. So, asymmetrically occupied d orbitals can get John-Teller distortion. Same like D9 system. This D9 system is copper 2 plus, D7 is copper cobalt 2 plus. This is chromium and manganese 3 plus. Chromium 2 plus and manganese 3 plus. So, you should know. You should remember these systems. So it's showing high John-Teller distortion than that of other systems. So these are the weak John-Teller distortion. Weak John-Teller when asymmetrically occupied orbitals is present in the EG system. Those systems having a high, high or strong John-Teller distortion. But when is asymmetrically occupied orbitals present in the T2G system, it may be a weak John-Teller distortion. So these are the systems having a weak John-Teller distortion than that of other system. In this case, this is symmetrically occupied. EG set having a symmetrically occupied. This is also symmetrically occupied. Therefore, this system is having a very weak John-Teller distortion. So here I am showing a different types of John-Teller distortion. One is Z out distortion, another one is Z in distortion. This is the normal octahedron. So normal octahedron, it's this bond energy, bond length are same, 6 bond length are same. But in distorted octahedral structure having a different bond length. These 4 are the same, but these 2 are the different. This is elongated form, this is compressed form. This elongated form is Z out distortion, this is Z in distortion. In Z out distortion, dx square minus y square orbitals having a very high energy level. It's splitting very high level than that of dz square orbital. So this one electron is present, one unpaired of electron is present in the dx square minus y square orbital. Suppose one electron, this unpaired of electron is present in the z square orbital, means it may be it goes to this level is higher energy level. So it's compressed. This is the elongated form. So you should know the splitting energy of elongator, that is Z out distortion and Z in distortion. Why we called this is Z means this is a Z direction. So Z direction is having a elongated form. This is a Z direction having a compressed form. So Z in distortion. So some questions. Which metal complex ion is expected to be subject to a John-Teller distortion? So we can consider this is a D9 system, this is D8 system, so this is D0 system, this is it may be a D4 system. So In this case, D9 system having a higher John-Teller distortion than that of other system. Therefore, answer is A. Copper 2 plus is having a higher John-Teller distortion than that of other complexes. So, this is another example. Strong John-Teller distortion is not observed. That is, they told is not observed. It's not observed for octahedral complexes. Which complexes having don't have John-Teller distortion. So, this is a B. B is a low spin chromium 2 plus. So, low spin D4 system. So D4 system low spins means is so all electrons get paired electrons. So these paired electrons and symmetrically occupied orbitals. So this system having a symmetrically occupied orbitals. So therefore, in this system don't have any John-Teller distortions. But other systems having a John-Teller distortions. So this questions is related to some magnetic property. So okay, this is related to John-Teller distortion. Why does the absorption spectra it's get exhibited a broad band with a solder? So when it's compounds having a John-Teller distortion, those we can get different UV visible spectral pattern. For example, in this system, this is I think this is a nickel hexago nickel 2 plus complex. In this system, having a due to John-Teller distortion in the excited state. This is not present in the ground state, excited state. So normal octahedral structure, we can get only this uniform Gaussian curve. But when this compound having a John-Teller distortion, we can get with a shoulder peak. So from this UV visible spectra, we can understand this compound having a John-Teller distortion or not. So this compound having a John-Teller distortion due to distortion in the excited state. So next topic is Ligand field theory. This Ligand field theory is also one of the important theory in the coordination chemistry. In crystal field theory, we can only explain in VPT theory is only explain hybridization of the orbitals. In crystal field theory is only explain the central metal splitting patterns of the central metal atoms. But in Ligand field theory, we can consider central metal atom electronic configurations of central metal atom as well as ligand. So we can get molecular orbital splitting. So in this case, we can get different bonding. Sigma bonding means this is a d square orbital in central metal atom. This is a z direction approaching the ligands. So head to head approach. This head to head overlap. We can get sigma bonding. So this is also sigma bonding. This is the dx square minus y square orbitals approaching a ligand in the same direction. So get a sigma bonding. So we can get different energy levels approaching the ligand as well as metal. This is the s orbital. This is the s orbitals from metal. This is s orbitals from ligands. So s orbitals overlap to get sigma bonding. Those sigma bonding we can identify. This is the A1G system. G is a geride, U is a ungeride. Geride and ungeride. This is ungeride. Ungeride T1U. This is a p orbitals present in the central metal atom. This is a sigma s orbital present in the ligands. So s and p overlapping to get T1U energy levels. Same like EG energy level and T2G energy level. EG energy level we know already studied in crystal field theory. So this is in EG energy levels, and this is the T2G energy levels. So in Ligand field theory, so this is this is EG system, this is T2G system. So ligand field splitting, we can consider this is bonding orbitals, ligand orbitals. This is central metal orbitals. This is the molecular orbitals. Molecular orbitals means this is the complex. So energy levels is different from metal orbital and ligand orbital. So we can consider this is a bonding orbital. So all ligands are fulfilled orbitals. So these fulfilled orbitals having a bonding orbitals, and this is a non-bonding orbital. So only in this T2G system is a non-bonding orbital, and these are the anti-bonding orbital, EG and A1G and T1U. So this system is most related to CFT, crystal field splitting. So crystal field splitting, we can study only T2G and EG. We are not studied these bonding orbitals and anti-bonding orbitals. So here I am showing some questions related to valence bond theory. These are the simple questions. So just I'm showing questions and answers, because I don't have much time to discuss about this all. So they, in this case, they are asking hybridization, which hybridization involved in this complex. So hexago cobalt 2 plus, it's having a D2sp3 hybridization. So valence bond theory, in this case, they are asking which statement is right for this compound. The complex is octahedral or like that. So so B is the right answer. B is the right answer means this complex is related to, the complex is octahedral structure because 6 coordination number, so octahedral structure, and then the complex is an outer orbital complex. Outer orbital complex means it can coordinate, its ligand is coordinated with 3D orbitals. It's not coordinated with, it's coordinated with 4D orbitals. It's not coordinated with 3D orbitals. Therefore, this is outer orbital complex, and then this is coordination number is 6. This is answer for this question, and which has maximum paramagnetic character. So, which compounds having a large number of unpaired of electrons, those compounds having a maximum paramagnetic character. So you can see this is first system is D5 system, this is D1 system, this is D1, and this is D5. So in D5 system, this is also D5, this is also D5. This is a D6 system, this is a D5 system. So D5 system having a, this is weak field ligand. So D5 system having a higher spin pattern, higher number of unpaired electrons. Therefore, this is a maximum paramagnetic property than that of other complexes. So, which statement is false and false? So, in octahedral crystal field splitting, the electron occupy each set of orbital before the. So, this is A is false. In crystal field energy, when the valence d orbitals of the central metal ion are split in energy in octahedral field, which orbitals are raised least in energy? So they are asked least in energy in the octahedral structure. So least energy T2G orbital. So T2G orbitals means dxy, yz, and dzx. These are the T2G orbitals. This is the right answer. So another question: how many unpaired electrons are there in a strong field iron 2 plus octahedral complex? Iron 2 plus means D6 system. So D6 system strong field ligand. Strong field ligands means it get paired electrons. So D6 systems is it don't have any paired unpaired electrons. Therefore, A is the right answer. So unpaired electron, no unpaired electron will be D6 system in iron 2 plus with the strong field ligands. This is another question related with the crystal field theory. So which statement is right in this complex? It is diamagnetic, it is a low spin complex. The complex ion is D5 system, ligands are weak field ligand, it is octagonal. So this is B is the right answer. So this is another question related with the color of the complexes. This color of the complexes is directly related with the DD transition. So which compounds having a DD transition? Uh, so yellow, right? This is complementary color. Complementary color means suppose complexes absorb yellow light, this opposite light can visible. So this is yellow. The compound absorbed yellow light means we can see the violet color of this compound. So this is another question from CFT. Strong field become like cyano. So usually C is usually produce low spin. Yes, strong field ligand means it's only produce low spin complexes because the electrons get spin paired. So usually produce low spin complex and high crystal field splitting. So these are the references for this coordination chemistry topic. So maybe I will send this PPT to organizer. You can get some this PPT from there. So thank you very much to everyone. If you have any questions, you can ask me. Any questions from audience?
Thank you, sir.
Yeah,
Krishna Kumar.
You can ask, no problem. You can ask a question, sir.
Okay. Can I ask a question, sir?
Yeah. Sure, you can ask. Okay.
Okay, sir. So please explain the isomerism of facial and meridional. Sir.
So facial isomerism.
And how many isomers are there?
So facial isomerism, same like donor atoms present in the corner, the trigonal corner of this complexes, the trigonal structure. When it's get a trigonal structure, so we can identify that is a facial isomerism. Meritonial isomerism don't show any trigonal corner of the same ligand present in this complex. So this is the identification of facial and meritonial systems. So different types of isomerism present in the octahedral structure. One is facial, another one is meritonial. As well as cis, we can also call the cis isomer and the trans isomer. Cis isomer means the same ligand is present in the same directions. Those compounds we are called the cis compound. Suppose it's present in the opposite direction, those compounds we are called the trans compounds. Are you clear? Are you clear?
Yes, sir. So I want with the examples for that meridional isomerism and facial isomerism.
So I don't have any examples in this slides. Okay, this is one example in the phase isomer and this is meritonial isomer. Can you see my slide? Can you see my slide? This is facial.
Okay,
This
sir.
is this is
I got it,
corner
sir.
of the trigonal. Corner of the trigonal. This is not corner of the trigonal. This is nitrogen, nitrogen, nitrogen. This is trigonal. This donor atom present in the trigonal structure, but this is not the trigonal position. Therefore, this is facial isomer. This is metonyl isomer. Got it?
Yes, sir. I got it, sir.
Okay. Thanks. Any other questions?
Excuse me,
Yeah, please.
sir, about reflexotic value, sir. How the
Uh,
reflexivity value changes according to the ligand, sir?
okay. Here I don't put any electrostatic values in these systems. Okay. So that is another topic in the coordination chemistry. Okay. Maybe I will explain next time present in total inorganic compounds. So I don't have any slides about electrostatic effect.
Okay, thank you, sir.
Good morning, sir.
Yeah. Good morning.
Sir, my question is about octahedral complex,
Okay.
strong field and weak field, but we are
Okay.
feeling that splitting energy, strong field is high and weak field is low. But
Yes.
electron pairing energy is both have a same energy, 10 dq. How it is?
It's not the same energy. Okay. This is I'll take some examples. So splitting energy is higher in the strong field than that of weak field. So pairing energy is lesser in the strong field than that of weak field. So maybe I don't have enough splitting here. So maybe we can explain from this slide. So this is T2G and EG set. Suppose if strong field ligand present in the octahedral structure, this energy level is higher than that of weak field. So we can fill electron first here one. Suppose if we have D5 system, if we take a D5 system, first electron, second electron, third electron. This strong field ligand is having spin pairing energy. So spin pairing energy, this fourth ligand is goes to this dxy orbital, and fifth electron is goes to dxz orbital. So here two electron, here two electron, here one electron. So this one electron is having a one unpaired of electron. This one unpaired of electron we are called to low spin complex. So suppose in this system having a weak field electron, this energy level is less. So electron can fill D5 system, first electron, second electron, third electron, and fourth electron is goes to higher energy level, and fifth electron is goes to another higher energy level. So 1, 2, 3, 4, 5. So 5 electrons, 3 electrons present in the T2G level and 2 electrons present in the EG level. So totally 5 unpaired of electrons. So totally 5 unpaired of electrons having a high spin complex. So this is the difference between how to fill low spin and how to fill high spin complex in octahedral structure. Do you understand me?
Yes, sir, understand. Thank you, sir.
Okay, thank you.
Thank you very much, sir, for your informative lecture.
Yeah, thank you so much.
Thank you very much, sir. And now we are moving towards our lunch break.
Yeah,
And
okay.
sir, and then we will resume our webinar at 2 o'clock, sir.
Okay, okay, so thank you so much.
So thank you very much, sir. This really this coordination chemistry was really very good,
Yeah,
and we
thank
have understood most of our students. They appreciated this
okay.
effort, and okay, so we are moving towards our lunch, sir.
Okay.
And I request all the participants and all the guest speakers to resume at 2 o'clock, because this webinar will resume at 2 o'clock, sir.
Okay.
Okay, sir. Thank you very much, sir. And
Thank you.
we hope in future, if we conduct new this continuation of this webinar, sir,
Yeah, yeah,
we
yeah,
hope
sure.
that
Sure,
you will
sure.
present one more informative session like this, sir.
Yeah, sure. That is my
Thank,
pleasure.
thank you, sir. Thank you very much, sir.
Thank you so much.
Okay, so we are moving towards our lunch, and we will resume this webinar at 2 o'clock. All the participants kindly resume, join the link by 2 o'clock. Thank you.
என்ன கிளாஸ் உடு யாரோ இருக்காங்க எல்லாமே கிட்டி நான் நீ போ 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 போடியா முடியா இந்த டிஎஸ் பொம்மை வந்தா அடிக்கும் நான் ஏன் பொம்மை கொண்டே போங்க ஆசி அவரை விட்டாங்களா நீ ஆமா போங்க எனக்கு அந்த கழிச்சு சாப்பிடலாம் நீ போ நீச்சு போ இந்தி இல்ல மோட்டர் போட்டிருந்தா பாரு மோட்டர் போட்டிருக்க பாத்துட்டோம் போடலையா போடு ஓடுது பாரு ஓடுது இல்லையே அவங்க கழுவி விடுதாங்களா இருக்கும் யார் இல்ல தண்ணி மோட்டர் போட்டிருக்காங்க அவங்க கழுவி விடுதாங்க இங்கதான் அங்க சத்தம் கேட்கல இங்க சத்தங்க ஹலோ எங்க இருக்கீங்க எங்க இருக்கீங்க போனீங்களா இவர் பாக்கலையம்மா பேசிட்டா சரி இல்லட்ட அது அவ்வளவுதான் பிடிக்கும் அப்புறம் அழுக்கு போவாது ஒவ்வொரு ட்ரெஸ்லயும் அழுக்கு படிஞ்சிடும் அடுத்தலதான் போடணும் அம்மா அம்மா யார்கிட்ட தர வேண்டிய தர சொன்ன அப்பா வச்சுட்டாங்க என்ன செய்யணும் என்ன சொல்லணும் சொல்லு என்ன செய்யணும் நான் ஃப்ரூட்ஸ் வாங்க கேட்டேன் சரி வாங்கிட்டு சொல்லுவேன் அப்பா இப்பவே வந்துட்டாங்க ஹலோ அப்பா எங்க இருக்கீங்க வரும்போது ஃப்ரூட்ஸ் வாங்கிட்டு வாங்க ஃப்ரூட்ஸ் வேற ஃப்ரூட் வாங்கிட்டு வாங்க ஃப்ரூட்னா நிறைய ஃப்ரூட் வாங்கிட்டு வாங்க நான் அப்பாட்ட சொல்லிட்டேன் மோட்டர் வரைஞ்ச பார்த்துட்டோம். மோட்டர் வரைஞ்ச பாரு, மேல இருந்து பாரு, மேல பாரு. இங்க தெரியாது. மேல போவும். வரைஞ்சிட்டா மேல சொல்லி மேலையா? அப்ப ஆஃப் பண்ணு. அப்ப ஆஃப் பண்ணு. தண்ணி மோட்டர எங்கம்மா தண்ணி வருது? தண்ணி எங்க போகுது? இங்க ஆஃப் பண்ணிட்டியா?
దోస్తికనని లూసి మెంటల్ చెవుట్లారేதான்.
நீ குளிச்சியம்மா இன்னைக்கு காலைல? என்னம்மா பண்ணுது நீ? என்ன வேலை பண்ணிட்டு இருக்க நீ? நீ போமா, அவன்கிட்டே போவாத. நீ போ, சனியன் கிட்ட போவாத. சனியதான் பிடிக்கும். சனியதான் பிடிக்கும் அவன்கிட்ட போவேன். இந்த இது உன் ட்ரெஸ்ல எடுத்து அங்கிட்டு வைந்தா அப்படி. இந்த ட்ரெஸ்ல எடுத்து மடிச்சு வைந்தா. இந்த இது வேணா எடுத்து சாப்பிடு. சரண், இந்த முட்டையை சாப்பிடலையாம்மா? மஞ்சள் சாப்பிடலையா? வேண்டாமா? எடுத்து அதில் எடுத்து கூட அங்கொண்டு எடுத்துருங்க. வேண்டாமா? எனக்கு தோசைக்கு என்ன கண்மாசம். கரெக்டா எடுத்துருவோம். சாப்பிடுவோம். அந்த முட்டை அந்த மஞ்சள் சாப்பிடு. தோசை பாபி ஆமா, மஞ்சள் சாப்பிடு. என்ன தேச்சியா? ஆமா.
நீ சாப்பிட வேண்டியதானமா எந்த ஊருக்கு போயிருக்கா
இந்த லோக்கல் தான்
ஆசிரியர்
நேத்து தேங்காய் பால் இருந்துச்சுல, அதை எடுத்து வச்சேன். குளுக்கோஸ் இது வச்சேன். கொட்டிட்டா அதுதான். அது தண்ணி தூர ஊத்திட்டு எடுத்து வைக்கணும். அப்புறமா எடுத்து
தேங்காய் பால் ஐஸ்கிரீமா? அதுல வந்து ஒரு குச்சி வைக்கணுமாமா?
குச்சி வச்சிருக்கல, வச்சிருக்கோம் பாருங்க. குச்சி வச்சு தேங்காய் பால் அது வச்சு ஃப்ரீஸ் ஆயிட்டா பாருங்க. என்னடா 2 கப்ல ஊத்தி
லைட்டா மாவு மாதிரி தெரிஞ்சுச்சு. அப்புறம் தேங்காய் பால்
கொஞ்சம் கொஞ்சமா தான் அது ஆகுதா இருக்கும். ஃபுல் ஆகட்டும். ஆமா, அப்படி தூக்கிடலாம்ல.
அது வந்து அப்படியே அது அப்போ அது வந்து அப்படியே வச்சிட்டு ஃப்ரீசருக்குள்ள கையை வச்சுட்டு அப்படியே கொஞ்சம் கைக்குள்ளே வச்சுட்டு அப்படியே வந்து நைட் வரைக்கும் நின்னுட்டு ஃப்ரீஸ் ஆயிடுனா அப்படியே ஸ்ட்ரைட்டா வந்துரும்.
அது நீ ஃப்ரீஸ் ஆயிடும். குளிர அதுனா அப்படி இருக்கும். அப்படி வச்சா நாளைக்கு தான் ஃப்ரீஸா இருக்கும்.
இன்னைக்கே வச்சேன்.
நேத்து வச்சேன், ஆகல.
நேத்து வச்சா ஃபுல் ஆயிருக்கும். பிஸ்கெட் வந்து அவன் தான் ஃபுல்லா சாப்பிட்டே இருக்கான். கிரீம் பிஸ்கெட் கூட அவன் தான், எல்லாம் அவன் தான் சாப்பிட்டான். எங்களுக்கு தெரியாம எப்பவுமே சாப்பிட்டு இருக்கான் போல. எனக்கும் கூட குடுக்கல, தோசைக்கும் குடுக்கல. அடுத்து லாஸ்ட் ஒரு டைகர் ஒரு பிஸ்கெட் இருக்குல்ல, நான் அப்ப எடுத்துட்டு வந்தேன், அதுவும் எனக்கு தான் சொல்லுவேன். நான் எங்களுக்கு குடுக்கவே மாட்டேங்கான். ஏன்னு சொல்லிட்டு இருக்கேன்.
முடியட்டுமா? எனக்கு முடியட்டுமாம்மா. 5 மணிக்கு தான் முடியும். 5 மணிக்கு தான் முடியும்.
நீ வந்து நான் இப்படி கால் தடவை தூக்கி கொடுக்குறா. இது வந்து தூக்கி கொடு.
ஆமாங்க, லைட் ஆஃப் பண்ணுங்க. லைட்டு ஃபேன் ஆஃப் பண்ணிடு ரவி. சாப்பிட்டியா? சாப்பிட்டியா? அப்புறம் சாப்பிடுங்க. நம்ம நிமிஷம் பார்த்தேன். சரி.
நெஞ்சுக்குள்ள கூடி இருக்கும் நம்ம வெறித்தனம், நம்ம இப்போ எக்கலனா, நம்ம நெஞ்சுக்குள்ள கூடி இருக்கும் வெறித்தனம், நம்ம இப்போ எக்கலனா. நான் முதல்ல என்ன பண்ண போறேன்னா பெட்ரூம் உருவாக்குறேன். பெட்ரூம்
முதல்ல அதுல இருங்கெல்லாம் எடுத்து கவர்ல வச்சிட்டியா?
screen na share பண்ணிருக்காரு. Okay.
Hello.
Good afternoon to all.
Good afternoon. Yes, madam. Please proceed.
Dr. Rajkumar, shall we start?
Yes, madam. Yes, please start.
Okay. So I welcome you all for the afternoon session. Now I request Dr. Rajkumar to hand over the session and do his presentation. So all the participants are requested to make use of his exposure. Thank you.
Good afternoon to one and all. Advance thanks for giving this opportunity to discuss the CSIR-NET coaching. For this section, I am going to discuss about the nuclear chemistry regarding the isotopes, isotones. That's a basic nuclear chemistry and the nuclear reaction and nuclear fusion and fission reaction and their related things. So how the questions are going to be a collective one, how to answer that one with the proper explanation. Everything is based on the simple structural representation which is presented here. So you must know about the nuclear, what do you mean by nucleus, what do you mean by neutrons and protons and subatomic particles, and how they are going to interact with your one each and every questions. What kind of variation is happen in the things. That's a thing we are going to discuss. Before going to that, in a single slide, that agency which is conducting the test for the CSIR-NET, National Testing Agency. So the agency is not only conducting the CSIR, in future it is going to conduct the most of the central university, central level examination. So once you prepare for your CSIR at present, you may have a possibility to complete your, at least complete your chemistry part when you are in a MS level or BS level. Okay. So when you are going for competitive exams like IIT, GATE and CU-SET, Central University Examination Set exams, whatever the things, in future everything is going to comes under the National Testing Agency. So that's the part of A, B, C with respective marks. You are having a negative marks, you must to alert about your present correct answer as well as the which one is a wrong answer. You must to choose it properly to enter such like a gate. Okay. So everything will comes under these two sections. Once you are having two things, that is a nuclear fission and fusion. At present, our team Ganesh Raja and Chandrasekhar, both of you give some other knowledge regarding the CSIR. It will lead to give some other effective result at the time of your competitive exam with the support of your institution. Okay. So like that, the fission is happening. So when we are giving some other additional things together, which leads to give some other new product, that will be a fission product, fusion product. When we come to the fission, in future you must to be very alert at the time of competitive exam. Whatever the competitive exam going to faced by you, at the end of your result, it must be a very fruitful. Okay. So be ready for the fusion reactions. At the time you may face exam as well as your theory and future entrance exams or competitive exams. So don't bother about your dates. It may be comes like a fission reaction. So the two process is the basic things which is happen in your nuclear chemistry. So when we come to the syllabus of CSIR-NET, we are having a one-line representation of your syllabus. It is a nuclear reaction and fission, fusion and radio analytical technique and activation analysis. So when we coming to this category, most of the questions will separated with these major topics. So basic things of your nuclear chemistry and how the nuclear reactions will happen, fusion and fission reactions, radioactive and their kinetics, and carbon dating, stability of nucleus, counters, and their applications. And counters means it will comes under the detection reactor part. Okay. So the best reference book which I am refer to you is Arniker, H.J. Arniker. And if you are having a possibilities, go for second and third books. Okay, we will start from little bit basic, even though you know. So the nuclear chemistry having a possibility to learn the content, whatever the content you are having right now with you, you may have a possibility to know more detail from their nucleus and their proton, neutron, and the electrons, and how far the electrons are arranged in your concerned atoms. Okay. So by that way, we can able to predict whether it will comes under the isotope or isotones or isobars. So the basic of nuclear chemistry, which is played by these three major topics. So if you are having a same, even though you are having a same element, there may be the possibility for changing in their values, especially the A values. So the A may be 12, 13, 14 in the isotopes. When we come to the next isotones, so the values of isotones is a one set of nuclei with the same number and consequently different things. And when we come to the isobars, it is having a one set of nuclei with the same A value, but having a different number of N and Z value. So everything is adapted with respective neutron, proton, and electron. So once you are going to touch this atom, you must to know about the concerned things, proton, neutron, and electron, and their representations. How far their charges and how far their symbols and how the mass will be arranged, and it will be how far the electron is removing or proton is removing or neutron is removing. So when we come to the nuclear chemistry with this knowledge, we are aware about that one is decay. Okay. So we have to know about the decay process which with respective atoms. Okay. So during the time of nuclear reactions, sometime it may be leads to spontaneous one, sometime it will be insisted one by some other external elements. Okay. So however, so the types of radiation comes under the three major parts. So one is alpha radiation, and another one is beta, and third one is gamma with possible particles. So the symbols usually is denoted by alpha, gamma, and beta. So alpha is represented by He2, 4, and beta, which is represented by electron -1, 0, and beta, which is a representation, both are comes under the 0. So the charge also comes under 0 for gamma. Beta tells about the plus or minus. So possibilities are there in beta radiations. So gamma, in that gamma, it will represent the +2. So like that, the charges and the mass and the sources are the things which is utilized in our nuclear chemistry. So among this, the penetrating power which is varied in these types of gamma radiation, overall radiations. Especially the gamma gives a very high penetrating power than the alpha and beta. So it also a little bit health-wise it is a dangerous one. So we must to utilize it very most necessary one. If you want to do that one, then we will go for the gamma radiation. So that's a representation for the limitation for your alpha, beta, gamma. If you are having some other paper to stop that rays, then paper is sufficient to stop the gamma, alpha, and aluminum is required to stop the beta and gamma, which is transmitted through the aluminum also. So it requires some other walls, concrete walls. Hello? Hello? Please mute the voice. Okay, so we are having the three possibilities. Either is the alpha, beta, and gamma. So alpha, we are having these examples which is representing alpha and beta and gamma. So beta having the possibility for positive decay as well as the negative decay. So when we are coming to this overall structure of this one, it shows the representation for your alpha decay, beta decay, and gamma decay by using this various response. At the time, how it will be changed in their mass number or atomic number. It will be denoted as per this case. Addition to that, alpha, beta, gamma, positron emission is there or electron capture is there. So once the reaction leads to give some other plus. So the responsible type is comes under the positron. If that reaction or the content absorb the electrons from the atmosphere or outside, so it will lead to give the result of electron capture. Okay. So the four basic fundamentals are there, forces. So these are the things: strong nuclear force, weak nuclear force, and electromagnetism and gravity. So each and everything is combined with one another based on our content. Whatever the content we are utilizing in our life, it will be based on such a case. So the nuclear force, which is a strongest interaction or weakest interaction, which is truly based on the neutrons and protons, okay, and their responsible forces. So based on that content only, we are telling that is the strongest material. This one is the weakest material. Okay, so that's what the paper is not sorry. So aluminum is not penetrated by the alpha particles. Okay, so it is already stopped by the paper material. So materials which is taken to stop such a kind of rays, alpha, beta, gamma, whatever it is, that are based on their force. And the important point in that one is nuclear potential well. So the nuclear potential well tells about the neutron and proton and their distance, how far it is interacted with the one another when it comes towards the one region nearby. Okay. So the potential energy of a nucleon as a during their approach, how far it is playing a role in such a material. That's a thing which is discussed in the nuclear potential well. Whether it is a neutron, when we are coming the neutron towards the center point, whether it is comfort or not. If you are bringing the proton towards that one center point, how far it is deviated or attracted. Everything is discussed in the nuclear potential well as per this diagrammatic representation. So it has some other peak during the time of interactions towards the center point. So there's the thing which is responsible for your concerned rays, decays, alpha or beta or gamma, whatever the decays. Why we are getting such a material as a stable one? Why we are getting that element as a unstable one? Okay. So everything will comes under this graphical representation of your concerned neutron and the proton. Okay. If you are having a one such a material, it is having some other content, which is a Fe56 or AG107 or tungsten or bismuth, whatever it is. If you are having such a material with respective isotope, it must to be comes under these dotted lines. Okay. So if it is comes under this one, it will it is having some stability nature. Okay. So based on this concerned values, we can able to say that kind of material is comes under the stable one or unstable one for your various decays. So the value of n by z is an important one to predict such a nuclei. So the binding energy and the decay process tells about the calculations of your concerned nuclei. So if you are having, if you want to identify the binding energy, how far it is going to bind with one and another at certain reactions, it tells about the final thing of your binding energy calculation. For that, binding energy divided by nucleon, then you can be able to get it the value. Okay. So per nucleon, or if you want to get a per nucleon, you must to multiply with respective 931.5 megawatt. Okay. So by using that way, we can able to get the stability of your concerned nucleus and the mass defect. The mass defect and the binding energy tells about the nature of your nuclei. So when we come to the graphical arrangement between your mass number with respective binding energy, it tells about the overall in this graphical representation. It started from the hydrogen to up to uranium. We can able to see the overall thing. Among that, it tells about the first part of your up to iron Fe56. It leads to give the fusion process. So it will be ready to combine with one another to give some other result. And when we go for the higher mass numbers, like the 235 and 236, 238 of uranium, it leads to give a immediate result under the fission process. So that's what we are wondering in the uranium reactions. So the reason for the lowest elements and the reason for the highest elements is split out by the two process, fission and the fusion. And the Fe comes under the region which is in a stable nucleoside. So before and after, we can able to split it this overall criteria under the two extreme level reactions. We can able to visibly see that fission and fusion is possible under these two. So the content, we are identified that stability factor. So the stability factor is identified with respect to 270 stable nuclei and 1700 radio nuclei. So every least, how far the least counting having a fission, how far the highest mass numbers having comes under the fission, everything is detailed in the nuclear chemistry. Okay. So based on their isotope activity and the ratios. So we are in the stage to discuss the nuclear fission and the fusion difference. Once we are having a neutron, it leads to interacted with the uranium 235. After that, it started its work to spread over the overall products and byproducts. Whether it is a major or minor, it's not at all a deal. The representation of your neutrons is a biggest play in the nuclear fission process. We can't, even though in this picture, the neutrons, 3 neutrons are in the smaller manner, but the smaller balls of green color tells about the extreme level of the reactions. Okay. As like this initial process, again this neutron is going to bombard with this uranium or this one and then it will started some other miracles like this process. So that's what the fission is a very much attractive one. It is a consistently, it will used to give a different kind of products and the energy. And the fusion reaction. When we come to the fusion, we are combining these two things, whether it may be deuterium and tritium, leads to give some other product. After that, it may leads to give some other response. It may leads to give a neutron or helium, okay, based on the conditions of your reactions. So that's an example for your alpha, beta, gamma. So the radiation which is having a possibility for non-ionizing and ionizing. Once it is interact, it is used to give a ion in their result, it will comes under the ionizing part. If it is not giving any other ions in such a case, it comes under the non-ionizing parameter. So when we come to the ionizing parameter, we are having two possibilities. One is directly ionizing and another one is indirectly ionizing with respective charges, electron, proton, alpha, or alpha, gamma, X-ray or gamma, neutron, whatever it is. So whether you are having ionizing one or non-ionizing one, that's it. So the another part of your classification based on the ionizing photon radiation, whether it may comes under the X-ray based or gamma based or annihilation or Bremsstrahm equation, which is the representation of your R. So the interesting thing is Bremsstrahm radiation. If you are having some other incident electrons, which is going towards your nuclei, the overall direction is changed. That's a thing which is discussed in the Bremsstrahm radiation, whether it may be elastic or inelastic. So to break such a radiation, we can able to learn such a electron nucleus Coulomb interactions. So in that one, we discussed these things. When we come to the additional of new thing is annihilation. When we come to the result of annihilation, the positron electron process and their temperatures is all comes under the discussion. So the basic representation of your material, what are the elements? It may be the example for cobalt 60 or radium 226. So the A representing the atomic mass and Z representing the atomic numbers. So the atomic number and atomic mass going to be under the discussion. So the next part of your nuclear reaction is projectile. So once we are having a projectile, so here the term, here the B is called it as a projectile. Okay. So already A is there and B is going to kick the A, which leads to give some other major product B and some small b. Okay. So our team is going to bombard you with respective knowledge, that is a CSIR. Okay. So we hope we are going to give some other things to enrich you from A category to B category. That means one stage to another stage. Okay. So you are going to change after this seminar with some other concern knowledge. Okay. So the role of A is to change the content of your reactant towards the some other product B. So the term A is a projectile. Projectile must to bombard your concerned nuclei, whether it may be a cobalt or radium, whatever it is, then it must to change their name into some other else. So with respective products, that is a B. So the changes will happen from one reactant to another, one content to another content with respective projectile Finally, it will give some other byproducts B. So by using that way, the projectile is playing. So it may be alpha or beta, whatever it is, alpha or neutron, whatever it is. So the physical quantity in that reactions is a main role to discuss, such like a charges, mass number, linear momentum, and mass energy. So once we must know about such a things. That's a basic content of your nuclear chemistry. Addition to that, so what are the advanced level which you must to get for your additional information in your nuclear chemistry? So the nuclear transformation and projectile and nuclear reaction, fission and fusion, and in advanced thing is reactors. If possible, get a more information regarding the reactors. Okay. So these are the things. So it is a basic knowledge of your nuclear chemistry. So once the old element which is changed into new element with respective result, that is an alpha particle. So at the time the overall transformation is changed from one phase to another phase. That is a new phase. So here we can able to view such a radium 226 is changed into radon. Okay. So with the result of these things. So something is going to bombard this Ra, which leads to give a Rn. So we will go a little bit fast. So the transformation, overall transformation is changed in your content from one to another. So that it also call it as a nuclear transmutation. So the conversion which is discussed by the Rutherford in 1919, the nitrogen 14 into oxygen 17 when in their research. Then they identified that alpha is playing a role in that part to changing this one to another form phase. So that's the initial reaction they identified by the Rutherford. There's an alpha bombardment. That's a alpha is a initial projectile, that is a small v, that is a capital B. So we are going to give a B, capital B and small b. So our major motto is oxygen. So nitrogen 14 converted to oxygen 17, which leads to give a result with respect to particles. That is the alpha particle. So the ones, if you want to write out the overall bombardment reaction in a nuclear artificial transmutation of such elements is denoted like this. Within the bracket, we can able to tell about the alpha and protons, which is presented here. So this term, overall term, designated the overall reaction in a compact manner. Okay. So A to give B with respect to this one is a additional product which is going to help. So so the reactor setup is a little bit different one. I am not going to interior in this part. So just for your view, this is the setup to declare this overall reaction, synchrotron particle oscillator, which helps us to promote the Al into P, into phosphorus. Okay. So the alpha, we are discussing the alpha particle. This is the alpha reaction. When we come to the another case, if we are changing, if we are changed by the alpha, there may be possible to bombard it by the neutron also. That's a thing they started. That's a thing they started with the neutron bombardment also. So the neutron also are playing a same role, neodymium 142 into protium 61, which is as similar to the previous one, alpha bombardment. So somewhat changes will happen in the charges, elements, and the electrons and neutrons, whatever content. So N01 playing a role in the neutron bombardment and alpha bombardment 2 alpha 24 is playing a role in this case. So neutron bombardment and the alpha bombardment. So like that we can able to get the distinguished product and the distinguished reaction. So whatever the alpha or beta, we are having a one product which is bombarded by some other external element. It is pleased to give new things, okay, with the supportive byproducts. So the transmutations of your elements is this is the chart which tells about the overall transmutation element and their possibilities after the 93 element, atomic number 93. So we can able to view how far it is going to change it from one to another, especially after the 92. So this is a nuclear fusion reaction. So nuclear, when we are coming to the nuclear fusion, the reaction, predominant reaction, which is a very highlighted one, is deuterium interacted with tritium, which leads to give a helium, and with respective neutrons and the excess of energy. So that's a thing which is important one in the nuclear fusion. So whatever the reaction is happening, we are getting some other energy. From that energy, we are going to convert it into the daily life utilization. That's a thing we are utilizing the solar panels, and in future everything is comes under the solar energy is going to convert for our daily utilization as per the petrol rate in India. Okay. So the nuclear fusion or fusion is happening in the natural process. When we come to the natural process, our sun supplies the energy to the earth with the respective distance. We can with chain nuclear reactions. So enormous energy is reflected from the sun towards our energy. It must to be utilized for our safest and cheapest one. That's a thing we hope the science will help us. Okay. So these are the nuclear reactors. How far the nuclear reactors are going to help set up is presented in various manner. Okay. So I am skipping that one. The nuclear fission. When we come to the nuclear fission, some other neutron is going to bombard your uranium 235, and which leads to give a uranium 236. After that, in addition to that, it leads to give a various type of response as like this image. Initially 235 uranium to somewhat uranium, or it leads to give a, after that it leads to give a krypton and barium with respect to 3 neutrons, and it will deliberately attack some other neutrons, and again and again and again it leads to give enormous energy, which is unpredictable one. Okay, the various changes will happen in your reaction based on the mass number with respect to fusion, and fusion is based on your binding energy and the electrons and neutrons which is presented in your cases. So this is the nuclear reactor. So here the setup are arranged schematic diagram of a light water reactor plant. Okay. By using that way, we can able to enrich that one. Right. So these are the things basics which we comes from the nuclear chemistry. By utilizing this one, which is started from your electron, neutron, proton, and isotope, isobar, isotones, and the nuclear reaction and nuclear decays, alpha, beta, gamma, electron capture, positron releasing, okay, and the transmutations, how far it is going to transfer from one to another. These are the things you must come across such cases. Okay. So right. Let me start with some questions regarding your CSIR. So the C14, so the C14 which tells about the question which is based on the carbon dating. The carbon C14 dating method is not usually used for the dating of organic substance greater older than the 60,000 years ago. Okay. So from this we are having the four example question answers. Such objects are rarely contain carbon. Such objects are accumulating C14 after their formation, and in those times there was no products of C14. Most of the C14 is sample would have a decay. So here we are having the possibility for the D. So here in that radiocarbon dating prefers the radio which is referred to a simple carbon dating. And this radiometric dating method that usually naturally occurring one isotope C14. So especially in the carbon dating, it must be very material up to the 58,000 to 68,000 years. Okay. So that's a thing, this much limit is there for your carbon dating. So when we come to the plant, like atmospheric carbon dioxide, when it is in the organic material, in the photosynthesis, whatever it is, the quantity of such a carbon 14 is approximately matches the level of the isotope in the atmosphere. So among that overall four answers, the C13 limit is 58,000 to 60 years. Okay. So when we next in the carbon dating applications, so we are having the four answers: alpha, beta, gamma, positron. So when we come to the carbon 14, we are having unlike carbons 12 and carbon 13 is radioactive. Means that over time of carbon 14 will decay. So when we are having a C14 decay, it gives the of a beta is a preferred one. Beta response or beta particle activities are more in the C14 emissions or emissions than the others, whether it may be comes under the 12 or 13. So the representation of your concerned carbon dating with respect to C14, which leads to give a N14 plus beta, which is most intense than the other reactions, especially other carbons. Right. When we come to the nuclei, of phosphorus and the sulfur with respect to isotopes. So we are having if you are isolated through this same potential difference, entire uniform transparency magnetic field is Z equal to 15, Z equal to 16, based on that content, whatever the things. So the concerned neutron and proton. So the proton in the phosphorus is 15 and proton in the sulfur is 60. So with respect to this, we want to tell about their as they merge from a magnetic field or not. There is an option for both nuclei merges undeflected, but in the B, P is deflected less than the S, and C, P is deflected more than the S. Both are equally deflected. So the reason for a correct answer is B. To just check out the rest of the things when I am discussing this one. If we are, if we right now we are having answer as a B. So B is when we go for the B having a number of protons which is 15, and number of protons, and S having a in the B we have P and S having a number of protons with the same number of additional protons and neutrons in the case. When it leads to give a beta decay. Okay. So such a reaction is happened during the time of conversion from P to next one, okay, with respective protons. At a time there may be some other less changes is deflected is happen in the case of phosphorus than the sulfur. So that's a thing which is not present in the case of C or D or A. So everything is bounded with respective neutrons and the protons which is presented in your case. So the highlighted point here is the phosphorus 32 only exists in small quantity of earth, as it has a short half-life of 14,268 days, and so decay rapidly. So here the decay is happening with respective elements. So the answer is B. Right. So the nuclei among the following capable of undergoing a fission process with respect to thermal neutrons. So thermal process is happen if you are having some other element. What will be the possibilities? So that elements may be 233, 235, 239 Pu or 232 Th. So we are having the four elements. Among that, we must to declare the things. So here the possibilities are and comes under the nuclear fuels. So the year 235 occurs a natural uranium and enriched uranium, and Pu 239 breeds the uranium 238 by the from capture, and the 241 breeds them from Pu by neutron capture, and the Pu 240 comes from the some other 238 isotope by the same process, and 233. So here they are asking about the nuclei among the following capable of undergoing the fission process. So here the fission process is ultimately goes to the natural uranium and enriched uranium. Okay. So that's a 235 with respective 240, 233. Okay. So we are having a possibility for 1 D. So in this case, we are having 239, which is from a 238. After that, it will used to give a Pu. Then it will goes for that case. So the answer here it is based on the D. Right. So the reaction which is based on uranium, we are having the 4 possibilities, which is based on the uranium oxygen content. So based on uranium oxygen content, how far it is going to deal in this overall set. So the among this, we are having a first one, which is based on the disproportionate more than the concerned things. So here we are having the possibilities for A. So 1, 3, 1, 2, and 4 is the result. So how they are declaring this one, just we will discuss. So if you are having a uranium oxide with a plus, it disproportionates more easily than the 2 plus. And U3O8 is more comfort zone in the stable manner when it is with the when oxygen of uranium. Okay. So there's a thing that A, which is 1 and 2, we are having an answer for that one. So the most stable one and the most disproportionation more easily than the case, that will comes under this one. So when we come to the point 4, the coordination number of your uranium in this such a complex is 8. So in this structural arrangement, it is a linear one. The respective linear structure based on this 8, we can able to see that overall thing is comes under the linear. So here the point which is given is whether it is linear or not. So here the coordination number for uranium is 6. So it is a wrong calculation for such a thing. So the rest of the 3 is correct one, 1, 2, 4 for A. Right. So the next case, when we come to the endogenic reactions, what will happen? What we mean by threshold energy? How far it is going to detailed? Okay. So we have to choose the statement for magnitude of threshold of an endogenic nuclear reactions between stationary nucleus and the moving projectiles. Once there is a stationary nuclei, such like your audience, we are a projectile, we are going to bombard you with the CSIR knowledge, which is leads to give some other result. Addition to that, some other result with some other thermal changes is happen or not. Whether at the time of Q, the equation is missed here. A and B leads to give a C and D with respect to Q. That Q is the energy which tells about the overall plan. Whether that energy is plus or minus. If it is a plus, it will be a spontaneous reaction. If it is a minus, then it will be a insisted one. Okay. So based on that plus and minus, we can able to declare it whether it is a endothermic reaction or exothermic reaction. So the endothermic is a reverse one. Okay. Don't think it as a, if you are getting a Q is a minus value, then it will be a in endothermic or exothermic. Don't confuse with this. So when we are having the delta H is equal to plus value, it will comes under the endothermic nature. So if you are getting the delta H is equal to minus, it will comes under the exothermic, which is releasing the energy and which is absorbing the energy. That's a thing which is distinguished in these two cases with respect to Q value. The threshold point. So the threshold point which is discussed here. So the threshold point is a minimum energy required to carry out such a reaction. So minimum knowledge you must to get by using this seminar, then it will lead to choose the correct answer in your CSIR examination. Okay. So the minimum energy carried out are that such a energy which is called as kinetic energy. So minimum energy of kinetic energy that the projectile must to make a reaction go through is called threshold energy. So here we are having some other Q. That Q is a kinetic energy. So whether that Q is greater than your threshold or lesser than the threshold. Based on that, the reaction plan is different. Okay. So the reaction plan here is if you are having a kinetic energy is greater than 1 in your then the threshold, no reaction is happened, nothing held. It must to be a lesser than compared to your threshold. Even it is equal to one another, there is no chance to get a reactant. Okay. So at the time of kinetic energy and threshold comparison, if you want to get some reactant to product, that must to be a less kinetic energy than the threshold energy. So you must to be very polite with your faculty to get a good knowledge. So you must to be a lesser person when you discuss with your faculty. Then only faculty will give much more interest to give more knowledge to such like audience. Okay. So here that Q value is must to be a lesser one compared to the threshold only. Then only we can able to get the reactions. So come to here. We are having some other nuclei and it will be projected by some other things. So it is a greater than the Q of your nuclear reaction. So the concerned threshold with respect to things is greater or not. So it must be lesser. Okay. So the last point which tells about the kinetic energy of the Q value, which must be lesser compared to your threshold value. So see this one, then only some other reaction will happen. So point number 1 wrong. So it must be great. Threshold, yes, threshold correct one. First one is the correct one. The threshold energy is a greater one compared to the Q. Okay. So the kinetic energy, that means the Q is lesser compared to 1, then only the reaction will start. So rest of the thing is against the rules, which we discussed with the kinetic and threshold one. So more than the kinetic energy, not possible. No reaction will happen. So less than the Q value, nothing is possible. Okay. So whether it is equal to one another, no chance. Everything, every 2 points are discussed in the single line. No reactions happen. Whether it is a lesser or equal, nothing is happening. That's all. So when we are having a reactions, especially the nuclear reactions with the Mg24, which leads to give a Na22. From this statement, we must choose the answer for such a case. So once we are having a reactant to product, which leads to give a Mg to Na, which is bombarded by the deuterium as a projectile. At the time some alpha is releasing, that is a He24. So here we are having a pointing the point number A is correct one, that is which is against the 4th point. Among the 1, 2, 3 overall result, 1, 2, 3 is a correct one. 4th is against the nature of such a reactions. So this is the reaction which is happening here. So the point number, we will go for answer that kinetic energy of D particle is not fully valid for the excited 20 mg. So, and the point 2, the total number of protons and neutrons is conserved. Q, the Q value of nuclear reaction is much higher than the magnitude relative to the heat of chemical reaction. The point number 4 already which we discussed, it is not possible by the previous discussion. Kinetic energy must to be a higher one than the threshold. So the point number 4 is skipped one. So possibilities are 3. So with respect to these details, the Q must be a greater one than the concerned heat of the reaction, and the proton and the neutron is conserved during the time of these overall reactions. no enough energy in d particle. That's a deuterium. Small d representing the deuterium. Okay. So no enough energy is in d particle. That's a thing. So among these four, 1, 2, 3 is correct. Due to that, A point is correct one. The nucleides among the following, the capable of undergoing the fission by the thermal neutrons by using these equations, by using these elements. So we are having the three possibilities already, which we discussed, right? Yes. So we are having the already which we discussed. Even though we are having some equations, just go through that one. So once we are having a 238, it may lead to give a nuclear reaction towards a 298, 239. After that, beta progress is happening 299, 239 with respect to changes in the element NP. Okay. So if it is going more, then it will comes to the Pu 239. So all of the isotopes of Pu are fissile and used as a nuclear fuels. So here they are asking about the fission process held by some other thermal reactor under the neutron process. This happened in the case. So here we are having a possibility for the D. 1, 2, 3 is the correct one. Fourth one is not possible to attain such a 232 thorium. Okay. So that Pu 239, 233, which is one already discussed by using the fission process, and 235. These are the possible fission reactions by the thermal progress. And Mg reactions, as is already discussed. Sorry. So the Q value, so the Q value, how to determine the threshold energy by using this equation. So based on your number of protons and number of neutrons and the mass of such a protons and mass of such a carbons. Okay, what are the things which is collected from your concerned materials. So here we are having the threshold values for calculating this result. Which one is going to correct? By using this formula, we are having a Q is a kinetic energy. With respect to kinetic energy, we have to substitute that value. So here they are highlighting the changes which happen in carbon 13 to 9 N13. During the time that MP and MC, which tells about the mass of proton and mass of carbon. So the 13, which is substituted for MC, is mass of concerned carbon and the protons. So by using that way, we can able to calculate such a result. Okay. So by using this, we can able to declare that overall result will comes under the N13. For such a case of N13, the result is 3.236. And for C13, we are having minus 3.236. So based on that, we can able to choose whether they are asking for carbon to nitrogen or nitrogen to carbon. We can able to calculate that. So by using that, we can able to calculate the things, and they are the value is negative value. That means is changed. The overall reaction which is started here, it is carbon to nitrogen. They are giving the two possibilities. One is nitrogen to carbon and carbon to nitrogen. So by using that way, we can able to tell. Okay. So the threshold frequency and threshold value and their calculation tells this overall result. So by using this threshold, the value is 3.485. Okay. C. So the identity of your concerned nuclear content. So we are having a two content. One is reactant and another one is product. During the time we are having a within a bracket we are having a probabilities. So among that probabilities we can able to declare that such a kind of what kind of type of decay is happened, what kind of emission is happened, what kind of capturing is proceeding within your content. Okay. So straight away I am going to the result of your changes which is happening in this case. So by using these corners, we can able to detect such a things. So when you go for the alpha decay, the A is decreased by 4, number 4, and the Z is decreased by number 2. And like that, the beta changes will happen, and the gamma unchanged one due to their 0, 0. So here we can able to see that one. Why it is changed by the 4 and 2. So it is alpha, which is a helium. So we are having, when we are changing the reactant to product, we can able to visibly see that A value and Z value is changed with respect to neutron and protons. So the changes will happen in these overall cases like this. So here the possibility when you are searching for this with respective changes, you can easily direct such an answer is 4. That means that electron capture is happened. So already they are asking that kind of question only. There is a clue that is a capture. So among that, we will straight away we will go for capturing process. X leads to interacted with some other E minus 1, leads to give a E minus 1 and Y. Okay. So there may be the interaction of electron with respect to X leads to give a Y. At that time, some other X-ray is released. Okay. So what will happen in the A unchanged? What will happen in the Z? It is decreased by the 1. So among this, you must to check whether that same type of result is merged, coincide with this overall result. The clue here is A is unchanged 1. So rest everything is changed with respect to reactant and product. So the numbers are changed 9, 8, 23, 24, 63, 6, 24. Only one thing is unchanged 107 and 107. So the result is there, even though there is a changes will happen in your Z value. So they are not insisted about the Z value as per your result. So one more thing, that identification of overall types, the result they are asking about the capture. So straight away we can able to move to electron capture, and final result is discussed by this key point: change in mass and change in atomic number. Right. Again, we are going to come with a threshold energy with respect to kinetic energy. And this is the thing. We discussed, but again they are asking this question in some other year. So for your more detail, so here we are having the two possibility cases. That is a representation of your overall chemical reaction when it is interacting with two type of reactant with one another. It must to come across such a energy barrier, that is a activation energy, which is leads to give some other product. So if you are getting some other excess of energy, then only you can able to get the come across such a barrier. Okay. So that kind of energy is what? That's a question. So if it is a threshold energy or kinetic energy, how far it is interrelated with one another. So here we are having energy between your reactant and the stage. Okay, so we are having some other energy between this gap and this one, which tells about your kinetic energy. This one is overall thing tells about the threshold energy. So once we are having such a things, so the threshold is always a bigger one compared with your kinetic energies. So that's a thing that Q is always lesser than the threshold Q, T, threshold energy. So whether it is equal to one another, this gap is equal to one another, that means the kinetic energy is equal to such threshold energy, or it will be greater than such things. It is there is no big processes happen in your chemical reaction. So whether it is comes under the endogenic or exogenic, that is based on your concern, gives energy and this reaction condition, reaction nature, whether it is a spontaneous one or insisted one. Okay. So if it is a spontaneous one, then that reactant must be a higher value than the product. So the delta G is lesser than the 0, and if it is a endogenic reaction, then it is a delta G is greater than the 0. So by using this, we can able to tell that energy absorbed or energy released. So once it is absorbing the energy, it will comes under the endogenic. If it is releasing the energy, it will comes under the exothermic. So the atmosphere will increased by the some other heat due to such a reaction. So by using that, we can able to declare that A1 first point is clear. Rest of things are omitted one. So the greater threshold energy, which is insisted here, greater threshold energy is higher than your consumed kinetic energy, which is presented here. The fission process of your concerned uranium-235. The concerned uranium-235 split into the krypton and barium, and then with respective neutrons. So each and every reactions we can able to see that 3 N's are split over from the previous cases. So there is a enormous neutrons is splitted in single uranium-235 bombardment with some other projectile, which is a neutron. So once it is considered in the reaction is a nuclear fission of concerned uranium-235 under the thermal process, what will happen in this case? Okay. So the percentage of nuclei undergo percentage of the percentage of nuclei undergo unsymmetrical fission is maximum. Unsymmetrically, whether it is going to split or not, yes. So we can't able to know whether it is going to split the symmetry one or unsymmetry one. There may be the more splitting. Definitely, it will comes under the unsymmetrical nature. So in each fission, one thermal neutron is proceeding. No. So we can able to see in each fission reaction, we can able to observe 3 N. Okay. So not a single neutrons, one thermal neutrons. Okay. So we can able to that overall thing in the single step reaction, overall thing we can able to get a nearly 2.5. 3 neutrons divided by so the average of such a reaction is 2.5. So the possibility for the second one is no. Okay. So the C magnitude of energy released per fission is order of 200 MeV. So that's a theoretical part. So based on your concerned reaction, that order of your magnitude is nearly 200 MeV. So by using the theoretical knowledge, they are choosing this question. So A and C is the correct answer for such a reaction. Right. So you can able to view the previous question in this case also. So if you bombarding this uranium-235, it leads to be 36, and then at least 141 barium and krypton with respective neutrons. And such like that, it will happen in this next case. So it will be a continuous process which is initiated by a single pinpoint neutron. So the projectile, even though the projectile is small, it leads to give a miracle in the overall concerned reaction. So whatever the knowledge, if you are getting a big or small, it may utilize in some other extent. So get a knowledge in correct time and correct one. So the reactions which is given here is possibility with respect to first one. Okay. So whether which one is the right one among this discussion? That's a question. So here there is a possibility for 235 to 236 uranium. So that's a thing which is discussed for your concerned answer. So rest of the things are there, but that uranium 235 to krypton and barium is there. But here that result of that one is 2 neutron. That is not hopeful. Only 3 possibilities are there in each step. So once it will be the preferred one is 235 to 236 during the time of bombardment of their projectile. So rest of the things are wrong one. Right. So the capturing of again one electron capture reaction is there. So by using this electron capture, we must choose the which one is the correct answer for the barium 13156. So what do you mean by electron capture? The electron capture is a process in which the nucleus absorbs an electron from an inner electron shell, usually the first or second, whatever it is. The ones inside the nucleus, the captured electron combines with the proton to form a neutrons. That's it. So this will happen in this overall process. Some proton and the electron is there, combining with one another leads to give a N01. That's it. So the carbon 11 with respect to electron leads to give a boron 11 with some other neutron. So that's a thing. So directly we can able to say there is a change, there is no changes will happen in your upper part. That is the one which leads to come to the resultant, the 1. If you are having a 1 in a proton and the electron leads to give a -1, hence we are going to give 0. So due to the electron capturing, some other minus is there. So due to that, it is losing some other numbers. So after that, if you are least to give the result, then which one is the correct one? So finally we will skip the first and third, which is very similar to such a things. Okay, this up. Okay, sorry. So BA. So when we come to the BA 13156, yeah, if electron is captured, then what will happen in that case? So 1 minus 1 E is there, then it will leads to give a 55 BA or some other element. So some other element must have some other reduction 1 electron. So -1 is must to play a role in this case. So some X product is there. It must to give a 55 131, right? We hope that one only. So the answer must to be at 131 is as such. Result of your result of one capturing of electron is 55. Then where is the result in this among the 4 1? Nothing is there. So then we must to read out your concerned reaction, concerned question with respect to things. Once again, you remember that one. The word here is 2. So 2 sequential electron capture is there. So 2 consistent electron capture is possible with respective element BA, then what will happen in your concerned product? That's a question. So you must to be don't take it as a single electron capture. You must to be a 2 electron capture with respect to BA. So for that case, you must to reduce one more -1 in that case. So 54 must to be there in this one, and 131 is as such. So 54 is having a 2 options. So among that, 130 is a wrong one. As such, must to be there. So the possibility of concerned X element is Xc. That's it. So that's a thing which is little bit discussed in the nuclear chemistry. I hope to finish the polymer also. So for that case, I am giving some other introduction regarding the polymer chemistry. Single line syllabus is there, but you can able to get a good marks in a nuclear chemistry and the polymer chemistry with respect to concerned reactions. So we are having a polymer having a more number of units. So due to that more number of units, we can able to view such a number of unit materials which is combined with one another. So for our daily utilization, whatever it is. So what do you mean by polymer, which comes from the Greek word many. Mers tells about the units. That's all. Many units. That's a thing which is detailed about your polymer previously. The word which is a common word is macromolecules. Then it will be changed further. It's a poly or macro, whatever it is. So the polymeric material having a more number of units combining with one another, it looks like a chain. So it is having a more different number of classification based on such a origin, structure, molecular forces, polymerization, and their concerned unit monomers involved in the specific structures. So this is an interesting slide. Just go through later. So whatever it is, the polymer is a branch of science. It deals about the physics, chemistry, and the interdisciplinary properties. Then it will be utilized for our daily usages, textiles. So the classifications, which is based on the natural, synthetic, semi-synthetic polymers. By the term itself, we can able to think whether it's a natural means we can able to get it directly. The rubber tree gives the rubbers, like that the cellulose proteins are which is come from the natural process. PVC and plastics, plastic chair, plastic pipe, laptop, whatever it is made by the synthetic polymers and semi-synthetic polymers. We can able to combine that both the things with one another, which leads to give the result. Structural features distinguish this overall case, whether it is a linear one or some other branched one or cross-linked polymers or things based on structure, based on molecular forces. So based on the molecular forces, we can able to split the polymers by thermoplastics, thermosets, elastomers, and fibers. So whenever we are using that one, the thermosets and thermoplastics are very much utilized, but how far it is going to change in future, that's a question. So the polymer classification under the mode of their additional and condensation methodology. Just I am skipping that one for more additional details. So based on the monomers, how many unit of chain is there within a single polymer, whether it is a homo polymer or more than that one. So basic things are polyethylene, PVC, and nylon 6 is a basic one, which is having a homo polymer, single monomer. That's a basic unit. It is combining with another, and then it leads to give some other string limit. So the classifications. I'm not going to discuss more things, just for the detail of the representation of polymer. So these are the basic things which is distinguish these overall arrangements of your classification under the polymer. So there's a slide, sir, which I am going to discuss. Each and every polymer is having a number of units which is combining with one another, which leads to give a different arrangements. From that arrangements, we must to calculate the concerned weight, such a molecular weight, such an average weight or weight average molecular weight. So some parameters are there, MW, MN, MU, and MX. Okay. Some parameters are there, that is to distinguish the polymer by using some other techniques. So here we are having the number average molecular weight, which is distinguished by M1, weight average molecular weight, which is distinguished by MW. Just go through that one after receiving my slides. That's it. So due to the time limit, I am concising this one with this one. Okay. So the next one is viscosity average molecular weight, MV, which is based on the with respect to viscometer and the molecular weight related to this concept. I will conclude it with respect to overall details. So the average molecular weight with respect to MZ, so by using the ultracentrifugal technique, MZ. So whatever it is, we are having a various type of M value, MX. It may be M viscosity or M average, or it may be weight average or number average based on the concerned I values. Polymer chain, whether it is a height of polymer or with molecular weight, concerned molecular weight, and concerned number of polymer, and weight, WI weight fraction of polymer chain with respect to molecular weight. So the graphical arrangement between the weight and the mass leads to give a different type of M values with respect to distinguished region. So that is MN, MW, MZ, M viscosity. So that's a thing which we discussed earlier in the previous slides. Just go through that one. So each and every values are distinguished. When you see this image, you can able to tell the once we are split out in this graphical arrangement, we can able to get the number average weight, and between the weight or middle the weight, then we can able to declare what kind of material and how far it is going to utilize for us. So finally, what is the content which is present in your concerned polymer, macromolecule, whatever it is. So by using that way, we can able to identify such a molecule by using these various techniques. What are the various techniques? So the various techniques which is utilized here is the techniques related to colligative properties, especially the osmometry and the vapor pressure osmometry, and the next one is mass spectrometry. Okay, okay. Okay, sir. Cooper, sir. So we are having a MN, MW, MZ, N. So it may be distinguished by the osmometry, mass spectrometry, and the light scattering technique, which is distinguished the MW, weight average molecular weight. And this is average molecular weight, which is by scattering technique, centrifuge technique, and chromatography, and M infinity, which is tells about the viscometry technique. So each and every part of your graphical arrangement, we can able to tell which type of polymer and how to detect such a things, and what is the upper limit of your such a polymers. So the technique for determining a molecular weight by using the various one, this is the highlighted techniques which is up to the CSIR level. That's a enough one. So osmometric technique, light scattering, gel permeation, chromatography, or viscosimetry. So by using that, we can able to distinguish the various type of molecular weight with respective upper unit, gram per mole. That means with respective unit, we can able to distinguish such a things. So the enormous techniques are there and the enormous different distinguished molecular weights are there. By using that, we can able to declare such a region. We can able to get their concerned shape in specific techniques like light scattering and X-ray microscope, which is having such a things, and molecular weight distinguish, and some by using the various techniques. So there's a value ranged. If you are getting some other range between the 10 to the power 4 to 7, then we can able to tell such a things having the smaller molecule, which may be a slow measurement, insensitive for such a things. That's the reason we can able to get it. Okay. So the less than the 10 to the power 4 tells about the smaller size. If you are having a more than that, the cell permeation. So the commands are different one for the different techniques with respective molecular weights. So these are the things. I'm having some other questions to discuss. By the time limit, we can't be able to do it. I will send the details with respective answers to your concerned coordinator. Then you can able to get it, the reactions, answers. Okay. So point to remember is nuclear chemistry, basic nuclear chemistry and their stability, nuclear stability with respective N by P ratio is important on mass effects and binding energy, packing fraction. You must come across in your UG level also. A magic number and cells and isotones, isobars, isobars. These are the things basic. So in addition to that, just gain the projectile details, whether it is a alpha projector or neutron projector and various nuclear reactions, nuclear fissions with respective detectors. Get some other knowledge with respective detectors and how some other detectors are utilizing, at least with respective schematic diagram of concerned nuclear reactions. With this knowledge, you can able to click out your correct answer in your nuclear chemistry part, and by using some other knowledge which I am given with the various techniques, you can able to click out the answer for your molecular weight of polymer chemistry. I will try to send you your concerned answer for your more explanation. One more thing is to remember you, I am working in Central University of Tamil Nadu. Here out of each and every class, we are having 30 pupils, nearby 30 pupils. Here only one thing is to discuss with you is out of 30 peoples, most of the peoples are coming from the other state. They are getting the offer letters. They are getting easily entering into our Central University, which is situated in our Tamil Nadu. That is the Central University of Tamil Nadu. Only one university which is present in Tamil Nadu. But out of 30 peoples, I don't know about other department. In the chemistry department, out of 30 peoples, nearly 20 to 25 peoples are coming out from the other states. They are get very much knowledge about the concerned details about the fee structure and infrastructures and everything. They are getting the knowledge from their friend circle or whatever it is. So whether we have to do or not, they are doing. That's a question. They are giving the information to their friend circle, whether I am applying or not. Just they are informing to your friend circle at the time of February month end or March month end. They are giving the opportunity, or they are discussing with their friends. Especially in the chemistry department, in their chemistry department, there is a possibility for integrated course. Integrated after +2, you may join MSc, direct MSc. After your BSc, you can able to join PG diploma course. If you want to line some other education atmosphere, you can able to get the get a PG diploma courses. And BSc BEd is there in other department, education department. They are providing BSc BEd with a four-year course. Okay, these are the possibility for the science, especially in the chemistry peoples. So try to spread over the information to the other peoples. At the end of February or the March month, the applications are open for everyone. Like that, one more university is there, which I got a PhD degree. That is a central university, which presented in Pondicherry. So nearby options are two big universities are there for you. One is Central University of Tamil Nadu, another one is Pondicherry University, and nearby NIT Tirchi and CSIR Karakudi. Everything is there. Bharatdasan. Okay, I am talking about the central institutions. Whatever the things you are having nearby, it's not at all issue. How far it is encouraging your next level of your work. That is the thing which is happening here. Try to get a seat in such a premier institution. And I would like to thank for fruitful efforts for Dr. S. Gomudi, who is a convener, who helped me much more supportive to give this opportunity with my scientific persons, especially that Professor Murugadas sir is a very kindful person who helped me more to arranging this, and Ganesh Raja, Dr. Ganesh Raja, and Chandrasekhar, who is a colleague for me, who is supporting this one. All credits goes to Gomudi madam, and additionally who supported here Dr. Keshavan sir, and webinar coordinators and organizers and management of PMIST. Thank you one and all. Questions?
Thank you, sir. Thank you very much, sir.
Yes.
So, moving on to our next speaker, Dr. A. Murugadas. He will be delivering the lecture on spectroscopy and their applications. He is a renowned scholar and he is the head of the Department of Inorganic Chemistry, University of Madras, Chennai. Sir. Sir, you are not audible to us, sir.
Sir, please join in your audio, left-hand corner.
Okay, sir. Thank you, sir. Now you are audible, sir.
Yes, am I audible now? Dr.
Yes,
Karthikeyan?
Yes, sir. You are audible right now, sir. Welcome, sir, to our department, to our webinar, sir.
Thank you.
So you can start, sir, your presentation, sir.
Shall I go now?
Yes, sir. Yes, sir. You can start, sir.
Okay. Let me clear one thing, Dr. Karthikeyan. What are the audience, whatever audience here, and only the students or scholar or postgraduate students or teachers?
Sir, scholars are also present, students are also there, and faculties are also there, sir. Everyone is there, sir.
So postgraduate students are all here, am I right?
Yes, sir. Yes, sir. Postgraduate, undergraduate students are also available.
Okay, sir. Thank you very much. Thank you very much.
Thank you,
yeah. So thank you very much, Dr. Karthikeyan, and the PMIT management and the convener and the co-convener and the organizing committee members who arranged for this webinar on national level, it's a national webinar on the tips and tricks in CSIR-NET, chemical science examination. This is a wonderful opportunity for me and to recall again some of my basics and also to deliver the lecture to in front of you all people. This is a great opportunity for me that once again I thank you very much for this one. I also thank Dr. Rajkumar who is connecting always connecting me to discuss about these topics and to discuss about this lecture for further arrangement along with Dr. Komadi and who is the convener of this one. Thank you very much. Okay, student. I think this is now so much tired you all of you because the whole day you are listening all the talks without any break except this 1 hour lunch break. I don't know how much I will be so worth that I can reach you this so much in this tired the circumstance. Let us try to explain much better and simple way so that I can interact you. All right. My lecture today is not question and answer based one because it's a more fundamental aspect on the spectroscopy one. First of all, you understand this. Then end of this lecture, we may discuss a few questions, 1 or 2, 3. If you answer clearly, then I will be so confident that you people understood something from my lecture. All right. So now let us move step by step. So this is kind of discussion. So feel free to ask me. Feel free to stop me at any point during my lecture whenever if you have any clarification. Okay. So don't sit with clarification and you please clear at the time at any point. All right. So it's like a discussion. So my aim is that I have to take you so enthusiastically till I complete my lecture. This one. All right. So let me start now. This is spectroscopy and its application. This is the title that was given to me to deliver on this topic today. So this is my contents. Today, the first few slide I'm going to talk about what is the spectroscopy and how to understand how it is applicable to understand the material or molecular properties and what information we will get from that and what kind of spectroscopy is available to understand your molecule. So we are the science people, either physics or chemist, doesn't matter, or biology. So the spectroscopy is like a backbone. Without that, it is not useful for studying. Okay, as a chemist people, our aim is to develop some molecule, understand those structure of the molecule using the spectroscopic tool, and try to bring out some new properties. Am I right? This is our aim. So that's the reason how much you are giving the importance for your study. The same impact you have to give to learn about the spectroscopic tool. Okay. So the second thing I'm going to talk about the principle of UV visible and as well as the principle of FTI spectroscopy and its application. So I will give you in between this during the talk a lot of tips which is very important for or which is frequently asked for the CSIR and NET qualification, this GATE examination questions. You please note on this some points. I also ask 3 questions in between. You have to be very careful, especially for the student, undergraduate or postgraduate or scholars. Okay. Okay. Let us move now. The spectroscopy. The spectroscopy is the science of or the study of interaction between the interaction between the radiation and matter. So which way it's going to interact and what is the main species in that? So what is that kind of interaction that we say here? So you see that radiation nothing but it carries the electric field and magnetic field. So the material is it's made of atoms or molecule. So the atoms or molecule nothing but is always again is the electrons and proton is there. So when the radiation interact with those atoms or molecule in the material, so that will respond. So how that going to be respond with your instant radiation? To study about that is called spectroscopy. Am I right? So how to probe that? What information it is giving? So how are going to measure that kind of this kind of interaction? Okay, so in order to that you need to make some device. So that is called as a spectrometry. That device name is called as a spectrometry. So we have the various kind of device to measure and to get the information of various kind of interaction when interacting the light with the matter. Okay. So another important the terminology is here spectrophotometry. What do you mean the spectrophotometry? It is specific to the specific norm, and never forget about that. People will confuse sometimes. For example, some guy you ask, they don't know sometimes the differentiate really mass spectrometry or mass spectrophotometer, or FTIR spectrometer or FTR spectrophotometer, or UV visible spectrometer or UV visible spectrophotometer. You can say only UV visible spectrophotometer, but rest of things you have to say spectrometry or spectrometer. All right. So the UV visible only you have to say that is a spectrophotometry or spectrophotometer. Okay. What is spectrophotometry? The quantity study of interaction of the light with the matter. That only the spectroscopy you can call the what is the spectrophotometer. It is an important difference between what is the spectroscopy and the spectrometry and spectrophotometry. So what we have to take here? So we have to take care because every molecule has its own unique set of spectra, and some of them look similar or near identical, but there will be the one spectrum which will be entirely different. So we have to pick up, and that is going to be distinguished tell us what kind of properties that molecule does or is possess. Okay, that is what we have to use. That is what our knowledge is. We have to learn that to get that knowledge. Okay. So second is that electromagnetic spectrum. What is this? Electromagnetic spectrum is there is which is the combined of series of wavelength region that start from the gamma ray to the radio frequency. So if you start from gamma ray to the radio frequency, you see that the lambda will keep on increasing. So when the lambda keep on, the wavelength of light is keep on increases. What is the energy is decreases because the energy and the lambda is inversely proportional one. So in whatever the wavelength that incident that is it has always the same velocity. Okay, that you have to remember. Okay, so this electromagnetic radiation, as I said earlier in my first slide, it carries the both electric and magnetic field that interact with your atoms of the molecule of the matter, and that gives some information about your molecular material properties. Okay. So there are some the formula that we use to quantify this interaction, because the electromagnetic radiation carries the photons or quantum of energy, and the molecular atom also possesses some discrete energy level, and each photon has related to the some kind of interaction with carry some amount of energy. That is what we are going to say, some kind of form of interaction. Okay, here you need to understand what is the wavelength and what is the lambda wave number, or what is the energy. Okay, the wave number is always directly proportional to your energy, whereas the wavelength is indirectly proportional to the energy. So most of the spectroscopy we will use monochromator or polychromatic, the beam of electromagnetic radiation depends upon the what kind of the analysis that you are going to do and get the information. All right. So the light can be used to understand some various spectral method. Because first of all, it can be used to gain the various material and chemical properties that can be measured the elemental composition and identify pure substance or the component of mixture, whether it's a one component mixture or two component mixture is there. You can quantify quantitatively, you can say using the spectroscopic method. And what are whether it's a trace amount of compound, whether it's ultra trace compound, these all things are there, you can easily quantify. Even surface composition, if you take the X-ray photoelectron spectroscopy, and using the spectroscopy, either especially you can measure very important parameter like reaction rate, and you can deduce from that mechanism and the type of product formation during the reaction. This all the information can be obtained using this using the various spectral method. So what properties that we can measure using this when the incident the radiation incident on the material. So the absorption, how it absorb the material, and once it's absorbed, it has to come down, whether it is coming down as releasing as a photon, or it is giving some kind of heat, that is called emission, whether it's a fluorescent or phosphorescent or thermal emission, or it is a photo emission or the chemiluminescence. Sometimes during the chemical reaction, some luminescence has come out from that, and whether it is some the scattering or elastic or inelastic scattering. We talk about the Raman in inelastic scattering, and the polarization and phase that can be used to identify the stereo, the chiral center or the chiral phase of the molecule, and the interaction, the diffraction can be used to understand the structure of your molecule when you use the X-ray, wavelength, and the coherence or non-coherence that can be used. Okay, so these are the properties can be measured. So how these next, so how the atom or molecule properties are affected when the light incident on the material. So when the light incident on the material which has the atoms or molecule that can respond to the incident light, that may cause the change of the rotational motion, that may affect the vibrational frequency, or sometimes the electron can be exited from one electronic state to another, the higher energy state. So this all will sell some information about your molecular properties or atom material property. Sometimes you can use this electromagnetic radiation. You can use this electromagnetic radiation to change the spin from one direction to another direction. So you may ask the question. So for whatever you talked now, you are talking about the interaction of the incident light with the outermost electron. Am I right? So that is the most prominent interaction. But now you can look at that when you talk about the spin of the nuclear, spin of the electron, when you talk about spin of the nucleus, especially because these are inside the atom. Okay, so how it is possible to interact with your electromagnetic radiation? You may have the question. So it is very, very simple. So that's why we use the magnetic, so high power magnet we use in the presence of magnet, and we can change the spin from one direction to opposite direction, that is excited state, and that will tell us some information about your molecular structure and everything. That is called nuclear magnetic resonance spectroscopy. Second, you can use the same electromagnetic radiation to knock out one of the electrons from the material, that will tell about the material binding energy and result the structure and other mechanical properties of that material. Am I right? So, and you can use the combination of about rotational and vibrational electronic to study about rotational vibration, spectrophotometry, the study and the rotational vibration or electron excitation. You can use the UV visible, the ionization or UV of those. You can use strong excitation that can be used X-ray or UV, right? You can use in order to ionize the molecule. So these are the things you can get from the spectroscopy. So this is this slide, the list of the so if you use the what spectroscopy will tell what kind of information. Okay, for example, nuclear magnetic resonance will tell about the kind of nuclei or different kind of protons arranged in the particular molecule, which interact with the nuclear spin upon the incident when the light interact with your the molecule. Okay, so electron spin tell about the spin of the electrons in the particular magnetic field. The infrared tell of the interatomic the strength, the interatomic distance between the molecule between the two atoms in a molecule, and the microwave spectroscopy tell about the arrangement of molecule, the angular momentum, everything in here between the two the atom in the molecule. and ultraviolet tell about the electronic the state or the bonding electrons in the or structure of the some of the molecule or coordination complexes. So these are the information can be probed using the various the spectroscopic tool. Okay, so this is what the introduction about the spectroscopy and etc. So if you have any clarification now, this is the first part, and now I'm going for the second part. You can now stop me if you want to clarify anything. You can clarify. I can give you a couple of seconds or a couple of minutes also. No problem for me. Do you have any clarification, audience? So for whatever we thought. So, do you have any clarification? Okay, so if you don't have any clarification, then I can move now next topic. That is what I'm going to talk about is another couple of slides, the principle and application of UV visible spectroscopy. I'm not sure about this. May looks very simple spectroscopy. Every institute may have this one box. That is called UV visible spectroscopy, but how many of you really understand this spectroscopy? This may look simple, but which carries a lot of application to understand your material properties. So just a couple of slides that I'm going to tell what are the things that you can use for this spectroscopy to study, to analyze your material in order to understand your material property. Okay. So this spectroscopy use the UV visible radiation, UV visible wavelength region from 200 to 800 nanometer. From 200 to 400 is the UV region is called a nanometer, and from 400 to 800 nanometer is a visible region. So you can use this electromagnetic radiation to excite the electron from the one electronic energy level to next higher electronic energy level. Okay, so that means each energy level, the electronic energy level. Possess them associated with the various rotational and vibrational level. So when you excite the electrons from the low energy electronic state to higher energy electronic state, so there is also associating vibrational and rotational energy transition also. So this is the reason when you see the UV visible absorption spectrum or the band, it always so broad in nature. So because why it is so broad in nature? Because it carries the rotational and vibrational along with this electronic transition. So the energy required to excite one electron to a higher energy level, you require a lot of energy. So compared to the rotational and vibrational transition, the electronic transition always require higher and higher energy. This is the reason why we need 200 to 800 nanometer wavelength of the light. Okay. Okay. This is the so what how this will this will interact with the sample, and what information is going to tell about that. So in order to understand that, we will use two laws that is called Lambert's law. What this law tells that the decrease the intensity of the radiation with the thickness of the solution is directly proportional to the your intensity of the incident radiation, that means incident light. That means whatever the light you use, the incident the light or incident radiation, that light, if you have the higher energy, you will get the more information about your material properties. So if we fix that and mathematically you derive that, you will end up with the tell of the absorption or absorbency A, that is directly proportional to your the thickness, the path length of your sample. If the path length is more, the more absorption will be more and more light will be absorbed. The path length will be less and the absorption is less, and the number of light absorbed the material is less. That is what the Lambert's law tells. So after the another law, the Beers combined with this, and he tell about another, the intensity of the radiation, the decrease of the intensity of the radiation with the thickness of the solution is directly proportional to the not only the incident radiation, it also the concentration of the solution. Okay, along with the thickness of the solution, path length. Okay, so use the same formula and put some other condition and do the differential and integration, and you will arrive with that absorbency that is directly proportional to the concentration as well as the path length. So in the UV visible spectrophotometer, when you do the analysis, the path length is constant, maybe 1 centimeter or 2 centimeter, only the path length. But I think 1 centimeter should be. So, but the only you are changing the concentration. If you change the concentration, your absorbency will increase. That means the molar extension coefficient will be higher and higher. Okay. So, but the more how much amount of light is absorbed, there is some certain condition is there. We will discuss what the condition is there. But the Beer-Lamb's law, you can use this law to quantify to determine the amount of unknown substance or unknown sample dissolved in the particular concentration and the solution. So now you may ask the question now, is there any difference between the amount or concentration? So the amount is a quantifying something, okay, or quantity of something, whereas the concentration is the is an amount of something in a volume of something. That means, for example, 100 gram quantity of sugar or 10 gram of quantity of sugar is a amount, whereas the 10 gram of sugar dissolved in 100 ml of water is called as a concentration. So if you have to understand, we can measure the unknown concentration, the solid concentration, using the Beer-Lambert's law very accurately. That is what we can use. But it has a certain limitation, this law. So what is the limitation? Because when you have the more and more concentration, if you take the high concentrated solution, but you see, look at when you take high concentration solution in a particular solvent, what will happen now? The molecular interaction it become more and more. When you have the more and more molecular interaction, that create unnecessary scattering, unnecessary reflection. So the amount of light you pass, so that may not get the molecule which is responsive, which is required to excite the electron to higher energy level. Okay, so this is the reason what happens sometimes. What happens this straight line you won't get sometimes straight line. The straight line may bend either in the positive side or in the negative side. So these are the deviation of the Beer's law. It also depends on the instrumental correction also. So the light you use, the monochromatic light, sometimes that may not be much more monochromatic. If you use the polychromatic, you cannot use the Beer-Lambert's law in the UV visible. So the most of the UV visible spectrophotometer, we use the monochromatic light only, which you do the wavelength scan versus and absorbency. Wavelength, number of wavelength scan, wavelength will be in the nanometer scale in the x-axis, and the y-axis will be plotted as a absorbency. Okay. So, but in order to, once UV visible light incident on the molecule, once the incident, so the electron has to populate from the low electronic energy level to higher energy level. So in order to populate this electron, it has to satisfy some certain selection rule. So why this selection rule is required? Because it is going the electron, the spin from low energy to higher energy level. If the same spin is also in the excited state, that means the total spin multiplicity in the both the ground state and excited state is not changed. If the total spin multiplicity in the both ground state and excited state, it is not changed, that means that transition is called allowed transition. You can see there is a amount of light is absorbed is more, that means molar extension coefficient will be so efficient, so you will get much more intense. So allowed transition means you will get intense absorption band. But whereas sometimes what happens, most of the electronic transitions are not allowed transition. What will happen now? There is some forbidden transition also happen, which reduce the molar extension absorption coefficient, that leads to the flat. You will get the intensity of those peaks much more flattened. So you won't get any information from that peak, because if you get some peak from that wavelength, you came to know what type of energy level is there, what type of orbital is excited, the electron from the which orbital is excited, the excited electron from the which orbital. We want to, you know, the which orbital is, you can tell about your molecular bonding or structure or the properties. Okay, this is the reason. So why this sometimes it follow the forbidden transition? Because when the electron is excited, in that time what will happen? It undergoes some spin orbit coupling along with the spin multiplicity, and you look at now that time what will the triplet state will be mixed with that, and now the singlet to triplet will be there. That overall the spin multiplicity now will change it, because ground state is a singlet and your excited state is the triplet. If the ground state is a singlet and excited triplet, the overall change in spin multiplicity is a change almost, so it becomes forbidden transition. This is the reason why the spin multiplicity is not same as the ground and excited state. So the another the rule will carry the Leporti. We talk about the symmetry. Okay, look at now. Suppose you are exciting the electron from the low energy level, which has the one orbital. The symmetry of the orbital something different. If the symmetry when this electron goes to the excited state, higher energy level, and now the orbital symmetry must change there. If the orbital possesses the same symmetry in the excited state also, what will happen now? That it finds this one here, whatever the symmetry is there, same symmetry in the lower energy state also, in the excited state also. That means that transition is called forbidden transition. So the forbidden, if the symmetry changes from lower energies to higher energy state when during electron excitation, and if that means Jared to unjared. Jared means symmetry. Okay, so that means unjared means unsymmetry. Okay, so the symmetry has to change. So the orbital, the motion, the orbital should flip the ground as well as excited state. If the orbital symmetry changes, so that state is called as the allowed state. There, because now the work done by the by observing the molecule, the work done during the observing by molecule with the work done by observing the light in the molecule will be more, so it absorbs the more light, so that you will get much more intense peak, so you will get much more information from that. So these are the two selection rules that must satisfy now. Okay, so what type of that electronic transition that can be used, that can be probed using this UV visible spectroscope spectrophotometer. So there are the four type of transition that can be inferred from this UV visible spectroscopy. One is the transition involving the electrons from the sigma orbital, pi orbital, and non-bonding orbital in the organic hydrocarbon or organic functional molecule. Second is a transition involving charge transfer, because this kind of charge transfer transition will happen especially in the metal ligand coordination complexes. The morning you already know what are the topic, already one faculty has thought about that. And another transition is that if we take a transition metal complexes or these F-log elements complexes will undergo the transition within the d orbital, so that transition also can be probed. So wherever the electronic transition is happening, those places we can use a UV visible spectrophotometer to study about this excitation process. 5 o'clock. So what type of electronic transition that will give the organic molecule? So if you look at now, the organic molecule will give, because most of the organic molecules are made of the sigma orbital. That means a single, the hydrocarbon if we take, that is a C single bond carbon single bond to carbon, or carbon single bond hydrogen. And some of the molecules, organic molecule may have some functional group like NH2 or OH, which carry the non-bonding electron. And some of the organic molecule may have the conjugation, double bond character or triple bond character. So you can look at that. It is a C single bond of the sigma to sigma star transition. The electron is excited from the sigma orbital, lower bonding sigma orbital to anti-bonding sigma star orbital. So that can be probed for using this spectroscopy. Similarly, the electron excited from the pi to pi star, the electron excited from the N to phi star or N to sigma star. So this is so saturated, all saturated hydrocarbon can show the sigma to sigma star, which require the very high energy. That means almost very far UV region. That means around 102, 150 nanometer will require. But this kind of analysis can be done under the vacuum condition, not possible in the UV visible spectrophotometer. So which is possible more than 200 nanometer, that molecule absorb, that light absorbed by the molecule, that can be possible, that can be easily probed in the UV visible spectrophotometer. That means we can study the pi transition, pi star transition, or n to pi star transition, or sigma, or the pi, or n to or n to sigma star transition also is possible to study also. Okay, so these are the terms. So this UV spectroscopy especially used for to understand the conjugation. So, for example, there are the three type of conjugation. Ethylene, which had a one conjugation, whereas another molecule has a two conjugation, whereas another molecule three different conjugation. There are some molecule has a many number of conjugation. The graphene, if you take, that is a series of so lot of electrons, pi electrons will be there in the graphene sheet also if we take that. So these are the conjugation. So many number of conjugation will be there. So if you keep on, so if you see that if you keep on increasing the conjugation, what will happen now? So the energy between the one orbital to another orbital, the gap between where the electron going to excited from the lower energy to higher energy level, the reduces. Okay, that means where the electron can be excited. You look at now, there is a CH orbital is there, there is a C double bond C orbital there. Okay, there is another sigma orbital, there is a 5-star orbital. So if you see that if you increase the more and more the double bond character in a particular molecule, so the HOMO, that means highest occupied molecular orbital, where the electrons is present there, and which electron going to excite it to higher energy level. That means LUMO, lowest unoccupied molecular, the gap will be reduced, so that become once the energy, the gap reduce, so that it can absorb the light using even the visible region. That means it which require the longer wavelength. So you can look at now, as you increase the number of conjugation, the peak will become shifting toward the red. Red shift means higher wavelength of the light. That means which reduces the gap between the HOMO and the LUMO gap. Okay, so if you look at the benzene and the naphthalene and the anthracene, and we increase the pi conjugation system series of, so as you increase the number of pi conjugation, the maximum, the lambda maximum peak will be shifting toward the higher wavelength. Higher wavelength means lower energy. So lower wavelength means higher energy. Okay. For one of the best examples that every day you can see that the carrot, which contain the beta carotene. Am I right? The beta carotene has almost 12 to 13 conjugation is there. So you look at that. That's why it absorbs the visible region. So that gives a red color. Whatever you see the color, that is not absorbed light. Absorbed light color is different. Whatever you see the color, that is a complementary color. All right. So don't misunderstand that absorbent and the complementary color. So you can ask the question whether is it the absorbency or the shifting of the wavelength? Is it depends on the how much big molecule, or it's a type of conjugation? So it is not depends upon how much big molecule. It is depends upon how many number of conjugation is there, how many number of pi bond is there. It depends. Okay, for example, the prednisolone and benzene, the two type of molecule has given, which has one bigger molecule, which is benzene simple molecule. But the absorption you can see that. So it not depends upon the how much big molecule is there. It depends upon the how many number of conjugation is there, how much chromophore there that can absorb the light, and that can show the shifting of the peak and in the UV visible region. So the another information that you can able to tell about the chromophore, which impart the color. So when you introduce some chromophore means the light absorbing molecule, light absorbing a couple of atoms. When you introduce that and the conjugation molecule or in the aromatic molecule, you see that the intensity of the light will increases, as well as the peak will shift towards to the higher wavelength. So whatever the compound, the peak, the shift to higher wavelength is always advantageous to probe the UV visible spectroscopy. All right. So this is. So oxochrome means nothing but which modify the absorption of the light, or which increase the intensity of the light. That is called when you introduce some functional group. Okay, that modify the absorbency as well as intensity of the light, that is called oxochrome. For example, benzene is a 255. When you introduce the one OH group and the benzene, the lambda maximum shifting to the 270 nanometer. When you introduce the NH to amine and the benzene, and it becomes 280 nanometer. That means it's when you introduce the some molecule and the conjugation, so it causes the absorbance as well as intensity of the light. You can see how the intensity varies in the figure as I shown here. Okay, so based on this, you can differentiate, or you can type the shifting of this absorption band. For example, if absorption band shift to the more and more higher wavelength region, that is called beta chromic shift. For example, 4-nitrophenol, when you treat with the under alkaline condition, become 4-nitrophenol anion, the well-known molecule. The most of the people used to study for catalytic properties of metal nanoparticle, this because this is the 4-nitrophenol. When become 4-nitrophenol become 255 nanometer. When it's ionized, become 400 nanometer. That is called beta chromic shift. So sometimes what happen? Some molecule will shift towards to the blue region, the lower wavelength. That is called the hypsochromic shift. And some of the molecule may increase the intensity of the light in particular wavelength. That is called hyperchromic shift. And where is the hyperchromic shift, which leads to the decreased intensity of the light. The decreased intensity of the light means the observing the power of those molecules will be reduced. That means molar excitation coefficient will be less for the particular molecule. So this is what how this absorption can be differentiated in various types. Okay, the next is the sometimes this beta chromic shift or this hypsochromic shift. It depends upon the what kind of type of solvent you use when you measure the during the analysis. Okay, for if you use the highly polar solvent when you measure something about your sample, but the highly polar solvent can interact nicely with the pi the conjugation, whereas the n pi star will affect. Okay, but that will increase the energy level, so that now your absorption maximum will shift towards to the blue the lower wavelength. So sometimes the solvent may enhance the shifting of the absorption maximum at the higher wavelength. So that is called sometimes we can say solvochromism effect also. Some molecule will show very beautifully solvochromism also. So these are the things what information tells. This all the things means. So with this you can easily understand about your molecular properties or your material properties. Okay, so with this, we can theoretically we can calculate using the Woodward-Fisher rule whether it is a the trans-net conjugation, whether it's a diene, whether it's a homo diene is present in the molecule. Based on that, some value we can give that how much aliphatic chain, how much external conjugation is there, so how much additional number is additional conjugation present. Based on the some value we can give using the Woodward-Fisher rule. With this Woodward-Fisher rule, we can calculate, we can determine theoretically without measuring the UV visible absorption spectroscopy. If they given some molecule, this may be asked in the GATE or CSIR exam also. They will give some molecule, they will ask you to calculate, they will ask you to find out what is the lambda maximum value. So how to do that? For example, if we take this this ring is contained the trans site, okay, which has the base value for 215 as per the Woodward-Fisher rule. You look at the trans site ring as a 215 base value. So if we fix the 215 base value and you look at how many extended the conjugation is there. It has the one extended conjugation, that means you can add 30. So how much the substitution is there? One substitution, 2 and 3, 4, 5 substitutions there. Each substitution you can multiply with the 5. So 5 into 5, 25. So how many exocyclic double bond is there? Okay, this is the one trans-siding. After this double bond is called as a exocyclic double bond, you can add another 15. So you add some of this all the value, you will get 285. If you go to dissolve this compound in particular solvent and measure the UV visible spectroscopy, that you will see the very nice peak, almost 282 nanometer peak. So with this Woodward-Hoffmann, this Woodward-Fisher rule, we can calculate theoretically which wavelength that molecule will absorb in the UV visible absorption spectrum. Okay, so this is a very good. So sometimes this is a very important for the master degree student and undergraduate student. So how you can calculate, how you can tell about which molecule at what wavelength you will absorb the light in the UV visible spectroscopy. All right. So, next electronic transition that can be probed using UV visible spectroscopy, that is inorganic metal coordination complexes, which show the DD. So the transition happen within the d orbital. Okay. So this complex also show the ligand to metal charge transfer or metal to charge transfer or ligand to ligand charge transfer. So based on this value, one can able to probe using the UV visible spectroscopy whether it's a DD transition, whether it's a LMCT, whether it's a MLCT, whether it's a LL. Okay, for example, these are the how the transition takes place. These are the one coordination metal complexes, the orbital energy diagram based on the molecular orbital theory. So this is the T2G orbital, this is the EG star orbital. If the transition is happened within this level, what is called from T2G to EG, that is called DD transition. If the transition happens from the ligand orbital to your metal d orbital, that is called ligand to metal charge transfer. If the electron excited from the here metal to the antibonding the ligand orbital, that is called metal to ligand charge transmission. So with the UV visible spectroscopy, we can easily probe whether what kind of transition takes place in particular coordination complexes. With the transition, you are able to say, so what is what is your coordination complex geometry, whether it's a high spin complexes, whether it's a low spin complexes. Once you know this, whether it's high spin or low spin, the geometry, we can easily detect the bonding and structure of your coordination metal complexes. Once you know that, we can easily understand the properties of your particular molecule. So once you know the properties, you can choose the what kind of application it can be used. That is what our ultimate aim, why we are studying this kind of spectroscopy. So for example, this is a hexaco nickel 2 plus complex giving the so many peaks. The peaks at lower the higher wavelength region is called a DD transition, and most of the DD transition is so the Leporti forbidden or partially allowed transition. Where there is another intense peak which has the ligand to metal charge transfer is a highly allowed transition. So from these number of peaks, as well as the intensity of the peak, the energy the energy of those peaks. With this information, one can know about the what type of metal the central metal atom in the coordinating or electronic configuration of those metal. And with the peaks, the position in the various wavelength region, that will tell you about the whether it is what type of the crystal field stabilization energy, whether it's octahedral, whether it's a tetrahedral, or it's quadruplanal. So the intensity will tell about whether it's a fully allowed or partially allowed. If you have the higher intensity, that has a more molar absorption coefficient, which is the lower intensity, almost flattened. That means it's almost a forbidden transition. Okay, so this is another very important. You can look at now the epsilon value for the sum of the transition. So the charge transfer complex is a fully allowed transition. Usually that is a more than 1000 epsilon value. Epsilon means the molar absorption coefficient. This is very, very important. Many times is asked in the NET or GATE examination. We can note it down also. So when the epsilon value from 1000 to 10, that is a partial allowed transition. That means that may be spin allowed, but where the Leporti forbidden transition, that is especially DD transition. The electronic transition happened within the d orbital. That kind of transition that show this epsilon value. There is a 10 to 1 to 10, that is a spin allowed or symmetry forbidden transition. That also will show octahedral, most octahedral complexes. The less than 1, both spin allowed forbidden as well as a symmetry forbidden, Leporti forbidden transition will show. So these epsilon maximum value. So remember that when epsilon maximum is very high, that has a fully allowed transition. With the epsilon maximum is less than 5 or within or 1 to 10, that the transition may be partially allowed or fully forbidden transition. You have to remember that. Okay. So this UV visible spectroscopy is a very indispensable tool to understand the nanoparticle properties or nanocluster properties. You know, the nanoparticle, one of the very hot field now, the current time. So every people are working in the nano. So you can look at the bulk gold. It is always yellow color, but it is in few centimeter. The size you can look at, you can measure few centimeter scale. But when you reduce that same bulk, the gold, the size is almost a few nanometer. You see the based on these nanometer. Whether it's 100 nanometer, 50 or 20 or 10, we show the different color. So you see the spectroscopy, you can probe. So what is the size of this nanoparticle? You can easily tell about that. So this peak is a characteristic surface plasma resonance. We show the oscillation of the collective oscillation of conduction, the free electrons. This free electron will oscillate. When this oscillation is frequency matches with your incident light frequency, there is a resonance that is called a peak. Okay. So similarly, you can also know you can also calculate the shape of the nanoparticle. You can tell about from the UV spectroscopy. Second, you can also see the quantum dot size. Okay, the quantum dot is a very nice luminescence material which show the quantum confinement effect, the discrete energy level. So molecule also discrete energy level. Am I right? So you can easily understand from the absorption peak, you can calculate what is the band energy. Once you know the band energy, you can tell about what is the size of the quantum dot. It's also useful for the UV spectroscopy. Okay, next is the instrument. This is a flow chart for the double beam instrument UV visible spectroscopy. For the light is coming and the grating, fall on the grating where there is when the grating means refraction is happen. Refraction means separate the different frequency. That means the polychromatic become monochromatic light. That couple of monochromatic light is inserted on your sample. Now the scanning will be done. When the scanning during the scanning, only one type of wavelength will be absorbed by your material. So that shows when one type of wavelength is absorbed by your material, that shows the very intense peak. From the peak, you can get the information what type of your material. Okay, the source typically used. This is also very important. Sometimes they ask question also for UV light. For UV region, they use a deuterium lab. For the visible region, they will use a tungsten lab. This is commonly and most commonly all the instruments you can find. Sometimes they use the xenon or SLAM to get the highly monochromatic radiation light. So we always use the monochromator. It is like a grating or the diffraction. The gratings also they use. The detector, mostly we use a detector is a photomultiplier detector. Is all the UV photometers are available. So the sample holder is used for a visible region. We use the plastic or glasses, or the UV region we use the quartz cell, because the quartz cell UV region will not available.
drive பண்ணிட்டு சொன்னீங்களா சார் நீங்க ஓ வேறயா
ஜேம்ஸ் பாண்ட் படத்துல நடிச்சிருக்காரு அவரு
என்ன சார்
அவர் நடிச்சிருக்காரு என்ன படம் சார் அது சார் நீங்க நடிச்ச படத்துல என்னங்க ஜேம்ஸ் பாண்ட் ரேஞ்சில பேசிட்டு இருக்கோம் நம்ம இங்க லோக்கல்
சார் நீங்க என்ன நினைச்சீங்க சொல்லுங்க லோக்கல் தான் முதல்ல தெரிஞ்சுக்கணும்.
So there is a noise for the talk. Please can you turn off mute your audio?
Wow,
extraordinary naanga.
Okay.
Gentleman la.
Seri.
Extraordinary.
Seri.
Please mute your audio.
Yes sir, சொல்லுங்க. நீங்க what is your role?
அதான் extra. இது பண்றீங்களா? இது extra.
Please mute your audio.
வேங்கேனா என்ன?
Convener, there is a disturbance for me. Convener, இருக்கீங்களா?
So you can continue, sir. Sorry, actually, when mic was
there is a disturbance.
Not.
Please ask them to quiet the mute their audio.
I asked them, sir. I asked them. Now you can continue, sir.
Okay. Shall I continue or what?
You can continue, sir.
Okay, I can continue now. Okay, fine. Thank you. Okay, this is a sample folder. So this is the principle and application of UV visible spectroscopy. So to summarize this, the UV visible spectroscopy can be used to prove the electronic transition of your organic functional group, to understand the type of conjugation, the type of functional group present in the molecule, and this can be also used to prove the metal nanoparticle, to understand the size of the particle. It is also used to understand the size of the quantum dots. It also used to understand the metal ligand coordination complex structure and bonding. So it's a one kind of indispensable tool. So sometimes the CSIR-NET question, they may ask what type of selection rule and what is the Leporti or spin selection rule, and what type of the source used in the UV visible, and what is what is sample folder used for the UV visible. Sometimes they may ask the detector also. So you have to be careful. This is to summarize. So do you have any clarification up to now from the spectroscopy to UV visible spectroscopy? Audience, do you have any clarification? Yes or no? If you say no, I can continue.
No, sir.
No. Okay, fine. Thank you. And the next one is the infrared spectroscopy. I have another half an hour or more than half an hour. Can I take or more than half an hour, or I have to complete it within half an hour? Okay. So next is the infrared spectroscopy. It's another important spectroscopy, molecular spectroscopy, which used to understand the functional group, to get some information about the functional group the present in the molecule. Okay. So it's a spectroscopy which interact the infrared light with your molecule. So we use mainly the three type of NIR region wavelength from the mid IR and near IR and far IR. So we use mostly the mid IR to get the information about the functional group molecule that works between 400 to 4000 reciprocal centimeter. So why I say here reciprocal centimeter means wavelength, wave number. So mostly I will say here wave number. Okay, all right. So let us now understand what is the infrared spectroscopy. So UV visible spectroscopy will tell the electronic the electronic excitation or the electron information about the molecule. Okay, but what infrared spectroscopy? So infrared spectroscopy tell about the how these light interact that cause the vibration between the two atoms. So, so based on that, we can easily deduce the bond length as well as the bond angle or particular, and also you can understand the what type of functional group present in the molecule. Okay, this is the what infrared spectroscopy. So what principle use the infrared spectroscopy? So you can use the classical mechanics here to understand that. So consider the simple harmonic oscillator, so where the two mass consider as an atom or atom connected by one massless spring, and we connect that creates some restoring force due to the displacement of these two atom with the help of this spring. So that force that is called restoring force is created, which the force is directly proportional to your displacement of this atom, that the interatomic distance. But this, though it can displace this atom through the spring, but that is in equilibrium position. So you can take now, you can use the potential energy in the help of Schrödinger wave equation. Put it that we can derive one equation that is a very big equation. I'm not going to derive this all the things. Simply I can say here with the help of this Schrödinger wave equation, we can deduce the vibrational frequency, the new oscillation, that is equal to 1 by 2 pi square root of f by u. F is here is a force constant. Nu is equal to reduced mass. So what this equation tells, carefully you should listen here. The vibrational frequency is directly proportional to the force constant. That means if the two atom which is connected through spring, that is nothing but is a bond. It's a kind of one bond. were connected by the two atoms. If this bond strength is more, your force constant is more. Your force constant is the high, what will happen? Your frequency is very high. Am I right? That is what it tells. You see the another one more term which is in the denominator, that is called reduced mass. The reduced mass is nothing but what type of atom is joined between this through this spring. Okay. If it is the atom, the size is less, you will have more high number of frequency. Okay, the isolation. So the frequency will be more. If an atom mass is high, so you will get low frequency. So this is this information, what is this? Infrared spectroscopy. That means infrared spectroscopy about the oscillation between the two atoms in a molecule. So what type of vibration it's going to create. Okay. So you look at now when the two atoms in a molecule vibrate, when this vibrational frequency matches with your light absorbing frequency. Okay, you know the light also called as a frequency. Am I right? Because energy E is equal to h nu by c lambda by h nu. But nu is equal to c by lambda. That means c into nu bar. Nu bar is equal to wave number. Okay, remember that. So frequency when this light absorbed frequency matches with your this displacement frequency, there is a resonance that gives a peak. That is what infrared spectroscopy. Look at now. If there is you can understand in potential energy term the vertical curve, there is a nu zero, that means the ground state energy, vibration energy, and then a higher energy, and first vibration, second vibration energy, and third. If you see that, look at this graph, this figure. If you go from 0 to higher level, then it become very close line. So once you cross this close line, it follow the unharmonic oscillator. No more the harmonic oscillator concept we will use here. So that means this can be applied within the from low frequency, that means the low level, low vibration energy region. When you go for higher and higher, because it follows the unharmonic oscillator where your bond will break. Am I right? So that means now we can put the selection rule here. That means the selection rule is the 0 to 1. It can be observed the light, 0 to or 1 to 2 can be observed the light, or 2 to 1 can be observed the light. If you go more than that, higher the higher energy level more and more, it become unharmonic oscillator. So that means you can now put the selection rule will be the delta n is equal to plus or minus 1. Okay, the next important selection rule for the infrared spectroscopy, during the oscillation or during the frequency or during the displacement of these two atoms, there will, because atom is nothing but the connecting the two atoms through the one bond, the two atoms will be the same electronegativity or different electronegativity. If the two atoms are connected with a different negativity, when it oscillate, there will be the change in the interatomic distance. Due to that, there will be the change in the dipole moment. If the change in the dipole moment during the oscillation, if it's not equal to 0 or higher or lower the dipole moment, that means that molecule can absorb the this infrared radiation. If the change in dipole moment if equal to 0, that means during the oscillation the electronegativity difference is not changes during the displacement. If that means that molecule can be called as a IR inactive. So that is the reason most of the diatomic molecule like nitrogen, hydrogen, oxygen, these molecules are said to be IR inactive, whereas most of the heteroatom molecule like a CO, CO2, H2O, HX, these molecules are called as a IR active molecule. Because of why? HX or CO, you can see that there is a lot of electronegativity difference. HX, hydrogen, and X is a halogen. So halogen has a very high electronegativity than hydrogen. So when it oscillates this HX bond, there is a very nice dipole moment changes will happen. So that changes lead to the absorbance of the infrared radiation. So this is a two selection rule, and this is a principle for the IR spectroscopy. So how do you understand which molecule can give you how many type of vibrational frequency? Vibrational band. In order to understand that, you can see that first you can assume that, so when you have the molecule, you take the couple of molecule in a box. In the molecule, it can have free to move. Okay, how many times it can move, how many directions it can move. If we put the Cartesian coordinate, it can move three kind of direction. So either the X direction or Y direction or D direction. That means it has a 3 degrees of freedom. That means the molecule has that you can put the 3n. N means n number of molecule because when you take in the container, it can be n number of atoms and n number of molecule. Am I right? It becomes 3n. It has 3n degrees of freedom. So in the 3n degrees of freedom, again it has a 3 translational motion. That means 3 plus. Okay. So how many kind of rotation? Because when molecules move under the room temperature, under the thermal energy, it can move rotationally, it can move vibrationally, it can move translationally. Am I right? So if it is a non-linear molecule, it has a 3 type of rotation. If you have a linear molecule, it has a 2 type of rotation. So now you know the 3n plus 5 or 3n plus 6 for linear non-linear molecule. Now you don't know what is the vibration frequency. If it's 3n is equal to 3 degrees of freedom plus 2 rotation for linear molecule plus vibrational motion. So if you want to subtract, get the vibrational motion is equal to 3n minus 5 for the non-linear molecule. If you calculate that, you can tell about how many kind of vibrational modes will present for the linear molecule. 3n minus 6 for the vibrational mode for the non-linear molecule. So if you use this formula, you can tell about the how many number of vibrational peaks that molecule will give. So you can easily understand from this degrees of freedom. Okay, that is the what. I hope you understand what is the degrees of freedom. So then, okay, now we understand how many type of degrees of the vibrational modes that each molecule can give. Either linear molecule, if it's linear molecule, 3n minus 5. If it is a non-linear molecule, 3n minus 6. So once you understand, now you can, what are the types of vibration the molecule can give. So these are the 2 type of vibration, mainly fundamental and non-fundamental vibration. Non-fundamental vibration is the higher energy vibration. We forgot about now. We are not going to talk about that. So now if you look at the fundamental vibration, again it can be the stretching or bending vibration. The stretching will be symmetric or asymmetric stretching. The bending can be the in plane or out of plane, which is the scissoring or rocking or wagging or twisting. So to understand that, you can look at this simulation, how this fundamental vibration is happen in a particular molecule. So the symmetric, how it is stretching, and asymmetric. The symmetric and asymmetric stretching the change in the interatomic changes between the 2 atoms. Whereas the in plane or out of plane stretching is the changing of the angle of atom will change between the 2 atoms. So when it changes, there will be change in the dipole moment. There is a change in the vibrational energy. So that gives that absorb the vibration, the infrared radiation, and that gives a resonance, which gives a peak. From the peak, we can come to know what type of functional group present in the molecule. This is the ultimate understanding of your vibration spectroscopy. So the infrared spectrum usually plotted between the percentage of transmittancy, and the x-axis is the wave number, usually per centimeter. That is not wavelength, that is a wave number. Okay, you have to remember that. So how it can be used? It can be used for the to understand the molecular geometry and the structure and the bond length as well as bond angle. Just now I told you how you can understand the bond length or bond angle. It's also understand the trace amount of gases, what type of gases is present in your system. It can be used for quantity as well as quality purposes. Okay, so for example, here the vibrational modes of carbon monoxide. So carbon monoxide usually is a linear molecule, which use the formula 3n minus 5. So how many vibration modes will be there? Carbon modes, 3 molecules are there. 3 into 3, 9 minus 5, 4. It has a 4 kind of vibrational mode. Okay, 4 number of vibrational mode. So among the 4 number of vibrational mode, one will be symmetric stretching, another will be asymmetric stretching. So another will be bending, another is a rocking, 2 is a bending vibration. With symmetric, okay, so this much, how much symmetry is happening, the same amount of another atom will be happened, C double bond O. Okay, but this will cancel, and the dipole moment with this A side. So what will happen? Overall change the dipole moment will be 0. So that means this will be inactive. Symmetric stretching will be inactive. Remaining 3 peaks I have shown here, which portion will come out here for the carbon dioxide. Okay. So what information we can get from the IR spectroscopy? You look at now the wave number region. That means this is the high energy state from the left to right. From the 3000 to 4000 will tell usually always the functional group which possesses the highly electronegativity atom. Where is around 2500 to 1800 will present always C triple bond and C triple bond is the multiple bond system. Where is the below 2000, that means around 1600 to 1800 will always present the double bond system called C double bond O, C double bond N, and NH bending vibration. Where is the below 1600 from 400, this is called the fingerprint region, is another important advantage of this FTIR spectroscopy. So the most information that you will get about your functional group is above the 1600, above from 2 and 400 reciprocal centimeter. All right. So these are the what I said shown here. So now we will understand how to differentiate one molecule to another using the IR spectroscopy with the different using the functional group. Okay, let us now go one by one. Okay, look at now carbonyl compound. Why I took carbonyl compound? Carbonyl compound is the mostly possessing all kind of organic molecule. Okay, whatever the molecule you take in your body also is present. Important molecule is the carbonyl compound, and moreover the carbonyl compound can be easily identified, distinguished in the FTI region, which show the high intense band at 1700 to 1800 reciprocal centimeter inverse, and this can be differentiated very easily with the shifting of this band. So what are the molecules this CO carbonyl group present? Acid, ester, and and as well as aldehyde and anhydrides, acid anhydrides, and amides and acid halides. Okay, amides and acid halides. So now, how to differentiate between aldehydes, acids, and ketone? Okay, look at now ketone, and ketone will always give you the absorption band from 1710 to 1000 or exactly that, but I'm not saying exactly, maybe 2 or 3 such a frequency may differ. Okay, whereas aldehyde you can, because why it gives 1710, because it has a positive inductive effect that double bond C double bond O partially become single bond. Okay, also remember that, because due to the positive inductive effect, so the such a frequency will be less for the ketone. Whereas aldehyde you can see is a very less positive inductive effect, because hydrogen is there, it gives strong intense peak to 1720. Okay, whereas if you go acid, it's a negative intense peak, you will negative inductive effect it will give you due to the negative inductive effect. So the touching frequency will increase compared to aldehyde and ketone around 17 to 13 centimeter inverse. We can see the absorption one absorption band. So how to differentiate now the esters, acid anhydrides, and acid halides? Look at now esters, the strong will give strong negative inductive effect, because of due to that your double bond category increases, so that increase the searching frequency 1750 7050. So look at the acid anhydride, it's a two kind of CO double bond. One will give you 1810, another will give 1716. So acid halide, look at now, because there is strong negative inductive effect, because halide is electron withdrawing group now. So the C double bond category will increase, the structuring frequency will be increased. So that is the reason it increases 1800 for the structuring frequency with the intense peak in the CO. These are the way you can easily differentiate what kind of the functional group is present in the molecule. So now look at the amides. So if you take the amides, though it has a strong inductive effect, NH2 is present because NH highly electron withdrawing group, but the resonance dominates here. Since the resonance dominates here, the C double bond will become partially single bond character. So now that causes the great reduction of the C double bond searching frequency, the 16-18 centimeter inverse. Okay, this is the way how we can differentiate this carbonyl functional group in the FTIR spectroscopy. So let us now learn how to differentiate the aldehydes and the ketone. Look at the aldehyde functional group there. It has a two functional group, aldehyde, C double bond O and CH. Where the C double bond will give 1720 reciprocal centimeter, where the CH will give you such a frequency 2960 reciprocal centimeter. When you go for ketone can only give the C double bond searching frequency 1710 to 1720 approximately, but where the CH touching frequency is absent. This is a way how we can differentiate whether your molecule, the molecule contain is an aldehyde or ketone when you measure the FTIR spectroscopy. Okay, how to differentiate acids and alcohol? Look at the acids now. Acid has a OH touching frequency and CO touching frequency and the C double bond touching frequency. Alcohol, if you look at now, it has a OH touching frequency and the CO touching frequency, where the C double bond touching frequency is absent. And moreover, when the acid is there and this one, when you go for acid, because the acid, there is existence of the hydrogen bonding. Because of due to hydrogen bonding interaction, this peak almost the very broad. It shows the very broad in nature, almost shift to the 3400 sometime. Whereas the alcohol will show the sharp peak at a higher wavelength region, wave number region. Okay, to understand that, look at that. This is the one pentanol. You see the how sharp it's given around 3400 reciprocal centimeter. So if you look at the, this is another isopropanol. Okay, alcohol. If you go for the acid, xenic acid, you can look at this due to this hydrogen bonding interaction. The intensity of the OH touching frequency is reduced with the shifting of the almost 200 nanometer, 200 reciprocal centimeter. So similarly, benzoic acid almost reduced. You can see there is almost structureless. This very broad peak is shown here. Am I right? This is a way how one can differentiate whether your compound is having acids or alcohol. Okay, next, how to differentiate the phenols and aliphatic alcohol. Phenol is aromatic alcohol. When you do the aromatic alcohol, you show the OH touching frequency around 3400. Because of it has some resonance effect, so the OH touching frequency will affect. It may shift from 3300 or 3350 something, but the OH doesn't have. It will show very sharp peak around at a higher value touching frequency region. So on the CO touching frequency, you can see that for aromatic alcohol 1060, where in the aliphatic alcohol we saw the 1100. This way you can differentiate whether your sample has a aromatic alcohol, whether it's aromatic alcohol very easily. For example, the higher spectrum of the phenol and the aliphatic alcohol, one can easily differentiate how this peak is structure release changes. Am I right? Next, how do you differentiate the amides and amines? Look at the amides. Amides has the C double bond O and NH touching frequency around 3350 centimeter inward, and it has CN touching frequency, and this NH bending vibration is a 1620. You come to the aliphatic amine. Aliphatic amine also see NH touching frequency around 3350. It is also CN touching frequency 1650, same, but when you come to aliphatic amine, the C double bond O touching frequency is missing. And moreover, you look at the NH bending vibration, here is 800 centimeter. So this way one can differentiate whether your compound having the amide or amine, even though it has a primary amine. So here you have to be very careful. So you can also differentiate this amide as a primary, secondary or tertiary one. If the tertiary one there is no peak here. If the secondary or primary is there, with the primary amine there, it will show the two absorption peak equal intensity. And if the single peak is there, if the secondary amine is there, then will show the only one singlet at the around 3,300 centimeter inward. This is the way you can easily understand whether your compound have the primary or secondary amine. Okay, this is a way, another way. So next, how do you differentiate ester, acids, and anhydride? As I said already, ester possesses a strong negative index effect, which was 1750, and the CO touching frequency is 1200. Whereas you can look at here, this acid anhydride, the CO touching frequency is 900 to 1300. This is a way you can easily understand. If you come to the acid halide, the C double touching frequency is a little higher, and the CCl touching frequency you can find out the 900 region to 1300. So the acid halide you can differentiate with based on this alkyl the halides CF, CCl, CBr, CI. As you know that CF is a more the electronegative difference between the carbon and the fluorine is a higher, so it has a higher touching frequency region. At the same time, you can look at the as it comes to the below the periodic table, the electronic difference will be decreasing. And moreover, as I said, you will remember the first time when you talk about the principle. So this higher touching frequency is also indirectly proportional to the reducer mass. So if you increase the from CF to carbon, this carbon iodine bond, so iodine has a more bulky, more atomic mass. Okay, so that also reduces touching frequency. This is a way you can easily understand, differentiate during the IR spectroscopy measurement. And next very important thing is how to understand whether it's an alkyne, alkene or alkyne compound. So look at now this alkyl CH touching frequency will be 3000 reciprocal centimeter, and the double bond CH will be 3100, and the triple bond CH will be 3300. You can remember like 0, 1, and 3, like that you can remember. Okay, the 3100 and 3300, like that you can remember very easily. Where the the single bond C will give 1200, C double bond C 1600, C triple bond C will give 2100. You can remember like 1, 5 and 6, like that. So 5 times is 4 times increases, and C double bond C, and this increase almost 5 times increases. Okay, well, look at the CH bending vibration. CH bending vibration for alkyl 720 reciprocal centimeter, and alkene will show 1000. This is the way also we can easily differentiate. Where is the alkyne CH such bending, it's not so much significant. This is a way you can one can easily understand whether your compound has the alkyne, alkene or alkane. Okay. So the effect of hydrogen bonding. So when hydrogen bonding is interact within the molecule, how you can understand? Whenever hydrogen bonding is exists in your molecule, the OH touching frequency is always very broad and shift into the lower frequency compared to the free hydroxy alcohol. So this is a way you can easily differentiate whether your compound has the exist hydrogen bonding or not. So the instrumentation, if we talk about, this is the instrumentation is available in the market, which we are having. We have the 3 type of IR instrument: dispersive, Fourier transform, FTIR, and non-dispersive instrument. The dispersive instrument, I have shown the flow chart here, and the IR source mostly use a nuanced glober, which can heat and which can produce the IR region. So the IR emission, you can easily probe that when you cook the idli. When you take out the idli, you can see that some vapor will come. That is what IR radiation. You can feel that. And the detector used for this IR, this is a thermocouple, and it is made of thermoelectric effect or nickel platinum resistant, or for photoconductive detector may be used. Detector is an important job with them to convert the photon to electric signal. That is what detector can do here. And this is the optical use for in the IR in order to diffract. These are the window, very important. Usually the KBR window is constantly used for the instrument. So another important breakthrough in the IR spectroscopy. So if you look at if you measure the IR spectrum in the before the 1990, you have to spend for at least half an hour to 1 hour to get the one spectrum. But when FTIR comes now, within the 10 to 5 seconds, you can get the full spectrum, because in the before 1990, look at we use a dispersive IR spectroscopy, which has a frequency domain only. But now what you are using FTIR, it has both frequency as well as time domain, which works under diffracto interferometer, and which has a coherent, which has a interference, which has the this destructive conference interference happen. So that collect all the frequency will give you within a second all the spectral region, immediate understanding of the functional group. This is one of the advantage for the FTIR spectroscopy. The very great application is FTIR. Okay, actually it's a very breakthrough in the scientific community, the FTIR Fourier transform infrared spectroscopy. All right. So these are the problems I have given for the MSc student. Based on my my lecture, you please identify what is this compound, what is the problem to containing this compound, what it is. Okay, you student can tell me. I will give the 1 minute time. So with this, I will complete my lecture. Thank you for your kind attention. Thank you very much. All right, for your passion. So this is the problem. MSc student or undergraduate student, you please identify what could be this compound, what this IR spectrum correspond to the what compound. You have to tell me the answer for the problem 1. So the convener or organizing committee member can take the responsible for this if you wish. Otherwise, you can go for completing of this session. Thank you. If you have any clarification, you please feel free to ask me any question.
Excuse me, sir.
Yes.
Excuse me, sir. Hello.
Yes.
Sir, actually, now the time is 5 o'clock, sir. Already, students are get ready for to go home, sir. Kindly, we can start the session, sir.
Yes, Sweta has answered for problem one pentanol. Yes, right, correct. Yes, I appreciate you, Sweta. Yes, organizer. Yes, you can do whatever you want to do. I don't know who is talking to me.
Good morning, sir. Good afternoon, sir. Sir, no one is there to ask any questions, sir.
No
Everyone,
right.
so no, they are not raising any questions.
You can go ahead, please.
They are not.
Yes,
yes sir. They are not raising any questions, sir. I think everything is clear to them. Yes, sir. So we will move forward to our concluding session, sir. That is, we are going to give vote of thanks, and this vote of thanks will be given by our student, the second BSc student, Sneha.
Okay.
Sneha, are you online?
Yes, sir.
Okay. Can you give the vote of thanks, please?
Okay, sir. Yes, sir. Good evening to one and all gathered here. This is Neha from 2nd BSc Chemistry. On this wonderful evening, I would like to present the vote of thanks. We take this golden opportunity to thank the representative chief guest of today's function, Dr. A. Murugata sir, Dr. S. Chandrasekhar sir, Dr. A. S. Ganesh Raja sir, Dr. K. Rajkumar sir.
Sneha, 1 minute. Sneha, 1 minute. While you are speaking, we are giving vote of thanks. Can you open your video and then you can give, if it is possible. Video mode.
I'm not ready, sir.
Okay, start.
Okay, sir. Good evening to one and all gathered here. This is Neha from 2nd BSc Chemistry. I would like to present the vote of thanks. We take this golden opportunity to thank our representative chief guest of today's function, Dr. A. Murugata sir, Dr. S. Chandrasekhar sir, Dr. A. S. Ganesh Raja sir, Dr. K. Rajkumar sir, for attending this function in their busy schedule. We will cultivate the advice you gave us in real life. Thank you, sir. I extended my gratitude to Representative Head of the Department, Mrs. Gomati ma'am, not only for spending the time with us today, but also for encouraging us achieve many endeavors. Thank you, ma'am. It is my pleasure to thank the dignitaries, teachers, and staff members on and off the stage, not only for participating, but also for guiding us to a beautiful life. And last but not the least, our beloved audience for making this a webinar as a great success. Once again, I thank you all wholeheartedly. Thank you.
Yeah, thank you, convener. Thank you, organizing committee, for giving this opportunity. Thank you very much. Can I go out?
Thank you, sir. Thank you very much for your participation and giving a wonderful lecture, sir. This was very informative, sir. Thank you very much, sir. In future, we will be happy to conduct more seminars like this, webinar like this. So all the participants.
Dr. Karthikeyan, actually there was a request from me. They asked me to do the NMR because at the time completing all 3 kind of spectroscopy is impossible.
Yes, sir.
If you give me one more opportunity, the NMR is also very useful for the student,
sure,
which is very important for them. Okay.
Sure, sir. Sure, sir.
So I'm pleased to give the one more also lecture. No problem for me. Thank
Sure,
you.
sir. Sure, sir. We will soon arrange one more webinar in continuation of this webinar itself, sir. So we will be conducting this, and this time, sir, we'll start with you, sir, because already too late is you gave the lecture too late, sir. So thank you for your participation and giving this informative lecture, sir. And all the participants, please give your feedbacks so that we can improve on this webinar. And next time, hopefully, we will conduct conduct this webinar more smoothly. And the webinar link is already, this feedback link is already given in this chat box. So you can go there in the chat box and you can give the feedback. And once you give the feedback, you will get your participation certificate directly through mail. Okay. So if it is clear, you can always ask us. All these slides and PowerPoint presentations will be available on our PMIST website. You can go there in our department website, and you can go and download all these this presentation. Okay. Our
Sir,
HOD
can you send the feedback link?
Gomati ma'am.
I would like to thank all the speakers and our department faculty members for the one kind cooperation for the successful conduction of this webinar. And I also thank all the participants to make use of this opportunity and kindly give us some positive and both positive and negative feedback to increase our program in future. Thank you. Thank you very much.
Okay, thank you, ma'am.
Thank you, sir. Thank you.
So we will conclude today's webinar with a good note, and hope in the future we will conduct this webinar, this extension of this webinar more smoothly. Thank you, everyone.
Sir, please can you share that feedback link once again?
Ma'am, this feedback form is available in the chat box. I have given this chat box. In this
Sir,
chat box,
due to network problem, I couldn't get that feedback link. Please kindly share it once again.
Sorry to interrupt. No problem. I will send the feedback link through your registered mail ID. Don't worry. If you are not get from chat mail, I will mail you to all.
Okay, ma'am. Thank you. Thank you.
Ma'am, again, I have sent the feedback link on the chat in the chat box.
Okay, sir. Thank you.
Yes, ma'am. Through this link, you can give your valuable feedback to us, and then you will receive your participation certificate via mail.
Okay, sir. Thank you. Thank you for everything.
Okay. Thank you, ma'am. So thank you all participants and respected guests. Thank you for participating in this webinar. Thank you.
Thank you. We can conclude, Danish. Thank you. Danish, sir. Danish, sir. Hello.